Hello, Daniel.
Good morning, all. Welcome back to QFA 2021. Dr. Subhashish Banerjee will be chairing this morning session of day 4. In this session, we will be having two amazing talks, one from 9:30 IST to 10:30, another from 12 to 12:50 IST. I request Dr. Banerjee to take over.
Thank you, Jyoti. It gives me great pleasure to have Professor Daniel Lidar to start this session today. Let me give a very brief introduction to Professor Lidar, though he doesn't need much of an introduction to people in this community. So Lidar has made huge contributions to the field of open quantum systems and quantum information, and he's at the University of Southern California for quite some time. He's also the director of the USC Center for Quantum Information Science and Technology, and the co-director of the Lockheed Martin Center for Quantum Computing. He is a fellow of many international physical societies, such as the American Physical Society and IEEE. And today he will be talking to us about algorithmic break-even in quantum annealing. So without more ado, I pass it over to Professor Lidar.
Thank you very much. Let me try to share my screen. I'm not used to WebEx, so please let me know if this is working. I'm now in full screen mode on my laptop. Can you see my screen?
Yeah.
Okay, great. Okay, so thank you for the invitation to this very interesting conference. It's 9:30 p.m. here, and I guess it's morning for most of you. So good morning. I will talk about a topic I like to call algorithmic break-even in the context of quantum annealing. And so let me start by asking this very simple question: what is a quantum speedup? So what do we mean by quantum speedup? Well, there's obviously this is not a new topic, and I'm sure everybody has opinions about it. So I want to define quantum speedup in the traditional sense, not in the sense that we've been hearing about recently in the context of quantum supremacy, which essentially is a discussion primarily about fixed size problems. And I don't want to talk about quantum speedup in the context of constant prefactors, like a factor of 100x better or so, because prefactors are essentially very classical processor dependent. So I want to think about the idea of a quantum speedup in the traditional algorithmic sense, where we have a quantum advantage relative to some classical algorithm in the time to solution metric. So the time to solution metric can be defined rigorously, and I could do that if anybody's interested later. But what I mean is simply how the time to solve a problem scales with the problem size n. So for example, what kind of quantum speedups could we get? The most famous example is Shor's algorithm, where we have an exponential speedup. The classical time for factoring is exponential roughly in the number of digits, and the quantum time is polynomial in n. Right, so that's an example of an exponential speedup. A different type of quantum speedup would be one where we have a lower exponent, for example, an exponential in q times n, where q is the quantum exponent, versus exponential in c times n, where c is the classical exponent and q is less than c. And so this is what we hope for in the context of NP-hard problems. We don't really have proofs of such cases yet, but this is certainly the expectation for quantum versus classical in the context of NP-hard problems. Or we could have a lower degree polynomial, n to the q versus n to the c, again with q less than c. And if you think of n as the size of the database, then Grover's algorithm is an example of such a speedup. So a quantum speedup, I want to define it as the time to solution scaling better for quantum computing than for all classical algorithms, right? And this is a heavy burden to prove that you have a scaling that is better on the quantum computer than for any and all classical algorithms. And in some sense, that can involve an exhaustive search over all classical algorithms, or if you can provide a mathematical proof based on some other principle, then of course that's great. Okay, so with this notion of a quantum speedup in mind, let's imagine that we had an ideal quantum computer without any decoherence, and let's consider what happens if we ran a quantum algorithm on it that is supposed to have an exponential speedup, like in quantum simulation. So if we then look at the time to solution on a log scale as a function of the problem size, well, then the classical exponential time would look like a straight line here, and the quantum polynomial time would look like this. And in an ideal case like this, we would have a very clear quantum scaling advantage for all problem sizes n. Of course, we all hope to see something like this one day, but so far we haven't observed it on quantum hardware. Instead, perhaps something like this happens where, because of decoherence, we see a slowdown of some sort, where let's say we still had a quantum polynomial scaling, but it was a polynomial with a higher degree. And in that case, we would only see a speed up for much larger problem sizes, but for small problem sizes, we would actually see a slowdown, right? But things could be worse. We could have stronger decoherence, and in that case, the polynomial could be of even higher degree, and the quantum speedup, if it exists, would be masked up to even larger problem sizes, and perhaps we wouldn't be able to distinguish it from a classical exponential scaling in practice. Right? Or it could be even worse than that. What if there's just too much decoherence, and perhaps this is what is happening in the NISQ era in which we live now. In that case, it could be that decoherence is so strong that actually even the quantum scaling is exponential. And that certainly seems to be the case for many algorithms that people are running now on cloud quantum computers. And in that case, we wouldn't observe a speed up at all. Right? But actually, things could get even worse. And you could have, let me call this a quantum blow up, where for sufficiently large problem sizes, the probability of finding the right answer on your quantum computer is zero. You just never observe the right answer. And in that case, the time to solution, of course, goes to infinity. Right? And in fact, we'll see an example of this towards the end of the talk. Okay, so let's look at an example in which we tried to demonstrate a quantum speedup. And this was done in the context of running problems on the D-Wave 2000Q, which is the fourth generation D-Wave machine. And in the example that I'll describe to you, we compared D-Wave to simulated annealing, which is of course, a well-known and highly respected generic classical algorithm. So the problem we're interested in is to try to find the ground state of a certain family of spin glass instances of up to 2048 spins. And exactly what the family is, I'll get into later. Right now, I just want to give you a visual of what's happening. So we actually found that for this particular carefully selected family of spin glass instances, we found an example of an algorithmic speedup of the D-Wave machine versus simulated annealing. Here's the time to solution on the log scale as a function of the number of variables, and it's the square root for technical reasons we don't have to get into. If you plot the time to solution versus the square root of the number of spins, you get these straight lines, and the blue curve is D-wave, and the red curve is simulated annealing. And you can see that not only is there a constant factor speedup, which as I said in the beginning, I'm actually not so interested in, there's also a slope difference between these two curves. The difference is slight, but it is statistically significant. And if you perform a fit, you find that the slope for the D-wave scaling here on these spin glass problems is 0.76. And the slope for simulated annealing is almost exactly 1. And so this is in fact, the first example of an experimental limited quantum scaling speedup on a non-trivial problem. And this is limited because it's relative to a particular classical algorithm, right? This is D-wave in comparison to simulated annealing. And remember, when the way I defined a quantum speedup, I emphasized that the speedup has to be relative to all classical algorithms. So it's nice to have a speedup relative to a good classical algorithm like simulated annealing, but when we dug a little deeper, unfortunately, the speedup disappeared. So in particular, when we compared the D-wave scaling to two other classical algorithms, one is called spin vector Monte Carlo, and the other one is called simulated quantum annealing. The results were better for those later two algorithms. So spin vector Monte Carlo is actually a fully classical model of D-wave where you replace every qubit by a magnet, like a rotor in a plane, and like a compass needle in a plane. And that algorithm, this classical model of D-wave, actually beats the performance of D-wave itself. So here's the SVMC scaling 0.5. And simulated quantum annealing is a type of quantum Monte Carlo algorithm, and in our tests, it had the best scaling of the algorithms that we tried, with an exponent that is less than half of the D-wave exponent. So so it was nice to find a limited quantum speedup relative to a particular algorithm, but this is not an absolute quantum speedup because there are better algorithms, classical algorithms out there that beat D-wave at this game of solving spin glasses. Now, this is, of course, not unique to D-wave. Again, we live in the NISQ era. And so I'm not going to show you here an example of an algorithm, but rather a different phenomenon. This is work from a few years ago on the IBM QX5, which was a 16-qubit device, where we simply looked at the problem of preserving the fidelity of a single qubit. And so this is what you're seeing here is fidelity as a function of time, where fidelity is computed by averaging over many different initial states, random initial states. And you see how the fidelity drops very sharply on this IBM device. But fortunately, there are techniques that we can introduce, like dynamical decoupling, which is related to the spin echo from NMR, that allow us to improve the fidelity and recover some fidelity, at least for sufficiently short times until all is lost for longer times. So I mentioned this as an example of what is happening in the NISQ era, where across the board, whether we're talking about quantum annealers or gate model computers, we're dealing with relatively low fidelities. But importantly, there are error correction or error suppression methods, in this case, dynamical decoupling, which allow us to do something about this. So let's go back to this cartoon version of what's going on with quantum speedups and consider what happens when we run an algorithm like the one I was talking about before, a hypothetical algorithm that gives us an exponential speedup when there's decoherence, but we introduce quantum error correction. Right? And so if previously the uncorrected quantum scaling was worse than classical, with quantum error correction, what we hope is going to happen is that it's going to push down this the scaling of the uncorrected quantum down to something that looks like a much milder form of decoherence, right? And so if we could do this, then the quantum scaling advantage returns for sufficiently large problem sizes, at least. And I would call this an example of algorithmic success with quantum error correction, right? And so algorithmic success with quantum error correction is the case where the corrected quantum scaling is better than both the uncorrected quantum and classical scaling, at least for sufficiently large problem sizes. And this is the holy grail, right? If we could do this kind of thing, which has never been demonstrated yet in an algorithmic setting, then that would be a home run, and quantum computing would be off to the races. So in other words, we accept the existence of decoherence, which can ruin things very badly for us. And then with error correction, we can try to push the scaling back to the regime where we get a quantum advantage. But again, this has never been demonstrated. So perhaps we can settle for something that is a more modest goal at this point in time. And this is what I call algorithmic breakeven, which was the title of the talk, right? So algorithmic breakeven. What I mean by that is this scenario where we perform some form of error correction that doesn't try to beat the best classical algorithm, but it does improve upon the uncorrected quantum scaling. Okay, so algorithmic breakeven with quantum error correction is the case with a corrected quantum scaling, which is the orange curve here, is better than the uncorrected quantum scaling, the purple curve, but it's not necessarily better than the classical scaling. All right, so it's a more modest goal. And if we can achieve this, then at least we know that we're on the right track, right? And so the question is whether this can be achieved with existing quantum hardware in the context of some non-trivial computational problem. Right, so that's the central question I want to address in this talk. Can we demonstrate algorithmic break-even for non-trivial computational problems on existing quantum hardware? So to introduce this, I'll talk about it in the context of D-Wave. I want to make sure that we're all on the same page what the D-Wave machines do, and I'll try to give you a very rapid introduction to what they do. So they are programmable quantum annealers, right? They are primarily designed to solve optimization problems. And those optimization problems are formulated as Ising spin-glass Hamiltonians. So here's an Ising spin-glass Hamiltonian. It has some local fields, and it has interactions. And the problem is to find the minimizing spin configuration. Here, the sigma z's are, you can think of them as classical variables in this context, where plus minus one. And so you're given the h's, the local fields, you're given the j's, the couplings, and given the h's and the j's, you try to find the minimizing spin configuration of this Hamiltonian. So that's a spin glass problem when there's some disorder in the j's. And the way that quantum annealing goes about it, and the way that if we could build such a machine, we would want to do it in hardware, is by essentially evolving a different Hamiltonian adiabatically. And the different Hamiltonian is the one where we add a transverse field. So you put sigma x's on all the spins, not sigma z, sigma x's on all the spins, with an annealing schedule A of t and another annealing schedule B of t, such that the A of t is very large in the beginning and the B of t is 0 in the beginning, and then you slowly decrease A and you slowly increase B, and by slowly I really mean adiabatically, so try to stay in the ground state at all times. And if you do that, then you evolve from the ground state of this transverse field, which is the uniform superposition state, to the ground state of the Ising Hamiltonian, which would be the solution to the optimization problem. And the adiabatic theorem of quantum mechanics guarantees that this can be done if you evolve sufficiently slowly. And of course, how slowly is the question, because that will determine whether you're going to get a speed up or not. Until recently, it wasn't actually known whether you can prove a quantum speed up in the context of such an algorithm. But very recently, this year, there were a couple of papers that actually proved superpolynomial and exponential speedups for certain oracular problems graph-based problems that put this whole notion in a theoretically firm setting. Okay, so this is what D-Wave tries to do, and they have built by now 5 generations of chips that implement a version of this quantum annealing algorithm, starting with the D-Wave 1, which was installed at USC back in 2011. It had nominally 128 qubits, and then the second generation, a couple of years later, the third generation, the 2X, already with 1152 qubits, and then the D-Wave 2000Q, which I mentioned earlier, with 2048 qubits. And currently, we have the D-Wave Advantage with more than 5,000 qubits. So, the progression here is that every 2 or 3 years, the number of qubits have doubled in these devices, which is certainly an impressive pace of engineering. So to go into a little bit more depth, the qubits here are superconducting niobium flux qubits. And in the first 4 generations, up until and including the D-Wave 2000Q, the underlying graph, connectivity graph between the qubits was called the Chimera Graph, which is depicted here. And so every red circle is a qubit. It's a tiling of K44 subgraphs. So every qubit, let's focus on this one here, is connected to 4 qubits across, and 1 above and 1 below. Or this one is connected to 4 qubits on the other side of this unit cell, and then 1 to the left and 1 to the right. So every qubit in the bulk of the graph is coupled to 6 other qubits, except that some of them didn't yield. So there are some holes in this graph. So there are some imperfections like that. And the newest generation D-Wave machine, the Advantage, has a different graph. It's called Pegasus, and I don't have a picture of it here. It looks a lot more complicated, and every qubit is coupled to 15 other qubits. So certainly a more connected graph that you get. But let's focus, for the purposes of this talk, on the Chimera Graph. So you can think of the Chimera Graph as a square grid of L by L unit cells. The number of qubits is 8, because there are 8 per unit cell times L squared. And in the largest Chimera Graph of the D-Wave 2000Q, you can have up to 6. So the graph has 16 such unit cells, so you can program problems that have up to 2048 qubits by choosing up to 16 unit cells. Okay. Now, 2 more parameters that are very important here are the T1 and T2 times, and they are measured to be on the order of about 10 nanoseconds. Whereas the annealing time, which is the time it takes to evolve from the Chern's field Hamiltonian to the Ising Hamiltonian, the spin glass Hamiltonian, cannot be chosen to be less than 1 microsecond. If you try to go faster than 1 microsecond, then, well, users can't do it. There's some filtering that prevents it. D-Wave itself can go faster than 1 microsecond, and then there's actually some interesting results that they have recently for these much faster anneal times. But as a user, you can only go as fast as 1 microsecond, which is 100 times slower than the T1 and T2 times. And so intuitively, you would think, and the intuition is not wrong, that there should be a problem here, because you will decohere faster than you can evolve the computation. In addition, we should also worry about temperature, because we're trying to stay in the ground state. So we have to worry about the gap from the ground state to the first excited state. And for most problems of interest, that gap can be much smaller than this temperature of 10 millikelvin, which is the temperature of the dilution refrigerator. So if you take these 2 factors into account, relatively short T1, T2, and a relatively high temperature relative to the gap, then the answer to the question of how quantum are these machines is somewhat. right? And so they're obviously not in the fully coherent regime. Hopefully, they're not in the fully decoherent regime. And other experiments that I won't talk about here have probed this, and the answer somewhat is I think pretty accurate. So again, they're not fully decoherent, and they're certainly not fully coherent. In any case, as far as I'm concerned, these machines, like all other NISQ era quantum computers, I think of them as test beds for algorithmic scaling with noisy qubits, right? And because the qubits are noisy, we should do error correction, or at least error suppression. Okay, so now let's go back to the idea of algorithmic breakeven. And let me tell you about some results that we obtained now quite a while ago, where we used the machine we had at the time at USC, which was the D-Wave 2, that yielded 503 out of 512 qubits. And the problems we were interested in were these Ising spin-glass type problems, where there are no local fields, just the couplings, just two-body terms. And the J's are chosen randomly from this set of values. Okay, so then we chose 1,000 spin-glass instances, so 1,000 instances of picking all the J's from this distribution. And we looked at D-Wave's ability to find the ground state, which we computed separately on the side on a classical computer for different sizes. And okay, and so when we do that, you can convert the finding the ground state, the probability of finding the ground state out of many runs into a time to solution. And so the time to solution here measured just in terms of the number of repetitions, of the number of annealing cycles on a log scale as a function of, again, the square root of the number of physical qubits, had this kind of behavior. And the different colors just represent different percentiles of the distribution of 1,000 instances, right? So 50% is just the median hard instances, and 95%, the 95th percentile are the hardest instances, and so on. So of course, the hardest instances took the longest to solve. So this is without doing any error correction. But when we introduced a form of error correction, which I'll explain in a moment, what we saw was exactly what I've been calling algorithmic breakeven. So with error correction for these non-trivial problems, I mean, they're non-trivial in the sense that I certainly can't find these ground states in my head, and I invite you to try. They are, you need at least a laptop to solve these kind of problems. What we found was that with error correction, the scaling improved. And this was true for all percentiles. Okay, so there's no claim of a quantum speedup here. We're not trying to beat the best classical algorithm for these problems. We're just trying to demonstrate that if we introduce error correction, then we get a scaling that is better than without error correction. Right? And that's what I call algorithmic breakeven. So the error correction scheme that accomplishes this, I'll talk about next. We call it quantum annealing correction, and there's a little schematic of it here. But I want to pause here and just again highlight that this is an example of algorithmic breakeven, which is the idea that you can improve upon the scaling of an uncorrected quantum computer or quantum annealer by introducing a form of error correction. And that's the first step towards restoring the ability of a quantum information processor to demonstrate a quantum speedup. The first step, a necessary step, but certainly not a sufficient step. Okay, so now I want to explain what I mean by quantum annealing correction. So what is this error correction strategy that was used here? Okay, and so what you have to appreciate is that with a device like the D-Wave machine, you can't do the standard type of quantum error correction that we learn about from the textbooks, because there aren't enough knobs and there's not enough control. You can't just implement a set of gates and run an encoding And a recovery circuit and a decoding circuit, those things just are not possible on these devices. We're limited to what you can do with this annealing setup. So what we did to devise a quantum annealing correction scheme was we encoded the Ising Hamiltonian. So the bars here denote encoded variables, and the encoding is done into a repetition code. So specifically what I mean is, imagine that you have, let's say 3 red qubits and 3 blue qubits. So n is 3. So this is your first encoded qubit, this is your second encoded qubit. And so now the logical z is just the sum of the z's on the red qubits, let's say. And the logical ZZ interaction is the sum of the ZZ interactions between the corresponding pairs of each of the 2 encoded qubits. So you can check that these are just the stabilizers of the bit flip repetition code, these terms. Okay, and these are the logical operators also these are the logical operators of the bit flip repetition code. Now, the next thing we do is we add a penalty qubit. And so this is not a standard move in quantum error correction, but it's kind of essential here. And so the goal of this penalty qubit is to keep, let's say the red penalty qubit is to keep the 3 red data qubits in the same state or aligned. So the green lines here mean ferromagnetic couplings. And because they're ferromagnetic, that means that these 3 data qubits, I1, I2, I3, want to align themselves with the state of the penalty qubit. And so that's described by this kind of a term, a ferromagnetic energy penalty. And the reason it has this particular shape is because that is enforced by the structure of the Chimera graph, right? So this is exactly the unit cell of a Chimera graph. Okay, so then after we introduce this penalty, which tries to align the 3 data qubits, we can now combine the encoded Ising Hamiltonian, H bar Ising, with the penalty term, and we can assign a scale to each of these 2 terms. So alpha is the problem scale, which is some variable that we can control, and gamma is the penalty scale, which we will need to optimize because there's going to be a competition between trying to align these qubits and trying to solve the computational problem. Right? So if we make gamma very, very large, it will overwhelm the energy scale associated with the problem, and then it's as if we're not solving the actual problem we're interested in. And so we can't make gamma too large, and obviously we don't want to make it too small because then this alignment will not work well. And so this is the encoded Ising plus penalty Hamiltonian, and then we can add a transverse field. And we cannot encode the transverse field, unfortunately, because the logical operators of the bit flip code for flipping are the product of all the sigma x's. And that's a many-body term, which we don't have access to on the D-Wave machine. So we're going to have this unencoded transverse field term together with the encoded Ising and penalty. And then at the end, when we're done running the algorithm with this encoding and the penalty, then we'll decode each of the logical qubits by that I mean groups of 3 in this example, simply by doing a majority vote. Right? So let's say we get a spin up and a spin up and a spin down, then we'll call it spin up. So that's the scheme. That's the quantum annealing correction scheme. And that's the scheme that explains the results that I showed you from 2014 and 2015, okay, which were the first demonstration of algorithmic break-even. So now I'll talk a little later about how quantum annealing correction works. So let me skip this. Now let's talk about more recent results, where we try to make things considerably harder than what happened in 2014 and 2015. So in particular, what we're interested in was what happens when you introduce what's called J chaos. And so this is what happens when there are analog errors, control errors. And so here again is the general quantum annealing scheme. You have a transist field, which you slowly reduce. You have a problem Hamiltonian or an Ising Hamiltonian, which whose magnitude you slowly increase. And you have programmable local fields and couplers, H's and J's. But now we take into account the fact that there are analog errors, meaning that whereas you wish to program certain H and J values, in reality, you don't get those. In reality, there's some error, delta H and delta J, which you get on the local fields and on the couplers, right? And those errors are real, they're there. They will be there also, of course, in gate model devices in a different form, but it's the same principle. There would be rotation angles, for example, there. Rotation angle errors there. And you could think of these errors as being normally distributed with zero mean and standard deviation eta. So these analog errors have been characterized by D-Wave for example, for the 2000Q device. And they, relative to the maximum H and J values, they have a standard deviation of about 3%. Okay, and so it's well known in the theory of spin glasses that if you have this kind of a term, if there are these types of random errors on the H's and the J's, then you get a form of chaos known as J chaos, which essentially means that the probability of finding the ground state decreases exponentially in a sense that I'll make precise very shortly. So now what we did was we wanted to see if we could make things worse and then make them better through the use of quantum annealing correction. But first, make things worse by increasing the analog error magnitude. So rather than limiting ourselves just to the intrinsic error, so the 3%, that's the eta intrinsic here, we can just add artificial noise by deliberately misprogramming the H's and the J's. And so we did that. And so we added noise, and added noise of going from 3% to 15%. Okay. So as I just said, it's well known in the theory of spin glasses that these kind of analog errors are very bad. And to be precise about that, again, here is the good Hamiltonian, the one that has the ideal H's and J's. And here's the bad Hamiltonian, the one that has some delta H's and delta J's that are normally distributed with standard deviation eta. And so what can be proven, for example, you can consult the paper shown here, is that when you add this noise, this analog noise, the probability that at least one ground state of the intended Hamiltonian, that's the green Hamiltonian, remains the ground state of the implemented Hamiltonian, which is the sum of the green and the red, that probability that you will actually get one of the intended Hamiltonian's ground states goes down exponentially in the number of spins. And the prefactor here is the exponent is eta, the standard deviation of the noise, to some power alpha, which is less than or equal to 1, and it depends on the particular Ising Hamiltonian. Okay, and n, remember, for Chimera, the number of spins, that scales like 8, that is 8 times the number of unit cells, which is L squared. Okay, now that's one important fact. So the probability of getting one of at least one of the ground states of the original problem goes down exponentially when you add this kind of noise. Now, the other thing to know is that you can actually solve any one of these spin glass problems deterministically. Right? You can always find the solution to a spin glass problem if you work hard enough. And so in particular, if you use one of the more efficient methods is called dynamic programming, then you can prove that the time to find the ground state scales like L squared times 2 to the 4L. Okay, so this is this, if you wanted to exactly solve the ground state of this total Hamiltonian, the green plus the red, provided that you know exactly what every value of H and delta H and J and delta J is here. You can always do it in this amount of time. So therefore, if you have a classical computer and enough time, then you can always solve any problem like this in using dynamic programming. And if you wanted to find a ground state of the original, the green Hamiltonian, then you have to divide this time by the probability given here. And if that probability is 1, then there's no effect. And if the probability is very small, then it's going to take you much longer to find such a ground state. And so the bottom line is that there's a classical upper bound on the time to solution that is finding the ground state of the green Hamiltonian. And that classical upper bound scales like exponential in L squared. That's the dominant term. So please remember that we can always solve any one of these spin glass problems classically in a time that scales like exponential in L squared. Okay, so now let's go back to experiments on D-Wave. And what is shown here is what happens when we take spin glasses with this distribution of J's, similar to what I talked about earlier. And I'm reporting to you experiments that were run on 2 D-Wave machines. At the time we had at USC, we had the D-Wave 2X with 1152 qubits, and NASA had a 2000Q with 2048 qubits. So we used both of these machines to generate this data. And so the lowest line here, curve, is with no added noise. Right? So time to solution is a function of problem size, and then increasing values of noise, all the way up to 15% added noise. And if you recall from the beginning of my presentation, I talked about quantum blowup, where you simply never find the ground state anymore. And that's exactly what happens when you add 15% analog error. Then at a problem size of L equals 9, that's where you stop. And for L equals 10, so that's 10 by 10 unit cells, you simply never ever find the ground state, no matter how long we tried. So you see the scaling without error correction. Right? Now, with the same quantum annealing correction technique, this is what happened. So when we introduce quantum annealing correction for the very same set of problems, every single one of these curves with no noise added or with noise added, the scaling, as you can tell by inspection, the scaling for every one of these curves got better. And that's, again, an example of algorithmic breakeven. Now it's in the presence of this very bad type of error that causes J chaos. So the scaling with quantum annealing correction is better than without for all values of the added noise eta. But we want to do a bit more. We want to figure out how good this improved scaling is. And so we can actually perform a data collapse analysis and extract the finite size scaling for these 2 types of problems, without error correction and with error correction. So if we do the finite size scaling, we find that we can collapse all the different eta values to a single universal curve, which has this form. So there are A, B, C, and D, 4 different free parameters here to perform this fit. And the most important one is D, because that's the scaling of the number of unit cells, L, right? L squared is the number of unit cells. So what's shown here is the log of this function normalized so that all the data fits onto one universal curve as a function of L. And this is what happened without error correction. And there was a very disturbing conclusion that came out of this analysis. The D value that we found, right, so L to the D, 10 to the L to the D, the D value is greater than 2. But recall from what I said here that the classical upper bound on the time to solution is an exponential in L squared, right? And so what we found, the disturbing conclusion was that without error correction, the scaling is actually worse than the classical deterministic upper bound. And so in that case, it certainly makes no sense to use this quantum annealing device because it's not worse than the best classical algorithm. It's worse than a deterministic classical algorithm, which is certainly not the best algorithm for solving these types of problems. Now, with error correction, the D value, fortunately, is now found to be less than 2. It's 1.7. In fact, all these other numbers are also smaller. And they all need to be smaller. And in fact, if you look at the absolute scale here, this goes up to 10 to the 4, and this is in the hundreds. So in every sense, but most importantly, in the sense of this scaling exponent, the error correction strategy improves the scaling. And so again, we have an example of quantum algorithmic breakeven. Right? So error correction restores hope here. It's not that we get a scaling that's better than classical, but we certainly get a scaling that's better than without doing error correction. And here it's summarized. It's the same data, just shown a little differently. The scaling without error correction and the classical dynamic programming bound with D equals 2, and then the scaling with error correction, which is below this classical dynamical programming bound and much below the scaling without error correction. Okay, so that's the story of quantum algorithmic breakeven. How much time do I have?
You have around 10 more minutes. 10 more minutes.
Okay, all right. So I assume that includes questions. So I think I have more material, but I think I'll just maybe I'll talk a little bit more about the how quantum annealing correction works, and I'll try to leave some time for questions. So so what I've told you so far is is descriptive and heuristic, but actually we can dive quite deeply into this quantum annealing correction method, and it turns out that to analyze it, we need to invoke some methods from quantum statistical mechanics and condensed matter, and so I think maybe this is interesting as well. So let's formalize what the QAC scheme is, and let's see if we can invoke some theoretical understanding for why it works. Right. So you could think of the QAC scheme as taking a logical problem. So here I schematically drew n logical variables and capital N qubits, and you're making capital K replicas of that problem, and then for each of the logical variables you add a penalty qubit, and these penalty qubits are connected to each of the capital K replicas with a strength gamma, right? So this is the scheme. This is the QAC scheme. Okay, so now let's take this scheme and apply it to a well-known problem, which is the p-body, excuse me, the p-body ferromagnet. So the p-body ferromagnet is the Hamiltonian shown in the round brackets here. It's basically just the sum of sigma z's raised to the power p. It's a ferromagnet, and so there are two ground states, all spins pointing up or all spins pointing down. But now we take the QAC version of this, and so we make capital K replicas, the factor n years for normalization, and we add the penalty term. And so the penalty term has strength gamma, and every qubit is coupled to its 0 qubit, which is the penalty qubit. Okay, so this is the penalty term. So this Hamiltonian Hz represents capital K replicas of the problem Hamiltonian of the p-body ferromagnet. Now we can add a transverse field to it, right? And so the transverse field is just the sum of sigma x's on all the qubits. And we introduce an annealing schedule, which is this capital gamma. And to do annealing, what we do is we start from a very large value of capital gamma, which we slowly reduce to 0. So when gamma is very large, we have just a transverse field dominating, and then as we reduce it, we go to Hz. Okay, so this problem can be analyzed using methods from StatMech. You can compute the partition function and the free energy and so on. And it's known for not the QAC problem, but just the standard p-body ferromagnet under annealing. It's well known that it undergoes a quantum phase transition from a paramagnet, which is when the transverse field dominates, you have full disorder, to a ferromagnet, which is when this term dominates. And that happens at some critical value, gamma sub c. And the order of the phase transition depends on p. When p is 2, we have a second order phase transition, and when p is greater than 2, we get a first order phase transition with an exponentially small gap. Okay, so we can analyze this problem using methods of StatMech. So the p-body ferromagnet with QAC, and here's what happens. So we took the case of p equals 4, which has a first order phase transition, and analytically computed the free energy. And so here you see a plot of the free energy as a function of magnetization. You could think of the magnetization as time, because over here, the magnetization is 0 in the paramagnetic phase, when there's disorder. And then as time evolves, we quantum anneal towards the ferromagnetic phase, right? And there's a phase transition. And this is plotted at the critical value where the phase transition occurs, but with no penalty term. Okay, so with the penalty term here set to 0. So in that case, you just have capital K copies of the problem, and it's just like the standard problem. And then the important thing to notice here is the free energy barrier between the paramagnetic phase and the ferromagnetic phase. So the system has to tunnel through this barrier, all right, to go from the paramagnetic phase to the ferromagnetic phase. Now, if you turn on the penalty, so gamma is 0.5 in this example, and again, you solve the problem analytically, and you plot the free energy as a function of magnetization. Then what happens is that the free energy barrier has now become smaller, 0.04 versus 0.12, and also narrower. Okay, and so the tunneling barrier under this QAC scheme has been shrunk. And that's kind of the key to what happens in these problems. It's easier to tunnel. And that's why QAC is an effective scheme. Now, it's not only that it's easier to tunnel, you can also quantify this in terms of the minimum gap, how it scales. So we can compute the minimum gap, delta, and because it's a first order phase transition, the gap closes exponentially in the number of variables n. And so the number c, this is c here on the y-axis, as a function of the penalty gamma. The number c, using an instanton analysis, we can show that it's e to the minus beta times the area under the tunneling barrier, delta m times delta f. Delta m is this width, and delta f is the height. All right, so it's the area under the barrier. And you can see that c increases as you increase gamma. And particular value of gamma, it goes to 1. So when C is 1, that's when the gap is constant. Right? And for any C less than 1, the gap is exponentially small as a function of n. So increasing the penalty is actually beneficial in terms of making the gap close less violently. Or in other words, turning on the penalty softens the phase transition. So with these StatMech type methods, we can actually analyze the scheme and associate the success of the scheme with the reduction of the tunneling barrier and the softening of the closing of the quantum gap. And in case you're wondering whether this is the scheme with 3 qubits plus 1 penalty, whether that's the only one, of course not. There's actually a more sophisticated scheme that we've also come up with and investigated, and I don't have time to go into it, but I'll just call it the nested quantum annealing scheme. It's some kind of a recursive construction or a nesting of codes. And in that case, we were able to show that the nested scheme reduces the effective temperature of the problem. And so basically, if you can reduce the temperature to 0, you're back to ideal quantum annealing. Right? Any finite temperature quantum annealing is going to suffer from thermal excitations. But if you can reduce the temperature through a coding trick, then you can effectively think of the problem as being free of an environment. And so the message here is that we can reduce the temperature using a more sophisticated error correction scheme by a factor as large as n squared, where n is the number of physical qubits per logical qubit. And so the more physical qubits, the larger your code is, the more physical qubits per logical qubit, the smaller you can make the effective temperature. So you can trade qubits, physical qubits, for an effective temperature reduction. And so this goes towards fault tolerance for quantum annealing. In the limit where we can make the temperature 0, then we would have completely removed the environment. Okay, so that's really all I wanted to say. So to summarize, I've talked about this idea of quantum algorithmic breakeven, which I think of as an intermediate goal for quantum computing, right? So it's similar in spirit to quantum supremacy, but the point is scaling. Quantum algorithmic breakeven is the idea that you would demonstrate an error-corrected scaling that is better than the uncorrected scaling on some non-trivial computational problem. I've argued that it's already achievable in quantum annealing, and you could think of it as an invitation for gate model quantum computation. Thank you.
Thank you very much, Professor Lidar, for this very interesting talk. We have time for a few questions. If anybody has a question, please feel free to ask.
Yeah, hi, Shivashishta. I had a question. Hello, yeah, can you hear me?
Yes, yes.
Yeah, Professor Lidar, thank you for the nice talk. So I'm sorry if I missed this during the talk. So I had a question. So the error correction scheme for the annealing algorithms, do you need to update it each time you come up with a different architecture and you change the number of qubits each qubit interacts with? And how difficult would that be if that's the case?
Every architecture would have its own tailored error correction scheme. Yes. Fortunately, the architectures aren't changing very fast. So the particular scheme that I talked about worked for the Chimera graph. The Pegasus graph has the Chimera graph as a subgraph, so we can actually use the very same scheme, or we can come up with a more effective scheme because of the higher connectivity of the Pegasus graph. And I expect that as generations of quantum annealers are built, and these graphs are only going to get more connected, not less connected. And the more connectivity, the easier it is to implement these types of approaches.
Okay, yeah, thanks.
Okay, any other question? May I ask a question? You
Sure.
showed that, which is very interesting, that even with decoherence, means you can add, do some add noise, with some error correction, and then this break-even is happening. What I was curious about is this what kind of noise you were using, or is it independent of the type of noise that you're using? Was it a bit flip or an amplitude damping, or it doesn't depend upon? It's a query. This.
Right. So there are, let's distinguish two types of noise. So one is the intrinsic noise that is just present in these devices. And the other one is the noise that we added by hand as analog errors. Right. So the intrinsic noise is, you can think of it as T1 and T2 type processes. So there's dephasing, and there's thermal excitations. Thermal relaxation normally in a gate model device would be an error, but thermal relaxation is actually beneficial in quantum annealing because it takes you back into the ground state. All right, so you basically have T1 and T2, and then you have these analog errors. And those are the errors that those three types of errors are the ones that we were dealing with.
If suppose you were to add some more sophisticated error, like something like a noise which has some memory or something like that, do you think something better could happen? Because you see, sometimes this with memory, for example, if you were to add something like an RTN kind of noise, which has a kind of backflow properties,
Yeah.
it does would it helps in some, of course, but then it would be noise specific. But would it be possible? Have you thought about such a thing?
So you know, we're dealing with the actual Markovian or non-Markovian noise that is present in these devices, right? And so when you're talking about adding noise, I assume you're imagining that you would not just do these analog error type noise additions like we did. You would introduce even more noise, but the intrinsic noise is already a combination of Markovian and non-Markovian processes. In fact, 1 over F noise, 1 over F to the alpha type noise is the dominant type of noise that is present in these devices, and it's non-Markovian in character.
Yes, sir. Okay. Yeah. Thank you.
So you know, whatever the error correction method is doing here, it's already dealing with non-Markovian noise.
Okay, that's good. Yes. Okay. So, any other questions from the? Okay, there's a question in the chat box. What kind of this is Anand is asking this question. What kind of quantum error correction techniques would be useful in gate mode? This is asked by one of the students.
What kind of quantum error correction techniques would be useful in the gate model? And so for the gate model, you know, we have numerous error correction codes that have been developed ever since Shor and Steen came up with the first one in the mid 90s. So I don't think we have a shortage of quantum error correction methods in the gate model. We have we have stabilizer codes and surface codes and topological codes and color codes and so on. There's a plethora of options available in the gate model. The quantum annealing case is really interesting because there's a real shortage of error correction ideas there. It's very different from the gate model in that sense. So the example that I talked about here, this quantum annealing correction scheme, is one of the few, one of the very few, one of a small handful of error correction strategies that have been designed for quantum annealing. If you're looking for a place to make an impact in quantum error correction, I would say quantum annealing is the place to be because there are so few known ideas.
Okay. So there are no further questions, then let us
So,
thank Professor Lidar. Okay.
Shubhashita, can I just
Yeah,
ask one
please.
small question? Yeah, Professor Lidar. So
Yeah,
this
go
question,
ahead.
I'm not really
Yeah.
sure about how relevant this is, but it may sound silly. So there are a lot of variational algorithms in place, which can use classical optimization to boost the performance. So do you think for the quantum adiabatic computation, can you have like control pulses which are classically optimized that can actually perform better?
Yeah, yes, absolutely. So it's not exactly pulses that would be relevant here because this is adiabatic, right? So you don't want to apply pulses. You want to do everything nice and slow. Everything has to be smooth. But with that in mind, if you remember the annealing schedules that I was talking about, the A of t and the B of t, the A of t is what controls the transit field, and B of t is what controls the Ising Hamiltonian. The question of how to choose those optimally is a really interesting and rich problem. And if I had more time, I would devote some slides to that as well, because it's something that I've actually worked on quite a bit. It's a really interesting control theory problem. And most recently, it's been realized that there's a strong connection to QAOA. And so the type of schedules that you get in QAOA, if I can use that term, you know, the way that you switch the two fields there, in the limit of large P for QAOA, they tend to become smooth annealing type schedules. And actually, there's very recent work that shows that for QAOA, the optimal schedule is likely to be something like what's called bang anneal bang, where you have a pulse and then a smooth annealing schedule, and then another pulse, and again a smooth annealing schedule, and so on. So there's a tight connection between the schedules, the optimal schedules for quantum annealing, and the optimal schedules for QAOA. There's a lot more interesting work that can be done in that area.
So, but do you think, like, if you were to look at something like this in the plot that you have right now, like, where would that fit? Would that give you an advantage in some sense, or?
Right. Yeah. So just to make it very concrete, if you try to solve the Grover problem with adiabatic quantum computing, and if you, and this is not my result, this is an old result due to Cerf and Roland and Cerf from 15 years ago. So they analyzed the Grover search problem as an adiabatic quantum computing problem. And what they showed was that whereas with a simple linear annealing schedule, or a linear schedule, you don't get the Grover speedup. With an optimized schedule, you can get the Grover speedup, right? So the schedule is extremely important in that context. It's the difference between realizing a quantum speedup versus not.
Okay, yeah, thanks.
Thank you, Dr. Lidar, for this enlightening talk, and Dr. Banerjee for chairing this session. Now, according to today's schedule, it's time for a break. We'll meet again at 12 IST for next talk of this morning session. Thank you.
Thank you.
Hello, Lidar. One question in the Q&A section. Hello?
Yes?
Yeah. The question is the term break even is being used here to indicate the improvement in scaling with error correction vis-a-vis no correction. Am I right?
So break even refers to what happens when you compare the case without error correction to the case with error correction. And you observe that with error correction, let me see if I can find the slide again. When you introduce error correction, you get a result that is better than without error correction, right? So I imagine, can you still see my slides?
Yes, yes.
Yeah, yeah.
Okay, so imagine that the red curve here, that it's moving, all right? So let's say that the red curve was actually like on the previous slide. I got no, okay, anyway. So imagine that the red curve is above the purple curve, and then you start to introduce error correction. And the more error correction you do, the more that red curve moves below the purple curve, right? So the more effective your error correction is, the better you perform. The point at which these two curves cross, again, imagine the red above the purple, the point at which they cross would be the break-even point. Does that make sense?
Thank you.
Any further questions? Okay, then let us thank Professor Lidar once again. Very nice talk. Thank you, sir.
Thank you for the invitation and for the great questions. I'm going to go to bed now, and I hope you have a nice rest of the conference.
Okay. Yes, thank you. Okay, bye. Good night.
Okay. All right. Bye-bye.
Should we start the session?
Sure. So should I start?
Just a minute, sir.
Okay. Oh, okay. Yeah, sure.
Just to
Yeah, no problem.
Yeah, I welcome
Sir, should we
everybody.
start?
Okay, Jyoti. Okay. Please,
Hello
please.
all. It's
Please start,
nice
Jyoti.
to have you back for today's second talk. Dr. Banerjee, who is the chair of this session, will introduce us to our next speaker. Dr. Banerjee.
Hello, am I audible?
Yeah.
Yes, sir, you are audible.
Yes. Yeah. So it's a pleasure Shrikant, Professor Shrikant, to this conference. Shrikant is, of course, very well known in the field of quantum information, and I have known him for quite some time now. And I would say that I started my journey in the field of quantum information with him. So he has visited our institute many times. This time he's doing it on the online mode. I hope the offline mode happens.
Hello?
Hello? Yeah, am I audible? So Subhashish was not audible to me. So
Yes, sir. Just a second.
yeah.
Shrikant, hello.
Ah,
There's some
yeah.
problem in the audio here. I hope you can hear me now.
Yeah, I can hear you now. Yeah.
Yeah. So sorry. So I'd like to welcome Professor Shrikant to our thing, and Shrikant, you can start.
Yeah. Thank you very much, Professor Subhashish, for your kind invitation. And it's a pleasure to be back in IIT Jodhpur, if not physically, then at least online. So I'll be talking about this idea of counterfactual security of quantum cryptography, which is done in collaboration with with my collaborator, Mr. Vinod. Yeah. We can go to the next slide. Yeah.
Sorry, sir. Convenience. You can proceed.
Yeah. So we can go to the next slide. Yeah. The second slide. Yeah. Thank you so much. Yeah. So this would be the brief outline of the plan of this talk. I'll introduce the idea of counterfactual communication, more restricted to counterfactual, to the matter that leads up to counterfactual cryptography. And the protocol itself that was proposed by No will then be presented. And we will then talk about extending this protocol in order to improve the efficiency of the protocol. So that would be the main technical contribution of what I'm going to talk. But there's also an interesting conceptual twist to the paradigm of counterfactuality that I will also be talking about, that goes hand in hand with the improvement in efficiency. And not just No protocol, there have been other protocols that have been proposed that make use of the interaction-free measurement or counterfactual principle. And we will show that, I will point out that this idea that we have for improving the efficiency can also be extended to these other protocols. So it's more like a template, though I will mostly be using the well-known No protocol as my primary example. Afterwards, we will draw certain conclusions to complete the talk. Yeah. Thank you. The next slide, please. The basic principle here is that of interaction-free measurement. And it is, so we have, let us say, a Mach-Zehnder interferometer. It goes back to the 1995 paper. The reference, I think, appears in the next slide, due to Elipsur and Weidman, in which they ask us to consider a photon that's being injected into a Mach-Zehnder interferometer. And as we all know, so once you have this photon going here, so you have a beam splitter that splits these two, splits the photon into the two branches that we may call A and B. And so the superposition here would be A plus B. And they again interfere at the second beam splitter and produce a deterministic detection, let us say at D2. It depends on the particular signs that we have introduced in the two beam splitters, but we might say that you have a deterministic detection at one of the beam splitters. But now when you have an obstruction that is placed on one of the pathways, in this case the pathway A, and colorfully Elipsur and Weidman invite us to think about a bomb that's being placed in this arm, and as a result you do not have any amplitude. So you could have occasionally a photon being absorbed by the bomb and you could have an explosion, for example, but you want to minimize the number of such trigger events while sort of improving your chances of being able to detect whether a bomb is present in the pathway or not. So what happens now, as a very simple application of quantum superposition, is that the amplitude in this arm, you could also have an amplitude that just goes through the B arm. So if you have a detection downstream, it will just happen due to the amplitude that travels along the arm B. But in this case, because you do not have the cancellation that you earlier had a cancellation through interference, you will have a detection both in the detector D2 and D1. So this idea that was originally called interaction-free measurement. So when you have a detection here, for example, in the other detector than the one in which you would have if you had a cancellation of amplitudes and you would have had a deterministic detection at D2. So if you have a detection in the other detector, even though you have a detection here, you know that there was a blocking event, namely the bomb that was elsewhere. So this concept has therefore sometimes been called counterfactual, namely that you have a detection that is elsewhere than the place or the station in which a blocking action has been made. Next slide, please. Yeah, so this is basically the basic transformations that are involved. So you have the arm A and arm B, which I can write in terms of superpositions of the kits corresponding to each of the detectors. So if you do not have any obstruction, then you have a deterministic detection that happens at D1. And so if you have a D2, the other detector firing up, then it only happens when you've had an intervention, that is to say a bomb or some sort of an obstacle that's placed in the arm A. And the detection statistics are again simply like this, that if you don't have a block, you have a deterministic detection that happens at 1. But if you have a block, actually it is 0.25, 0.25. So you could have the photon getting absorbed by the bomb, but otherwise you will have a detection that happens 50% of the times in the detector D1 and 50% of the times in detector D2. So the event of detection in D2 signals to us the presence of an object that is elsewhere. I hope that the reference appears below. Yeah. Thank you. Next slide, please. In 2010, No introduced a very interesting way to harness this counterfactual measurement principle or the interaction-free measurement principle for the purpose of creating a key distribution protocol. So in this protocol, you have a source that injects photon. For example, it could be a laser and it injects photon. You have a circulator here so that you prevent photons that go back to the source. So, and if you have return photons, they just can go only to detector D2. So you have a circulator here. So you have these photons that are injected into the beam splitter. The injected photons will always be in orthogonal states, namely horizontal or vertical. And they are, of course, split at this point, and one of them goes into the arm which is within Alice station, and one that goes farther downstream into Bob station. And as against the original Elitzer-Weidman scheme, the Qkd protocol here involves a Michelson interferometer, not the Mach-Zehnder interferometer that was earlier used. And at Bob station, what he does is to perform two actions. One is to block a given polarization. For example, you could block vertical and reflect the horizontal polarization, or he could block the horizontal polarization and reflect the vertical polarization. So these are the two actions that are possible to Bob. So once a particular polarization, let's say that H has been sent here. Now, if Bob applies the reflect action on H, then the photon returns back here and you have a constructive interference. That is to say, you have a constructive interference between these two arms, and it is similar as the Elitzer-Weidman protocol, and you have a deterministic detection, let's say at the detector D2. On the other hand, if Bob had applied a block action with respect to the particular polarization that had been sent, then you just have the amplitude that travels down from Alice's mirror. In the case of Alice, she doesn't have a choice, so she just applies a Faraday mirror action. So you just have the mirror that always reflects. So therefore, you just have the amplitude that travels down from Alice's arm, and you can potentially have, with probability 50%, a detection that happens in D1 also. And as a result, when a D1 detection happens, Alice will make a public announcement saying that she has obtained such a detection, and Alice and Bob immediately can share a key based on the polarization of the light that has been sent, because she knows what polarization she has sent, and Bob knows the polarization also, and Alice knows that Bob knows, because the blocking action is polarization dependent. So in this way, we find that every time a D1 detection is made, ideally speaking, of course, that you have single photon events and all the components, optical components are working ideally, then you have a key that is shared between Alice and Bob. So this is a counterfactual bit, namely that the blocking action was done by Bob, but the detection happens on Alice's side, and this becomes a basis for sharing the key. Yeah, next slide, please. It's fine. Yeah, so this is what we were discussing about. So it is counterfactual because the detection is an Alice station, whereas Bob tries to measure it. And so the statistics is what I'd mentioned earlier. So if Bob has performed only a reflect action, then you always have a detection 100% probability that happens at D2. On the other hand, if he has performed a block action with respect to the polarization that was sent, then of course half the time you end up detecting the photon, and the other half of the time you can have a D2 detection. You can have a D1 detection, which will signal that there is a mismatch between the polarization that Alice prepared and the blocking action that Bob did, and that becomes the basis of the key, as I was just explaining. Next slide, please. To understand how security arises in this protocol, it's worth noting that in familiar key distribution protocols, let's say, for example, the BB84 protocol or the Bennett 92 protocol, the B92 protocol, the basis of security, if we may summarize it in one line, is that the states that are being sent, the signal states that could potentially give rise to key bits are being sent are non-orthogonal. And as a result, we know by virtue of unitarity and linearity in quantum evolution, we have the no cloning theorem that says that you cannot clone non-orthogonal states. So no cloning theorem becomes the basis of security. But here, surprisingly, we only use H and V. That is to say, we use orthogonal states. So it's worth pausing to think about how security arises. And this was again pointed out by No during his proposal. So we can use this sort of a quantum optical language or a kind of an entanglement language in this case. So the state of the particle after it has crossed the beam splitter, for example, would be something like 0J plus J0. So J could be H or V depending on whether it's horizontal or vertical polarization. So this says that you have the first kit says that you have the photon traveling in Bob's arm with a vacuum traveling on Alice's arm. So in normal quantum mechanical language, we would simply say that there's a superposition of the photon. That is, if you like, in the first quantization sort of a language, we would think about the photon having a superposition of traveling either in Bob's arm or Alice's arm. So here you would say that there's a vacuum pulse that goes along Alice's arm versus the photon traveling in Bob's arm. And the other kit basically says that you have the photon traveling on Alice's arm and a vacuum pulse traveling on Bob's arm. Now, when they announce, so the way that they are going to, they announce their respective actions to estimate the quantum bit error rate. And the idea is that if the error is too large, then they will abort the protocol. So as I said earlier, so the way that they might estimate error is that on the D1 detections that they make, they will check where, rather than to have mismatches between the polarization sent and the action of Bob, they do have a match. For example, if the polarization H had been sent and Bob had applied the reflect H action, then we should have had a detection at D2. So conditioned on having a D1 detection if such an event has happened, or with a D1 detection that you have a vertical polarization was sent and a reflect V action was performed by Bob. So this they find through a public discussion. So that is the number that would quantify the amount of error in the channel that they would conservatively attribute to Eve. But of course it could arise due to noise also, but they can just assume that all of this noise is due to Eve, just to err on the safer side. Next slide, please. So as we can see, though the encoding state that I showed are orthogonal, the corresponding states, reduced density matrices that are accessible to Eve are not. In particular, if we look at rho H or rho V, so what you have when you trace out the Alice part, you have a mixture of a vacuum state and a particular polarization state. So you can find that the distance between these two is actually half. So that then is the key to how non-orthogonality arises. And therefore, Eve's optimal probability to guess the correct polarization given by the familiar formula would be half into 1 plus V, which is 3 by 4. So the possibility for Eve to err would be 1 by 4. That is, there is no way in which she can be completely sure of the polarization that's being sent. Even though the polarizations are orthogonal, because of the superposition that's being set in, it is as if the state that is accessible or that is exposed to Eve is a uniform mixture of the particular polarization state and the vacuum state. And as a result, you have non-orthogonality, and we therefore find that Eve cannot perfectly distinguish the two encoded states, or any attempt by her to try to distinguish them will potentially introduce errors through the information versus disturbance, general result that appears in quantum cryptography. So what we now wish to do is so this being the no protocol, the efficiency of this protocol is just 1 by 8, because 50% of the time you have the detections that happen on Bob's side. So technically with probability 1 by 4. So of the total number of number counts that we make, on 1 by 4 of the occasions you have detections that happen on Bob's side, and only with probability 1 by 8 you can generate a key. So the task we want to ask is whether these detections of Bob's side, which are essentially sifted out in the no protocol, can we recycle them back into the protocol and use them for the purpose of key generation. So that is what we want to do. So let's consider the provisional protocol, wherein we use the DB detections for key generation, and we will continue to use D1 detections based on the counterfactual principle. And as in the no protocol, we want to use it only for error estimation. But it's important here that the DB detections are not announced. So if we assume that single photons are being sent and that all the optical elements are ideal, then Alice and Bob know. So if Alice has sent a photon and it has not returned to her, so she assumes that a DB detection has been made. So in this way, Alice and Bob can certainly establish a key between themselves, but on the question of how secure it is, we will just consider. Now, prima facie, the advantage of this modification is that the efficiency of the protocol is doubled, because here, like I said, the number of times you have a detection on Bob's side is 1 by 4, and the no protocol's efficiency is 1 by 8. So we have actually doubled the efficiency. So far, so good. But then we will show that with the modification that we made, it is 100% vulnerable for the reason that we will just talk about next. Yeah, next slide, please. Okay. So the idea here is that with this sort of a modification, Eve can launch the perfect attack. Namely, she can extract information without introducing any noise. So the state of the protocol after the beam splitter action we've already seen. So that's the superposition state which we wrote in the second quantization, sort of a quantum optical notation. Now what Eve can do is she can have a probe on her side and she can entangle it with a unitary operation. For example, let the probe be prepared in the state which is epsilon naught, and let the attack unitary that Eve uses be described in the following way, namely that if you have a state alpha and you have a unitary this way, and so you have the probe that just picks up the the identity of that particular signal state. So if it's 0, then you get epsilon 0 or epsilon h or epsilon b. So if a vacuum state was sent, then of course epsilon 0 remains epsilon 0. Otherwise, it gets modified. And if you have a vacuum state, then that was sent, then if you have an EJ, just to complete the full description of the unitary, then we would say that the state is unchanged. So this is the way that we describe. Therefore, after the attack, what happens is earlier the state that we had was some J0, that was the ket, and then we have the second ket, which has taken on, which has got modified in this superposition state according to the state of Bob that has just been encountered. So the probe becomes entangled with the state of Alice and Bob. And on the return mode, what Eve does is she simply reverses, she just applies an unattack, if you like, which is U inverse on the return probe. So in the initial part here, this is the state that goes in the onward direction. Bob may or may not apply the block action. He might apply a reflect action, in which case then the U inverse will perfectly return it back to the original state, or the person might apply a block action. Next slide, please. Yeah, so there are a few points to note here, that Bob cannot test for the coherence of the beam splitter arms from the DB detection. So once Bob has a detection on the DB arm, then obviously he cannot test for the coherence between these two arms. And once you have a DB detection, Eve's probe is collapsed into a state which has the imprint of the particular polarization state that was sent. So she gets complete information on all the DB detections that happens. And in all the other cases, namely the cases where you had a reflect action, so Bob's, or when only a vacuum state was sent, yeah, so what you find is that, yeah, the application of U inverse will take us back to the initial state of the probe. And this means that the probe becomes disentangled with the Alice Bob state when Bob has applied a reflect action. It doesn't get disentangled when Bob applies block action, but it will not matter, because once the photon is detected by Bob, then the fact that there was an entanglement cannot anyway be found out by Alice or Bob. Hence, Eve can potentially get all the information on the DB bits without introducing any error in the channel. It's important to note here that there is no contradiction with our earlier claim that Eve can only distinguish these two with probability 1/4, since the key rate is now modified and the key rate is exactly 1/4. So I mean, only the amount of information that she's allowed to get, she is getting, except she's not introducing any errors. Next slide, please. So the new protocol then essentially is modified, that we have is to take the provisional protocol, the plus point of the provisional protocol, namely that we have the enhanced efficiency by allowing the direct detections of Bob through his block actions to be considered as the key. On the other hand, you have this powerful noiseless attack that could be launched by Eve, wherein she can get 100% of the information without producing any noise. So we want to correct it. And there's a very simple fix, namely that there's a quantum flip operation that flips the polarization of the photon between H and B. That is, when on a certain fraction F of the photons, both Alice and Bob can apply the flip operation, namely that they can flip horizontal to vertical polarization and vertical to horizontal polarization. So in Bob's case, if he applies RH, namely reflect the H polarization, followed by a flip, then his action is to block the V polarization. That's what he would do if a V polarization came. On the other hand, he would reflect the H polarization, which is then flipped to V. So that would be the effective action that he performed. Notice that this is also an orthogonal state-based protocol like No09, since the flip action only toggles between two orthogonal states. I want to stress this because we don't want to introduce non-orthogonal states and thereby make it closer to something like BB84 or B92. So the point was we want to still retain the fact that it's an orthogonal state-based in terms of at least the polarization states that we prepare. It's an orthogonal state-based protocol. Next slide, please. Right. So now let's try to understand. I'll just try to I will point out now why introducing these flip actions in a very simple way makes the protocol secure. And this is what we like to call as counterfactual security. Earlier, I mentioned about counterfactual cryptography, where the key bits are generated through the counterfactual principle. Now, we also have counterfactual communication, where you can have communication being made through the counterfactual principle. We also have counterfactual computation in the that has been studied. In all of these, the idea is that we have the counterfactual or the interaction-free measurement is the basis of the particular quantum information task that is being performed. So to that, we wanted to add this twist where even a security arises out of the counterfactual principle. So the idea here is basically that we will continue to rely on the statistics of counterfactual detections in order to indicate the security of our proposed protocol. But the detections that we made, that is to say the key bits that we generate, will be obtained by the non-counterfactual bit. So that is the kind of twist to the counterfactual paradigm that we bring, namely that the key bits that we generate are based on non-counterfactual detections, but the statistics that indicates security would be based on counterfactual detections. So in this case now, supposing Eve launches the attack U as we mentioned before in the noiseless attack case. So she produces an entangled state that looks like this in equation 10, namely that the particular polarization gets imprinted on the probe during the onward leg. Now, if Alice were to flip and Bob were to apply the reflect J option and introduce the flip as well, then what happens is that we have the scenario of equation 11, which is the same as 10, except that the J has got flipped to J bar, meaning to say if J is H, then J bar would be V. So both of them have flipped their respective polarizations. Now notice that if Eve had not attacked, then we would still have a detection at D2. So this is something that they can find out by subsequent classical post-processing and classical discussions over a public channel, that if they both of them had flipped the polarizations, then you expect it to be the same as when neither of them had flipped the polarization, and you would have a detection at D2. But the moment Eve entangles, she cannot be completely sure that as to whether a flip action has been performed or not. And this means that applying the U inverse action, she will not be able to disentangle the probe on those occasions where they had flipped. For the following simple reason, a flip action would essentially take the ket, which is given in action, which is given in equation 12, namely it takes the state J epsilon J into the state which is J epsilon 0. So if a flip action had not been done, then the U inverse would have perfectly disentangled her probe from the Alice and Bob's particle, and therefore they recover their coherence, and Eve is thereby not indicated or not revealed. But the same U inverse action, if it were to take us back to the state which is J bar epsilon naught, then we find, namely that it takes it to the state which is J epsilon naught. If it takes it to the state, then we find that such a unitary action cannot exist, right? Because you need to have two orthogonal states that become non-orthogonal under the action of this unitary. So in general, she cannot perform any such unitary in a noiseless way. Next slide, please. So in this case, the way that they define error, the earlier definition of error that we encountered was that they check the D1 detections and find out whether the polarization sent and the reflect actions were matched, because you need a mismatch in order to have a D1 detection. So when you do not have instances where this mismatch does not happen, that is to say they both are matched, you have an error, but you have a slightly extended version of that in which we have also to consider, separate these two cases in general, wherein both of them, neither of them applied the flip action, and another definition of another quantification of error, which would be in terms of those instances where both of them applied the flip action and then they had a D1 detection, and you have matching polarizations and reflect actions that are performed by Bob. So these are the E1 and E2. This is just to take into consideration the possibility that Bob and Alice might or might not apply the flip action, and one can conservatively again take the quantum bit error rate to be the maximum of E1 and E2. Next slide, please. Just to give an illustration of what happens how Eve's ability to counterattack this with the flip action will fail. Supposing Eve attacks, so on the onward leg she uses the U attack, and in the return leg her best bet is to either apply U inverse or apply U2, which is just U inverse but corresponding to the flipped version. And one might say that she might start by applying them with equal probability. So U2, for example, would basically be this, that you have the state 0x. So as far as the vacuum state is concerned, it behaves in the same way. Now the normal, so unitary, when it is inverted, so you would have had that it does not change in any way when the wrong polarization is encountered. But in this case, what happens is that when the flipped polarization is taken into consideration, then you have the probe being reset to epsilon 0, namely an attempt to disentangle Eve's probe from Alice and Bob's state. So this is the action that she would perform. Again, this is basically going to fail because when she applies U inverse in the case where both of them flip their polarization, she will fail to disentangle the particle. And in the cases where they both flipped, she might apply the attack U inverse, in which case again she will fail to entangle. So you will have these anomalous detections in D1, which will show up in the error E1 or the error E2 as we have defined it, and that would alert Alice and Bob to the presence of U. Next slide, please. So just to recapitulate, so E will generate no error if she applies U inverse in the case where neither of them apply a flip action, and if she attacks with U2 in the return leg in the case where both of them apply the flip action. It's not too hard to study this case, and what we find is that if Eve has attacked the fraction G of the photons in the onward leg, then the error, which is symmetric in both the cases, will turn out to be G by 1 plus G. So of course, if G is 0, namely she does not attack any fraction, then she introduces no error, whereas if G is 1, namely she attacks all of it, then she introduces the maximal error of half. And We can quantify Alice and Bob's information in terms of 1 minus HE in the usual way. So where E is the channel error as computed by Alice and Bob through public discussion. Next slide, please. So now we want to estimate what sort of an error happens that Eve encounters through her attack. So among the non-announced bits, that is from Eve's perspective, Alice, she has the following uncertainty, namely when Alice and Bob do not make a public announcement. You know, when they have a D1 detection, they make a public announcement, but when they don't make a public announcement, it is that a DB detection could have happened on Bob's side or a D2 detection could have happened on Alice's side. And this, it turns out, would be part of why Eve's uncertainty exists over the channel. So one can then show that if F is the fraction with which Alice and Bob, both of them apply the flip action, of course Alice and Bob will do it independently, then in the DB detections can be shown to happen on the fraction W of all M, so Gn by 4W potential qubits. So the potential qubits correspond to the occasions on which Eve obtains EH or EV. That is, her probe has been shifted out of the state epsilon 0, the default state or the initial state, into the state EH or EV. So Eve's bet is to assume that on these occasions there's been potentially a DB detection and potentially a key that is shared between Alice and Bob. But actually DB detections happen only on the fraction W of the time, and on the remaining times actually they could have had D2 detection, for example, but Eve does not know this because of the flip action. Because an error has happened, Eve falsely gets EH or EV because she has not been able to properly disentangle her photon or her probe from the state between Alice and Bob. So with this sort of an uncertainty, therefore, as far as Eve is concerned, her uncertainty could be quantified by looking at all possible key strings that she should allow Alice and Bob to be sharing, which is M, the number of potential key bits that you have, and W is the fraction of it that would actually be the genuine DB detections from which Alice and Bob have a key that is generated. And so we then estimate that if taking F to be the value half, which is optimal for Alice and Bob, we find that the log beta is given by this expression. So Eve's ignorance on the whole transaction would be this expression, that is 0.72 into 5gn by 16, which is, this expression is just log of beta, where beta is mcmw as explained. So her total ignorance would be this expression plus 1 minus g, which is the fraction that she has not attacked. We factor all of this by n by 4, which is the detections that you have on Bob's side. And so we find that her ignorance is quantified by this expression n by 4, 1 minus 0.1g. But the bottom line is that through this attack, Eve gains information which can be quantified as 0.1g under this particular attack, which is reasonably, which is kind of the best, which is a reasonable attack for her to launch in an incoherent way. So we're not talking about unconditional security, or we've not considered joint attacks or collective attacks. We just look at incoherent attacks where single photons are being attacked. So Eve's information then can be estimated in this way. And next slide, please. Therefore, key rate can again be estimated in a very simple way as the difference between these two mutual informations, which we find to be k epsilon. Here, the expression that we've given is we've assumed f, the flip fraction, to be half. We could, of course, have, and that is optimal, that turns out to be optimal for Alice and Bob. You could have other flip fractions also that could be considered. I'll have a plot that comes later on. Also, we can look at this whole thing in terms of visibility, namely that one can look at, because we have an interferometric setup, and we can look at the visibility that happens in the interferometer, and we again find corresponding to the error rate that we have calculated. So this will lead us to tell about what is the highest error rate under this attack that can be tolerated, right? Such that higher than that, Eve could potentially be having more information than Alice and Bob. The corresponding numbers for visibility can be shown to be, so the minimum visibility that they can have is 0.718, corresponding to the maximum tolerable error rate that this particular attack on this protocol would allow. Next slide, please. Yeah. So this would be a quick overview of the error rate. So the blue line that is here is the performance of this particular protocol. So it, I mean, based on this very simple-minded attack, we find that it remains secure for a considerable deal. One could, of course, have more powerful collective attacks, etc. But in order to compare it with the no protocol, so that is something that I've not included in the slides because of potential want of time. So you can consider a similar single photon attack also, or incoherent attack on the no protocol, but it would obviously be different because the key bits are generated in the no protocol counterfactually, whereas for us, key bits are generated non-counterfactually. So even a potential attack to be incoherent would be different, but we can consider a similar attack on the no protocol, and we find that not only is the efficiency of the no protocol, right, this is 1/8, it starts at 1/8, but that we know basically based on the protocol design, but also the error that can be tolerated in the no protocol and the current protocol, we find that the proposed protocol gives us an advantage, not only in terms of efficiency, but also in terms of its error tolerance. And so this intermediate expression is one where we allow the flip fraction to be 0.1. That is the probability with which Alice and Bob can flip their reflected, the instances where they just reflect a photon, they flip its polarization. So ideally you want it to be, the optimal one choice for them would be 0.5. But even with this choice, we find that in terms of the tolerable error rate, at least under the incoherent attacks that we have considered, the proposed protocol seems to outperform the original counterfactual key distribution protocol. Next slide, please. Here I will very briefly talk about the idea that this method we have said about obtaining the key from the non-counterfactual bits and using counterfactual statistics only for security, that can also be applied to other protocols. For example, the semi-counterfactual key distribution protocol that had been proposed earlier, in that the basis of key that is being shared between Alice and Bob is not the polarization. Instead, you could simply have a fixed polarization. We still have a Mach-Zehnder type of interferometer that is shared between these two. The difference instead is that Alice also can apply block or reflect operations, just like Bob was doing in the original no protocol. So the key is then shared again in the same way that if both of them apply the reflect action, you have a detection that happens only in the D1 detector. Whereas if of course, if both of them apply block actions, then the photon is absorbed in one of their stations. But only if one of them applies the block and the other applies the reflect actions will you have a D2 detection, which again happens with probability 1/8 as in the no protocol. And that will then give them a basis for sharing a key in terms of who performed the block and who performed the reflect action. That is to say, once D2 detection is signaled and Bob knows that he blocked, so he knows for sure that Alice should have reflected. So this forms the basis of the key in the semi-counterfactual protocol. Yeah, next slide, please. So this is just what this table summarizes what we were telling earlier, that if both of them have the reflect action, then you have a detection in D1. And if both of them perform block actions, then of course you don't have a detection in D1 or D2. So when you have a detection in D2, then we know that the actions of Alice and Bob were necessarily mismatched, and that forms the basis for the key. And here again, if we were to include the DA and DB detections for key generation, and again here it can be shown that Eve can launch a noiseless attack, and here again one can introduce these flip actions that would give protection against this noiseless attack that could be launched if we did not have those flip attacks and just had the non-counterfactual bits being counted. Next slide, please. Yeah, so this is again the same idea that if Eve were to have a probe that she entangles, so let's say she creates a state of this form. So you have a tripartite entangled state between the photon system of Alice and Bob and Eve's probe. And the first case here indicates that that neither of them perform the flip action, whereas in the second case, both of them flip, so they change the H to the orthogonal state, which is V. Again, in this case, we find that Eve cannot design a unitary that can take care of both these cases and disentangle her probe. So if she gets it right for the case where neither of them flip, then there's with a certain probability she fails to, she will introduce an error in the other case because she will not be able to disentangle her probe from the state of Alice and Bob and thereby reduce the coherence that they're able to measure. Next slide, please. Again, there's the protocol that was proposed by Guo and Shi, which is very similar to the semi-counterfactual protocol that we proposed earlier. Historically, actually, this predates even the no protocol, but in retrospect, it could be considered as analogous to the semi-counterfactual protocol, except that it uses a Mach-Zehnder configuration instead of a Michelson interferometer configuration. And pretty much very similar considerations that we mentioned earlier will apply here also, except for certain subtleties, namely that in the Guo-Shi protocol, technically both arms can be exposed to E. Whereas this might initially seem like a major good news for E, the fact is that these two arms can be quite well separated in space, thereby highly constraining the quickness with which, the speed with which she would have to have probes that interact with both arms in order to be able to, extract useful information. Next slide, please. Yeah, so the statistics again in the Guo-Shi protocol are similar as the semi-counterfactual protocol. Yeah, next slide, please. Yeah, finally, a quick mention to the cascaded no protocol, which is a very simple but clever extension of the no protocol. So in the no protocol, we find the efficiency to be 1/8. So here you have a cascade of beam splitters that effectively cut down exponentially the amplitude that reaches Bob. As a result, that if Bob performs a block action, you could have a detection in any one of these detectors. So the D1 detector that you have any one of these D1 detectors. Now, if he performs a block action, then you would have the detection deterministically coming at D0. But if he performs the block action, half the time you get detection here rather than here, because exponentially very little amplitude leaks out or reaches Bob. So his blocking action actually goes down from half, which was the case in the no protocol, to something that's exponentially small in this case. And therefore you have an improved efficiency, like the efficiency, next slide please, as we will show. So if a reflect action is performed by Bob, then 100% of the times you get a D0, let's say in the detector D0, whereas if he performs a block action almost 50% of the times, as n tends to infinity, you get a key that is generated. So from 1 by 8, you have, it gets increased to a fourfold increase to half. And now if the point I wanted to mention here is that our idea of using the, counting the non-counterfactual bits is not of any use, that particular idea that we use, because the block actions are anyway exponentially small, they go as half power n. So the non-counterfactual bits that you get would really not be very helpful in this particular protocol. Yeah, next slide, please. So to conclude, I just summarize some of the ideas that we presented. So that the non-counterfactual bits in the protocol, in a counterfactual cryptography protocol, can be used for key generation in order to increase the efficiency, while the security can still be guaranteed by counterfactual statistics. So the fact that you have counterfactual security, namely that the key bit is generated at a certain place, whereas the security is based on detections elsewhere produced by IFM. So that is what we mean by counterfactual security. And it is advantageous over BB84 in certain ways. The counterfactual Qkd protocols are orthogonal based, so state preparations are simpler than in BB84. And again, the check bits that we use are not, unlike in BB84, the check bits here are not drawn from the sifted bits, but instead from the data that is eliminated during the sifting process. A point that I have not included here is that we can also include some of the counterfactual bits as part of the key to further boost the efficiency. That is something that can certainly be done. And again, the idea that we proposed here can also be used to other counterfactual key distribution protocols. Next slide, please. Yeah, so I guess that concludes my talk. Thank you very much for your attention.
Thank you, Shrikant, for the nice talk. So, for questions, please feel free to ask questions. I have one query, Shrikant.
Sure.
What do you think will be, how drastically will things change if you include noise in this thing?
Yeah, that's of course the most important question in cryptography, namely how do things. So so in the particular attack that we have considered, we assume conservatively, as you know, that all of the noise that would appear is due to E. So for example, when we get error bounds that we make, we assume that it could very well be due to noise, but we will assume that it's due to E, and the error bounds that we get are due to it. So we do not, for example, specifically, yeah, you got it right. So that's what we do. So we'll basically assume that all the error that we have is due to E. Now, if you introduce a collective noise, then probably a full security model should involve security checks with collective attacks, joint attacks, which has not been done here.
Okay. Okay. Any other question? Okay. If not, then let us thank Shrikant once again. Thank you, Shrikant.
Thank you, Shubhashish. Thank you, everybody.
Thank you, sir, for sharing your work on security of quantum cryptography. With this, today's first session comes to an end. We will resume for another set of wonderful talks after the lunch break at 2 p.m. IST. Enjoy your lunch. Thank you.
Hello. Am I audible?
Yes, sir.
Yes, thank you. Actually, the share option is not working for me. I don't know why.
Just a minute, sir.
Thank you. It's now working. Yeah.
Now you can present the.
Thank you. Thank you. Let me just check whether my presentation. Can you see my screen?
Yes, sir.
Thank you.
Yeah, you can just. So I can mute, is it? When so मैं खुद को mute. हाँ, तो एक बार कोशिश करो. Let me just talk on the. Okay, yeah, I can mute myself, no? Since you have unmuted me, जब मैं चाहता हूँ मैं mute भी कर सकता हूँ, like when the person is talking.
Hello. Am I audible?
Yes, sir, you are audible.
Yeah, I was not able to hear Professor Sikand's voice, so that's why I was thinking that is there any connection problem?
No, actually, he's confirming about his voice and everything.
I can't hear it properly.
The session is not started yet.
Yeah. So I'll call you on WebEx. I'll talk to you on WebEx. Am I audible?
Hello.
Hello. Yeah.
Professor
Am I
Sikand,
audible?
I'm not able to hear you properly.
Oh. Yeah.
Maybe I leave and join then.
Yeah. Achha, I can hear you.
We can hear both of you properly.
You can hear me, madam?
Yes, sir, we can hear you properly.
Oh yeah, I can also hear you. So it's all fine. All's good. Yeah. So is that okay? So what's the issue?
I think there is some issue at Professor Chakraborty's end.
Oh, okay. Am I audible?
You're audible.
Am I audible?
Yes, sir.
Mute me myself.
So now I am audible?
Yeah. Oh, that's Indranil. Yeah, you're audible,
Yeah.
Indranil. This is Shrikant here.
Yeah. Now I can hear you properly. Was there some glitches because of the internet connection?
Okay. Oh, nice. Okay.
We start now then?
Sure. Okay. Shall I start now, madam?
Yes, sir. That's what I am asking.
Okay. So,
So
good
let's
afternoon,
now
everybody.
resume the. Okay, sir. Let's.
Please go ahead. Yeah, go ahead.
Okay, sir. Let's now resume the afternoon session of day 4. Dr. R. Shrikant will be chairing this session. I request Dr. Shrikant to step in.
Yeah, thank you, Dr. Jyoti. So, good afternoon, everybody. It's a very beautiful duty, a pleasurable duty has devolved on me of introducing the guests of this session, beginning with Dr. Indranil Chakrabarti, who will be talking to us about the interesting topic of quantum conditional entropy, a resource. So he is a quantum physicist and an associate professor at the IIIT uh, Hyderabad, before which he had been an adjunct professor at HRI Ahmedabad and an honorary visiting faculty at the Center for Theoretical Physics, Jamia Millia Islamia University. He received his PhD from the Bengal Engineering and Science University. He is the founding member of the Quantum Ecosystem Technology Council of India, a member of the Indian Physics Association. He works in the areas of quantum information theory, quantum foundations, quantum cryptography, quantum communication, and network. He is also interested in classical information theory. Over to you, Professor Indranil.
Thank you, Professor Shrikant, for such a nice and a generous introduction. Let me begin by thanking the organizers for giving me this opportunity and inviting me to present our work over here. In particular, to Professor Subhashish Banerjee. There is a long association with Professor Subhashish Banerjee over a decade, and it was very nice to give a talk in such an occasion, the conference organized by Professor Banerjee. And let me share my screen. Please let me know whether you are able to see my screen. Can you see my screen?
Yes.
Yeah,
yes, Dr. Indranil. Yeah.
Yeah. So as Professor Shrikant was mentioning, the title of my talk is Quantum Conditional Entropy, a Resource. So I will be talking about quantum conditional entropy in general. So couple of my slides initially would be of pedagogical in nature to introduce what is quantum conditional entropy. And as there are many experts of the field over here, for them it may be a pedagogical slides, but since there are students, I just kept 2-3 slides in a fashion to introduce the quantum conditional entropy. So this work is based on the 2 papers. One was published in this year, Physical Review A 2021, archive, which you can also get the archive reference over here, and another based on another work which had been published in the year 2017. So the whole presentation is based upon these 2 physical review papers on 2017 and 2021. So outline of my talk. So as I told you, initially I will be giving about a little bit of idea of what is information and how this transition in particular takes place from the classical to quantum, one way of understanding information, and then I will talk about classical entropy, classical conditional entropy, and then I will talk about the idea. I will give you the idea of quantum conditional fundamental entropy, conditional fundamental entropy. So then I will use a couple of slides to tell you about what are the different applications of the conditional fundamental entropy in the information processing task, and how these applications have actually motivated us to do this kind of work. So these applications lead us to the motivation to the fact that how we can characterize this particular state. And so here we call this conditional fundamental entropy non-negative. So conditional characterization of conditional fundamental entropy states which are of non-negative values, and the existence of the weakness for the negative value states. So we will also talk about how we create weakness operator to detect the states with negative conditional fundamental entropy, constructing a weakness for negative conditional entropy. So how do we find out the upper bound for the conditional entropy value with the help of the weaknesses? And finally, I will introduce the second part of the topic of my presentation, characterization and existence of ACVNN classes. So ACVNN classes is a kind of a class which are called absolute conditional fundamental non-negative entropies class. So we will introduce this class, and we will tell about what is the importance of this class in particular, and we will discuss this, and then we'll automatically tell about what is the characterization, how do we characterize this ACVNN class, and we'll talk about the existence of the weakness operators for these classes. And then as the last part of my talk, I will talk about how to connect all these absolute kind of classes, the absolutely separable classes, absolutely conditional fundamental entropy non-negative classes, and absolutely local classes. So this connection, connection of these different types of classes, I will talk about. And finally, I will conclude. So as I am telling you that it has always been intriguing to understand what is information in particular, and how information is connected to the reduction of uncertainty. As you can simply consider myself to be as a system A, and all the people who are actually listening to this talk as the system B. And whenever I am coming to give the talk, there is lots of uncertainty in each of our minds. And my uncertainty is that how the interaction will be, and how the talk is going to be. While the uncertainty in your mind will be that how I am going to deliver the talk. So all these uncertainties gets reduced once we start interacting and asking questions and each other. So this reduction of uncertainty can also be interpreted as only because there is a flow of information that is happening from the system A to the system B. So there are two systems, one is the system A and system B. Once they start interacting with each other, there is a constant flow of information between them. And this leads us to the reduction of uncertainty of the each of the system. So we generally in classical information theory, all of you know this, that we define the uncertainty or by the entropy, by the Shannon entropy, which is given by minus pi log pi. And you know what is the reason and why we have chosen this particular kind of definition, where pi is the probability distribution of the random variable x, which are taking the values x1, x2, xn, right? So and why we select this kind of definition to quantify information, and all of this falls into the foundational aspect of information theory, right? So there are many axioms associated with information theory, and we need to satisfy those axioms whenever we design a measure for the information amount of information present in the system. Now, when from classical to quantum, when we move on from classical to quantum, we are no longer dealing with the probability distributions, but instead we are dealing with the kind of mixed states or density matrices where to represent those mixed states. So we have ensemble of pure states psi I and their corresponding probabilities pi, right? So and that information content over here for S rho is minus of trace of rho log rho, right? So and this is given by the Shannon entropy gets replaced by the von Neumann entropy. So S of rho is minus trace of rho log rho. What does von Neumann entropy does? Von Neumann entropy measures the minimum classical uncertainty of a present in the a mixed quantum state. So operationally, it denotes the minimum number of qubits per symbol required to transmit information from a quantum source, which will be described by a density matrix rho, right? So now we move on to the conditional entropy. In case of classical, how do we define conditional entropy? So let me give you, before going into the quantum conditional entropy, let me give you an example to explain what is the idea of conditional entropy and how we try to quantify conditional entropy. Think about a very interesting situation where there are two friends A and B, and B ask his friend A that to come over for the dinner in the night, and A told that there is a possibility that I will come, but I am not sure about it. Right, so B has a certain amount of uncertainty in his mind whether his friend A will come over for the dinner in the night. So if we quantify this event of coming of A onto B's house as X, and the amount of uncertainty that whether this event will occur as HX, and then HX gives you the amount of uncertainty. Now what happens? A's car actually got broken down, and this has been observed by C, and C was coming towards B's house. So A tells C that there is more unlikely he will be able to come to B's house. So C, while meets B, he tells B that C, you are waiting for A, but A is not likely to come. Not likely to come, as I have seen that his car has got a broke. So he's repairing his car, right? So B is still unhappy, but what happens? The B's uncertainty whether A will come or not gets reduced. So there is a reduction in the uncertainty, and so this reduction in the uncertainty happens because of this event Y, which is the reporting of the person C to B. So this HX/Y is the new uncertainty of B, and which is obviously less than HX. Which is obviously less than HX in the sense that now because of this added information Y, this uncertainty gets reduced. So this is what is conditional entropy in a small sense, right? So the classical conditional entropy. But when we move from classical conditional entropy to the quantum conditional entropy, what we see? We see that this is given by S of rho AB minus S of rho B. So S of rho AB is the von Neumann entropy of the combined system AB, and S of rho B is the von Neumann entropy of the subsystem B. So this difference S A/B rho AB is given by this condition. Von Neumann entropy is condition entropy in the quantum scenario is given by this quantity. Now it is interesting. In the previous slide, while we are talking about the conditional entropy in the classical scenario, it is always seen that the classical conditional entropy is a positive quantity. Whereas in case of in a quantum scenario, when we are dealing with the density matrices, there can be conditional entropies which can be negative, and not all density matrices will have positive conditional entropies. So we denote this set as, so if ASH is the set of all density matrices, we denote this state FVH as a which is a subset of SH, the set of possessing non-negative conditional entropies. So CVNN. And so we call it in short as CVNN class, right? Now one quick example that conditional entropy can be negative in a quantum realm, quantum scenario, is if you take a Bell state. So if you take rho AB 1 by root 2 0 0 plus 1 1. So if you find out S of A slash B, then what is happening? So so by the definition, it will be S of rho AB minus S of B. So S of rho AB is what? S of rho AB is a pure state. So the S of rho AB will come out to be 0. Where S of minus S of B will be a completely mixed state. If you trace out any one of the qubit of the Bell state, it will come out to be completely mixed state. So it will be 1. So 0 minus 1 will give you minus 1. So here you can clearly see an example where the conditional where the quantum conditional entropy is negative. So there are 3 situations over here. Number 1 situation, when the quantum conditional entropy is positive. Number 2 situation, when the conditional entropy can be 0. And the number 3 situation, when the conditional entropy is negative. Now, those states for which quantum conditional entropy is a negative, they are actually a resource. So we will try to emphasize on this fact first with the help of an example that they are actually is a resource, and this will motivate our work to detect such states operation in a lab, how to detect such states in a lab with the help of an witness operator. So negativity here, there is a crucial point one should remember. So this particular state is an entangled state. And we see that for an entangled state of this type, the conditional entropy is coming out to be negative. So is there a connection between the entanglement and the conditional entropy? And if they are same, then what is the point of looking into quantum conditional entropy? I can always detect entanglement with the help of witness operator. But the situation is not the same. The negativity of conditional entropy definitely indicates the signature of entanglement. Although the converse is not true. There are entangled states with non-negative conditional entropies. So just by merely detecting whether the state is entangled will not enable you to tell that the state will have a negative conditional entropy, right? So there are certain specific tasks. We will see that in the coming slides, when the negative conditional entropy states are useful. There are certain specific tasks, and for that reason, we need to detect states with negative conditional entropy. Okay, now a couple of applications which will actually motivate us to detect such states. So applications number 1, I will call, is the state merging. This is an in this, what is happening in case of state merging? Consider 2 parties, Alice and Bob. Where Bob is having some prior information B, and Alice has some missing information A. Okay, Alice has some missing information A. Now, Bob wants to learn about A. Now we ask this question: Bob has some prior information B, and Alice has some missing information A. Bob wants to learn about this missing information. So how much information Alice needs to send Bob so that Bob learns about this missing information, right? So it turns out that if Alice and Bob is sharing a state rho AB, thus conditional von Neumann entropy S of A slash B will suffice in this case. So the amount of missing info, to know the missing information that is present in Alice, that is withheld by Alice, given that his information is B, how much extra number of bits Alice needs to transfer to Bob so that Bob knows about this missing information. And it turns out that this is given by the conditional von Neumann entropy. Now, so there are three, as I told you, conditional von Neumann entropy has can be three possibilities: greater than 0, 0, or less than 0. So for each of these three possibilities, there will be a certain meaning associated in context of the state merging. So let us consider the first possibility: when S of AB is greater than 0. Then in that case, the sender needs to communicate that amount of qubits to the receiver. When Alice and Bob is sharing a state rho AB, and it turns out that S of A slash B is greater than 0 for that particular state rho AB, that means the Alice needs to send this amount of bits to the receiver Bob, so that Bob gets about to know about the missing information A. Now, if SAB is equal to 0, that means Alice do not need to do any kind of communication. Bob is completely aware of Alice's system. But the interesting part, so this state merging was introduced by Winter in his very famous Nature paper, where he talks about these three parts, where he and his collaborators talks about these three particular situations. So the third situation is whenever S of A slash B is less than 0. The sender whenever S of A slash B is less than 0, this means that Bob already has the information about A. But not only that, there is some amount of the sender and the receiver gain some amount of potential for future communication. So if your conditional von Neumann entropy comes out to be negative, then this state rho AB shared between the sender and the receiver can be used for potential future communication, right? So one of the important application was state merging. The second important application in this context is the superdense coding. And most of you know from the very basics of the quantum information theory what is superdense coding. In the superdense coding is a kind of a process where we transfer classical information from one place to another, and we are taking the help of a quantum entanglement or a quantum resource or entangled state. Now, in general, when we consider Bell state, we start with we consider a Bell state. We know that we can send 2 bits of classical information, but in general, the capacity of a state rho AB mixed state in general shared by Alice and Bob to send classical information from one side to the another is given by this quantity CAP, which is maximum of log2d plus S of rho B minus S of rho AB. Now see, if you are having a 2-qubit system and a Bell state, log2, so what is this? Maximum of log2d, d is equal to 2, this is 1, and here this is 1, plus if you are having a Bell state, so S of rho B will be 1, and minus S of rho AB, since it is a pure state, it will be 0. So this is 1, 2, so you will get 2. So as you know, in case of Bell state, that you will get 2, you can send 2 bits of classical information. So this will come out to be 2. Now, interesting part is this. So the second expression inside the bracket will be more than the first expression, which is the classical limit, only when this quantity is positive. That means S of rho B minus S of rho AB is a greater than 0 quantity, So so they say in this way that whenever this quantity is positive, we are gaining a quantum advantage over the classical protocol. So this is referred as a quantum advantage. So we definitely try to look out for those kind of entangled states or those kind of states in particular for which this quantity will come out to be positive. But what is this quantity? This quantity is nothing but the negative of the conditional entropy, right? So this quantity is nothing but the negative of the conditional entropy. So and this will be given by minus of A slash B, right? So that means whenever S of A slash B is negative, this quantity becomes positive, and then we gain a advantage of the quantum advantage in the process of superdense coding. So again, we see that negative conditional entropy acts as a resource for the task like superdense coding. And third example in this scenario is the example of a coherent information. Suppose you consider a channel with a quantum system A and a reference system and both of the P, and now both of them are in entangled state. Hello, is there any question? Hello. So we start with a quantum system A and a reference system, and they are in a combined pure entangled state. Now, if you see that if your unknown quantum state A, if your state A goes to an unknown quantum channel N, through which the state rho A is transmitted, when P, while this reference system P remains isolated. So A is undergoing a channel. So after undergoing the channel, the resultant density matrix will be rho PB.
Yeah, let's go.
Hi, I'm Joe. Hello,
So in my last video, I made some data that I wasn't very happy with, and I was making a lot of mistakes. I don't know, I've just been feeling all over the place. So
Ashish, can you please mute yourself?
At first, I thought they were waiting to see Holly's friend.
The combined output states rho AB will be given by this IP cross NA psi PA. So the NA is the channel which is acting on the system A, and there is nothing happening to the reference system. Now the lower bound, the capacity of this channel is given by the quantum coherent information, which is the lower bound for this capacity of this channel, and this is given by this conditional S of rho B minus S of rho PB. So that means this is again the conditional entropy of the output state, negative of the conditional entropy of the output state. Now, if this comes out to be negative, this the coherent information comes out to be positive. So the channel, in that case, the channel is useful for transferring the information, transferring the quantum information through the channel. So again, we see that a negative conditional entropy is playing a pivotal role in understanding and isolating the system which are useful as a resource, right? And the fourth application, I will tell a little bit about this fourth application. So consider two parties. So this is associated with quantum memory. So consider two parties, Alice and Bob, which are agree on two measurements, say X and Y. And Bob prepares some state and sends it to Alice, who actually in measuring this observable X and Y and reveals a measurement choice. Now, what is Bob then trying to do? Bob then is trying to guess her outcome to prepare the initial states. But he finds that this there is an entropic uncertainty relations for these two measurements outcomes X and Y on a incompatible measurement that are performed on a quantum states, and these are given by this amount of uncertainty of guessing the outcome is given by this entropic uncertainty relation Hx plus Hy greater than log 2 1 by C. But C is nothing but maximum of modulus of the inner product of Xi and Yj square, where Xi and Yj are nothing but the eigenvectors of these two observables X and Y. Now what happens now if suppose Bob access to some quantum memory, some other system, and he can prepare a state that is maximally entangled with the memory and send it to Alice, right? And the memory part is the B part. So send it to Alice. Then apply the same measurement that Alice picks up on his own memory and can guess, and same measurement that Alice picks on his own and guess with full certainty. So now the new uncertainty relation between the entropic uncertainty relations about these two measurement outcomes X and Y is conditioned by the event B, which is the memory that is which Bob is having access to. Now, this entropic uncertainty relation will be h of a x slash b, h of a y slash b is greater than log to 1 by c plus this quantity. Now see, this uncertainty relation initially which was there is now getting changed to this quantity. So s of a slash b rho ab. Now what is rho ab is nothing but the combined state of Bob's memory and the subsystem that he is sending to Alice, right? A subsystem. Now here we notice that whenever this quantity is negative, whenever this quantity is negative, the Bob's prepared state now beats the original uncertainty bound and witness the original uncertainty bound. So there can be three different situations. In a particular situation, when the conditional entropies are entropies are positive, there is no gain.
What's up, okay.
When the conditional entropies are positive, there is no gain. But when the conditional entropies are negative, but yet but it is less than is negative, but it is less than log to 1 by c, then there is a significant advantage. But whenever this s of a slash b rho ab becomes less than equal to log 2c, then the uncertainty bound becomes trivial. That is ha x slash b plus ha y slash b will be greater than 0. So with all these four examples, we have seen the applications of the conditional von Neumann entropy in the quantum scenario, but there are many more applications. So we are not going into those applications. Now first, so what motivates our work? The first thing that you are motivating over here is that think of a situation while we are actually looking out for resource which will help in realizing to execute tasks like quantum dense coding. So now the question will be, is that entangled state will be sufficient? So the answer to this question will be no, as there will be twists, because there are entangled states. We need only entangled states with negative conditional entropy, as there are entangled states with positive conditional entropy. So what we did in this work, in the first work, is to develop a method, construct operators which can witness negative conditional entropy in entangled states belonging to arbitrary dimensions. So so that means in witness is a kind of an operator that the expectation value of the operator will possess negative conditional with the entangled state will possess a negative conditional entropy. The second part of the work is that we try to see the states which are having non-negative conditional entropies, right? So in this work, negative conditional entropy. But see, once we are looking into the states which are having non-negative conditional entropy, is this the end of the story, or do we need or there is a twist over here? Because there are certain states which are right now non-negative conditional entropy, but then can be made useful. They can be made negative conditional entropy after the application of global unitary operators. However, there will be some states which is sitting in the code. Even after the application of the global unitary operator, we cannot turn them into a negative conditional entropy states. So, and then that particular class of states which is sitting in the code and which are resilient to the attack of the global unitary operators and remains and whose conditional von Neumann entropy remains positive even after the application of the global unitary operator are known as the ACVN class, or the absolute conditional von Neumann entropy class. So we try to characterize those class and also find out the detection procedure for such experimental detection procedure for such class of states. Because while we are identifying those class of states, ACVN class of states, we are actually able to identify those states which can be made useful in the later period after the application of the global unitary operator. So I will come to the absolute von Neumann entropy class later. But first, FVH is the set of all conditional von Neumann entropy positive class, right? So FVH, this particular class, is the set of all states which are having conditional von Neumann entropy positive. Now, from Hahn-Banach's theorem, if I can show that this class, the set of all states which are having positive conditional von Neumann entropy greater than is as a convex and compact. So if from Hahn-Banach's theorem we are able to show that this class is convex and compact, then I will be always able to create a hyperplane which will separate out a state with a negative conditional entropy from this class. So for the given state with a negative conditional entropy, we'll able to create an hyperplane, and this hyperplane is separating out this negative conditional entropy state from the class which are having the set of state having positive conditional entropies. So if this class is convex and compact, then there is always possible to draw a hyperplane to separate it out from the other class. Now, the interesting question, so this hyperplane is nothing but actually the witness operator, which we can create in the laboratory in terms of the Pauli operators, expressing that witness operator in terms of the Pauli operators. So, but to prove this is, so whenever we talk about the witness theory, we need to first show that whether the witness exists or not. So whether the set is convex or compact or not. Whether the other class is convex or compact. Once we know this set is convex and compact, then we can ensure that there can exist a witness which will separate out that set from the rest of the others, right? Otherwise, we'll never be able to do that. So to prove this set is a convex and compact, let's take two examples, very simple examples, sigma 1 and sigma 2 from this class, right? So S of sigma, because if they belong to the class of positive conditional entropies, then S of A slash B sigma 1 and S of A slash B sigma 2 will be greater than equal to 0, right? So as sigma 1, sigma 2 are belonging to this class of positive conditional entropies. Now we take a convex combination of this sigma. Sigma is lambda sigma 1 plus 1 minus lambda sigma 2. Now if we are say that sigma also belong to this class, if we are able to show this, then we can say that this class is actually a convex set. So if you take a set sigma, lambda sigma 1, 1 minus lambda sigma 2, while lambda belongs to 0, 1. Now from the concavity of the conditional entropy, we can always write down sigma to be as greater than lambda S of AB sigma 1 plus 1 minus lambda S of AB sigma 2. Now each of S of AB sigma 1 and sigma 2, S of AB sigma 2 is greater than equal to 0. So whole expression S of AB sigma is also greater than equal to 0. That tells you this state sigma is also belonging to this class FBH. So we start with two states sigma and sigma 2, and we take a convex combination of these two states, and we see that that convex combination is also belonging to this state. So this set is FBH is convex. Now the interesting part is the compact part. So what is to show that compact, we take an SAB, we have to show that this set FBH is closed and bounded, right? So to show that the set is closed and bounded, what we do, so the so all the states that are belonging to this class is having the conditional entropy is greater than equal to 0. So the minimum value 0 is attained for all the the several states in this class. Not all, but for example, all pure separable state will give you this conditional entropy equal to 0. Now, from the sub-additivity of the S of AB, we can always say that S of sigma AB is less than equal to S of sigma A plus S of sigma B. Now, if you take down S of sigma B on the left hand side, you will get S of A slash B sigma AB, which happens to be less than S of sigma A. And S of sigma A for a d-dimensional system, we know that will be less than the log to d value. So this is the maximum value of the entropy that it can attain. So this value is attained at I by d square. Right, for whenever you have a state like this, sigma A of the form like this, the conditional entropy will be log to d. So all the conditional entropies is bounded by log to d. So what we see, if you take this to be as a function, S of A slash B, this conditional entropy as a function, and if you take this to be your domain set, FBH to be your domain set, where sigma is coming from, sigma AB is coming from, this function is mapping all the elements of this domain set to a closed set, which is 0 log 2d, right? And we know that this function from this winter paper, you will see this function is a continuous function, and their image set of this particular function is closed. Now, if the image set and the particular function is a closed set, and the particular function is continuous function, we can say that FBH is FBH is also continuous. The P image set is also closed. Sorry, not continuous, is also closed. So the set FBH that from where sigma AB is coming is also closed. This is a very important results of the functional analysis. So FBH is closed. Now, since every density matrix has a bounded spectrum, so FBH, we can easily say that FBH is also bounded. Now, so we actually do not need to prove for bounded. If we are able to show that this is closed and closed, then we can say that FBH is compact. So now we see that since both this FBH is convex and compact, there exists a witness operator which will able to detect with a negative conditional von Neumann entry states. For example, if the Hermitian operator W is a witness and witness for a state possessing negative conditional entropy, that means there exists a state rho which is not belonging to this class of positive conditional entropy. And if you take trace of W rho, this will come out to be negative. But however, if you take sigma from the set of all positive conditional entropy class, there will be trace of W sigma will be greater than equal to 0. This will come out to be negative. One such example of a witness is this witness, W rho minus log of rho AB plus I cross log rho AB. So if rho AB does not belong to FBH, then W of rho is a witness for such state. So whenever you take trace of W rho with rho AB, you will see that this will be less than 0. But if you take any arbitrary state sigma from the class FBH class, where the set of all positive conditional entropies, then trace of W sigma will be greater than equal to 0. And this is very closely related to the conditional amplitude operator, which was first introduced by Nicholas, this in this paper by Nicholas Firis, right? So, Professor Sikant, how much time I have left?
You've got about 10 minutes, Dr. Indrajit.
Okay, thank you. So in that case, I'm just quickly going through this proof, and then I will try to move on to the other part. So if you, as I told you, if you take trace of W rho AB, if you take the trace of W rho with rho AB, you will see that it is nothing but it will coming out of S of A slash B rho AB. Since rho AB is a negative conditional entropy state already, so it will be less than 0. But however, that is not sufficient to tell that W rho is a witness. But you have to show that for all such states sigma which is belonging to this group FBH, trace of W rho is greater than 0. So for all sigma AB belonging to F of this particular class, S of W rho will be greater than equal to 0. So S of sigma B rho B is less than equal to, from the monotonicity of the relative entropy, we can always write S of sigma B rho B, relative entropy of rho B is less than equal to S of sigma AB with the relative entropy of rho AB. Now, if you break down the relative entropies on both the sides, this left-hand side becomes trace of rho B log sigma B minus trace of sigma B log rho B. And similarly, the right-hand side becomes trace of sigma AB log sigma AB minus trace of sigma A log rho B. Now, if you rearrange these terms, the left-hand side, we take this, and the right-hand side becomes S of A B slash sigma AB. Now, sigma AB has been taken from FBH, so the conditional von Neumann entropy of sigma AB will be greater than equal to 0. So this particular left-hand side will always be greater than equal to 0. But what is this left hand side? This left hand side is nothing but trace of W rho and sigma AB. So this is your W rho. If you take trace of W rho with sigma AB, this is the left hand side that you are going to get. So you see that you take an arbitrary sigma from sigma AB from FBH, and we are finding out that this W rho with all such sigma AB will be greater than 0. So W rho is actually satisfying both these conditions. Like for a negative conditional entropy state, it is giving you a less than 0, and for arbitrary positive conditional entropy states, it will give you positive trace value. So, and we can safely say that W is a witness operator. One such quick example of W witness will be like this. Let us consider this Warner state, which is of this form 0.995 plus 5 plus 0.01 I by 4. So this is a witness corresponding to the state. This is corresponding to the state. So if W is the witness corresponding to the state rho, then corresponding W gamma is the witness corresponding to the state gamma. And this is given by minus log of gamma m, where gamma is this I cross log gamma b. After tracing out a, this will be gamma b. Now W gamma is given by this, when expressed in the computational basis, it is given by this, right? Where A, B, C, D are the values. Now if you take trace of W gamma, you will see that this is minus 9.244. That means it is detecting this negative conditional entropy state gamma. Not only it is detecting the negative conditional entropy state gamma from which it has been created, but it is also detecting another negative conditional entropy state delta, where delta is of the form like this. And so it is not necessary a particular witness will detect one particular state. It can detect many states. But it is also it is not also true that if there can be a state which cannot get detected by a particular witness. But I will say this is a witness only when there is at least one state which is getting detected by the witness, and all other states, for example, the positive conditional fundamental entropy states, it is giving greater than equal to 0. The trace value is giving greater than equal to 0. So we can always decompose this witness in the lab in form of the polymatrices or in the horizontal or vertical polarization basis, and then you can implement these measurements, to detect the states with negative conditional entropy. So I am not going into the upper bound of the conditional entropy. Rather than I'm going into the second part of my talk because there is less time. So I want to talk about this paper, which was published in year 2017, which is called the absolute class of von Neumann entropy non-negative states. So as I told you, absolute class of states, absolute class is a class of states which are very much resilient to this attack of the global unitary operators. That means, for example, this is not only common to the conditional von Neumann entropy or non-negative feature, but it is also common in case of separable. Much before this concept of ACVN came, the absolute separability, absolute locality, Bell-CHH locality is an important concept that people had worked on. For example, there are certain separable states where if you apply the global unitary operators, it will remain separable in spite of your application of the global unitary operators. And some separable states will be such which will lie in the fringe, and they will become entanglement after the application of the global unitary operator. Now the question is, this set is not just I by D or identity matrix. This is a finite amount of sets, right? And this set will these sets are very much resilient to the global unitary operator. So, and this class of state is known as absolute class of states. Just like in case of separable and absolute local, there are other absolute classes of states. We have introduced a new class of state, which is called absolute conditional von Neumann entropy non-negative state. So these states will remain, whose conditional von Neumann entropy will remain non-negative even after the application of the global unitary operator. And this is how we define these states. So all those sigma AC such that sigma AC S of U sigma AC U dagger minus S of U sigma AC U dagger, and then the trace is taken over the subsystem A, then it will be greater than equal to 0 for all U. Means whatever view the applications of the U, this this state is not going to change its positive property of the conditional von Neumann entropy even after the application of the global unitary operator. So what are those class of states? So that we find out a necessary sufficient condition for this class of states. So all those states, all those two bipartite states in 2-qubit systems whose von Neumann entropy is greater than 1. For example, here we are considering 2-qubit systems, right? Greater than 1 will belong to this class. It's very easy to see this proof. Suppose sigma AC belongs to this ACVNN class. That means S of U sigma is greater than 0 as per the definition. Now, what is this first quantity? The first quantity is we are applying global unitary on sigma AC. It will not change the entropy. Because of the similarity theorem, the eigenvalues will remain invariant. So S of U sigma AC U dagger will be nothing but S of sigma AC. But this is going to change. S of U sigma AC U dagger, then you are taking the partial transpose. So we keep it as it is. Will be greater than 0. We can write this. So you can say that we have for the states whose conditional von Neumann entropy is positive, absolute conditional von Neumann entropy states which remains positive after the application of global unitary operator, those states for which this inequality holds, right? Now, what is this maximum value of S of U of this reduced subsystem? So this reduced subsystem, the maximum value it can be obtained whenever it is a Bell state, right? Whenever whenever sigma AC is a Bell state. That means the sigma AC, the subsystem, after tracing out A, you will get I by 2. After tracing out A, you will be given I by 2, and the maximum value will be 1. And we know that there always exists an unitary operator that will convert sigma AC to a Bell diagonal state. So sigma Bell for a given spectrum. So so if S of sigma AC is greater than this for all U, then it is also greater than S of sigma Bell, which is for a particular U, which is happening for a particular U, and sigma, and which is nothing but I by 2. And what is the value in case of 2-qubit system of the mixed state? S of I by 2 is 1. So it is a necessary condition. So if your state is if your state belongs to this class, then it has to be sigma AC greater than equal to 1. Now, if sigma AC is greater than equal to 1, then always the conditional von Neumann entropy, always the absolute conditional von Neumann entropy will be greater than equal to 0. So why? So for example, if sigma AC is greater than 1, whose von Neumann entropy is greater than so the reason is following. So all the states which is having the von Neumann entropy greater than equal to 1, we know that this state cannot have negative conditional entropy, because the sigma, this left part, the maximum, if this part is always greater than equal to 1, this part is always the maximum value this part can attain. The maximum value this part can attain is 1, and right. And if this part is always greater than equal to 1, then this is always positive. So whenever sigma AC is greater than equal to 1, this quantity comes out to be positive. That means the state's sigma AC is actually belonging to ACVNN class. So Professor Sikant, how much time I have left?
Yeah, maybe 5 minutes.
Okay, thank you. So we can, just by the similar argument, we can always also show that this particular class ACVNN is convex and compact, right? You can take two states, sigma 1, sigma 2 from ACVNN, and you take the convex combination of this state, and you know that for sigma 1, sigma 2 belonging to ACVNN, this will be greater than equal to 1. So S of lambda sigma 1 plus 1 of lambda sigma 2, by again using the concavity of von Neumann entropy, you can easily show that it is greater than equal to 1. And similarly, you can also show that this particular set is a compact set. For example, if you take this function, so S of rho is a function. So then as a function f, right? So for ACVNN, we know that S of sigma rho will be always greater than equal to 1. The maximum value of the sigma AC can attain is the 2. So all the image set is a closed set 1 and 1 comma 2, right? The image set is a closed set 1 comma 2, and this function S is a continuous function. So therefore, the pre-image set, that is f inverse of 1 by 2, is a closed set. Since this function f is a continuous, or the S function S is a continuous function, and the image set is a closed set, this pre-image set is also a closed set. That means this set is closed. And similarly, we can, since every density matrix has a bounded spectrum, then the eigenvalues lies between 0 and 1. The set is also closed and bounded, and hence this set is compact. So ACVNN class, this class is this is a convex and compact set. Now that means any state that does not belong to ACVNN class can be identified by this hyperplane from the Hahn-Banach theorem. So now this particular state, what is the need for identifying this particular state? Because this particular state is maybe one of such state which is right now having a conditional von Neumann entropy non-negative, but can be made useful to a resource by making application of the global unitary operators, and can be made useful as a can be converted to a state with a negative conditional entropy. So we can actually, with the help of this kind of regularity, we can actually identify states which are not yet useful, but at least they can be useful after the application of the global unitary operators. So identifying the useful as a resource. So identifying this hidden resource, these characteristics, is also very important in this context. Here also we try to do a maximization, minimization to find out the class of the ACVNN class, and we take the distance of rho from the I by 4. Here is the I by 4, and if rho does not belongs to ACVNN class, then we numerically minimize this to see that this bound is 0.570225, and similarly we take sigma from ACVNN class and maximize this. So in that way we try to get an idea of the two different radiuses which will try to give you the estimate of the ACVNN classes. Now these are couple, so I am coming into the end part of my talk. These are the couple of examples, the examples where I can give you this, but for example, this particular state. So look, this is in a CVNN class. So its conditional von Neumann entropy is 0. It is non-negative, right? It is 0. But after the application of the unitary operator, this state rho AB turns out to rho AB1, and then the conditional entropy of the new state becomes minus 0.1887. That means the state is not useful right at this moment, but can be made useful after the application of the global unitary operator. Now, our process tries to identify experimentally those kinds of states with the help of weakness operator. Now, a classic example of a state which is very resilient or ACVNN class. So sigma 1 for example, if you take the 1 state, so where psi is a Bell state, sigma 1 will give you ACVNN when S rho is greater than 1. That means it will turn out to solve this inequality, and this inequality will give whenever P lies between 0 to 0.746, all these states are ACVNN class. That means these are resilient to the attack of the quantum condition, attack of the global unitary operator. So this is the class. So we can show easily that absolutely separable state is a part of ACVNN, and then also we can show that we can say for Warner state absolute local is a part of ACVNN. But I am not going into this because I am already a little late. So let us, if you have any questions on that, I will be happy to answer on that. But let us come to the conclusion. So what are the takeaways from this? So, one is that we are able to characterize the states which are absolutely conditional von Neumann entropy non-negative. And in the process of characterization of that states, we are able to identify those states which are having negative, which are now having non-negative conditional entropy, but can be made useful by the application of global unitary operator, useful in the sense that they can be converted to a states into negative conditional entropy after the application of the global unitary operator. So and then finally we also try to create the witness for such states. And we not only that, we also talked about how to create a witness, how to create that witness for the conditional not even talking about the absolute conditional fundamental entropy, only for the conditional fundamental entropy negative class states. And this particular witness will be able to detect states with negative conditional fundamental entropy. Here in this presentation we showed in a construction of an algebraic witness. In the paper you will also see a construction of a geometric witness and many more applications in context to this. So I didn't, since there are two concepts, I didn't go into those things. So we also, these are some few references which are useful for our work. And finally, I would like to thank my collaborators who have been working with me, Professor Arun, on these two projects, Professor Arun Kumar Pati from HRI Prayagraj, Nirman Ganguly from BRICS Hyderabad, and my student Shubhasri Patru, who is now doing her PhD in CWI Amsterdam, and Mahati, who is now working with me as a master student. So thank you. Thank you.
Thank you very much, Professor Indranil. So now the stage is open for questions.
Hi, Indranil.
Yes.
Himadri here. Yeah, so I had a question. So thank you very much for the nice talk. I just wanted to know how easy or difficult do you think it is to come up with a kind of a resource theory formulation here?
Yeah, this is a very good question. In fact, we have actually come up with a resource theory of the conditional fundamental entropy, and we will be soon uploading our paper on the conditional fundamental entropy resource theory. But it is not in case of resource theory, we are not even yet able to characterize all the free operations which will keep the non-negative condition fundamental entropy non-negative. But at least we are able to figure out several class of free operations which will help you to keep the non-negative conditional entropy non-negative. So yeah, it is difficult because the question is not fully answered, but there are certain definitely a very partial result, important partial results that we got. Yeah, because we are actually working on this, because the whole motivation was to start with the resource theory of conditional fundamental entropy, and so this and then we found out that the idea of the detection is not yet even done. So we first went with the detection part. Then we are working on the resource theory part. But yes, that is an important question.
Okay. Yeah. Thanks.
Any other questions? Okay. So if there are no other questions, maybe I have two small questions to ask Professor Indranil. Thank you again for the wonderful talk. So you had mentioned this point that not all entangled states need to be C-wind, right? Like they need not have negative, conditional entropy. So
Right.
I wanted to ask you whether steerable states, can we make the statement that steerable states will necessarily have negative conditional entropy? Can such a statement be made?
Yeah, that part is a good question, but I have not looked into this idea with the steerable states, right? But I have just checked with the absolutely local. Bell CH is local. So
okay.
But my feeling is that out of absolutely separable, absolutely locality in terms of Bell CHs, locality in terms of Bell CHs,
right,
and absolutely conditional fundamental entropy, though there is not a concrete proof, but I think ACVNN is the largest class.
Okay. Okay. Also, this other point, that interesting point you had made about the situations in which negative conditional entropy states can be used as resource. You had also mentioned about relaxing the uncertainty principle, right? So on the right hand side you get. So does it mean that when you have negative conditional entropy states, it could also be used to indicate positive secrecy rate, like in a key distribution like situation?
Right. Because actually this negative, the using of the quantum memory and the entropic uncertainty relation, that is a corollary to this paper. In that particular paper, they actually use this thing, negative condition, to for the key distribution, key distillation part.
Oh, okay. Yeah,
so the whole application was on that context. So they use this quantum memory.
Sure. Yeah. Oh, thank you so much. Yeah, absolutely. So if there are no further questions, we conclude this particular talk by thanking Professor Indranil once again for this wonderful talk and informative talk. Thank you so much, Professor Indranil.
Thank you.
So maybe now move on to the next talk, organizer.
Hello?
Am I audible? I think the audio seems to be down. Am I audible?
Yes,
sir, you're audible.
Okay, so we can have the
Yes,
next
sir,
session. I guess we are already running short of, slightly
Yes,
we are
sir.
behind schedule. So we start the next talk with Professor Alok Pan. And it's again a pleasure to introduce an old friend who would be talking about generalized.
Hi, Sikant.
Hi, Alok. Hi.
Am I audible?
Yeah, you're audible.
Okay, I'm good.
You're good to go, Alok?
Yeah, sure.
Okay. So Professor Alok will be talking on the generalized n-locality inequalities and their optimal quantum violation. He is an assistant professor at NIT Patna. He received his PhD degree from Bose Institute, Kolkata. He completed his postdocs at the Pusan National University, South Korea, and then at CNRS 8089, Paris, France. He also received the prestigious JSPS fellowship to pursue postdoc at the Nagoya University, Japan. His research interests lie in quantum foundations, quantum information and cryptography, and quantum metrology. Over to you, Professor Pan.
Yeah, thank you, Sikant, for this nice introduction. May I share my screen?
Yeah, please do.
Hello. Yeah. Is it okay, right? Is it okay?
Yeah, now it's fine.
Should I continue?
Yeah, very much. Yeah.
Okay. So let me start by thanking our Subhasis for inviting me for giving this talk here. And I can remember that in the last 2 years back, we met there at IIT Jodhpur. And we expect that maybe next year onwards, we can meet there at IIT Jodhpur again. So the title of my talk is the generalized n-locality inequalities in quantum network and their quantum violation. So this work is done with my collaborator and students, Sneha Munshi and Rahul Kumar. And this paper is recently published in Physical Review month. So here is the outline of my talk, and I shall briefly explain the Bell CHSH scenario. And I think I can stop my video. That's okay. Okay, no problem. Well, I shall briefly describe the Bell CHSS scenario, the standard non-local scenarios, and that will be helpful to understand the main purpose of this work is that bilocality scenario in network. This is the simplest non-trivial network. And then I shall extend it to the when we have the n locality scenario. That means there are n different parties, and I shall be considering a particular kind of network scenario, which is the star network. And then finally, I shall conclude and I'll provide some open problems and outlook. So let's start with the Bell CHSS scenario. Yeah. So this is a very common and very well-known scenario is that there is two parties, Alice and Bob, and they are receiving the inputs, that is X and Y. For the for the CHSS scenario, we used to consider that there are two inputs for the Alice and two inputs for the Bob, and they're producing the outcomes that are also dichotomic. That's a 0, 1. And the important thing is that there is a source S that emits a shared randomness. That means there is a lambda variable which is used to call the hidden variable in our quantum foundations. That there are hidden variables that is being shared by the Alice and Bob. And what hidden variable provides, that provides the reality, that's the predetermined values before the measurements. And the most important thing, or important quantity we are interested here in the Bell CHSS scenario is the joint probability distributions of the outcomes of the two outcomes of Alice and Bob. So this is the PABXY. And then that can be written in this particular form, which is actually very known as called the factorized conditions. What the factorizability means is that actually factorizability is actually, when local realism holds, we have that this factorizability conditions also holds. Let me explain a little bit. There are many students, I suppose, that you can see that this PABXY can be written in terms of the PAX lambda. That actually means is that the Alice's outcome is independent of the Bob's outcome or Bob's measurement settings. And similarly, the Bob's outcome is independent of the Alice's outcome and the settings, but only dependent on the lambda. Outcomes are only dependent on the lambda. And this is actually called the locality assumptions. And lambda provides the reality conditions. So altogether, it's a local realism conditions, local realism assumption that is actually tested by the Bell CHSS scenario. So this is the very famous factorizability conditions that PABXY can be written as a factorized form of the independent probabilities of Alice and independent probabilities of the Bobs of their outcomes. It is well known that if that factorizability condition holds, then also we can formulate an inequality which is very well known CHSH inequality whose bound is restricted to 2. And here A1 and A2 are corresponding to the observables of Alice corresponding to the outcome, corresponding to the inputs C receives. That is the 1. If the input is 1, the observable is A1. If the input is 2, then the observable is A2. And similarly for the Bob. As we know that in quantum theory, we get this beta 2 values is actually restricted by the 2√2 values. It's upper bounded by 2√2. And the optimal value is definitely 2√2, and that is available only when the Alice's observables choices are mutually anti-commuting, Bob's observable choices are also mutually anti-commuting, and psi should be the maximally entangled state. Of course, I have not mentioned about the dimension of the Hilbert space, dimension of the systems here, but when this condition is requirement is that Alice's outcome Alice's observable has to be mutually anti-commuting, Bob's has to be mutually anti-commuting, and such a choice can be available even for the qubit systems. But in the Bell scenario, you don't need to mention the dimension. But for the qubit system, the simple example I can provide, that is when A1 equal to sigma x, A2 equal to sigma z, and B1, B2 can be chosen cleverly, and they are also mutually unbiased basis. That means they are mutually anti-commuting. So for this particular entangled state, you can get the value 2√2. So what does it mean by that? When we get the value of this beta 2, the Bell expression, value is more than 2, we say that local realism does not hold. That means the factorizability condition I have mentioned here, that is based on the local realism assumption, the local realism does not hold in quantum theory. Once again, let me rephrase the quantum non-locality once more. Quantum non-locality says that the quantum statistics, I mean, all quantum statistics cannot be reproduced by local realist models or local hidden variable models. Good. So this is a very well-known scenario. And now let me just tell one slide that what is multipartite non-locality scenario. In the multipartite non-locality scenario, there is again a single source that distributes the particles in many places, many different parties. So it may be the case that, for example, there's a very common example is the G8Z state. For example, there's a 5 observers are here, so there's a 5-qubit G8Z state. You have then a single source distributes all the systems to all the 5 parties. And this is the that is also very well studied in the last 20 years. It has been studied extensively, and people have demonstrated multipartite non-locality. So why I'm discussing multipartite non-locality is that the network scenario is little different. In the network scenario, we have many independent sources, not the single source. So these were actually first introduced, this bilocality and bilocality scenarios that was first introduced by Branchier, Gisa, and Pironio in a paper in 2012. And that was actually motivated from the entanglement swapping experiment. So briefly, I just mentioned the entanglement swapping. That's also very well known to the guys who study quantum information theory. In the common, very simplest entanglement swapping experiment, there are 3 parties, Alice 1, Bob, and Alice 2. And throughout this whole lecture, I shall be considering that there's only one Bob and there are many Alices possible. So here Alice 1 and Alice 2 are there. So there are 2 parties. Importantly, Alice 1 and Bob are sharing an entangled state, that is psi plus A1B. And Bob and Alice 2, the second Alice, also sharing another entangled state with Bob. Now you can consider if it's a 2-qubit entangled state, then Alice has 1 particle. Alice 1 has 1 particle, Alice 2 has 1 particle, but Bob has 2 particles. So Bob, when he has the 2 particles, he can 2 particle and 2-qubit system. He can consider measuring a Bell operator, and you know that Bell operator had 4 eigenstates. All are the Bell states, that's the Bell basis. So by performing a measurement, Bell operator measurement at here, and post-selecting one of the eigenstates, produce an entanglement between Alice 1 and Alice 2. Why this interesting? Interesting in the sense is that there is no connection between Alice 1 and Alice 2, and they never interacted. I mean, the particle they have, Alice 1 and Alice 2, they never interacted, but due to this measurement by Bob and the post-selection, this Alice 1 and Alice 2 can get entangled. Actually, the work I shall be discussing the bilocality scenario, it is quite similar, but actually the whole entanglement swapping experiment is actually not required, but they presented the whole paper in the beginning that this is kind of swapping experiments. Well, this is now let me discuss about the bilocality scenario, which is nothing but just entanglement scenario, just entanglement swapping scenario I just discussed, that there's Alice 1, Alice 2, and the Bob. Now, Alice 1 is receiving 2 inputs, Alice 2 is receiving 2 inputs, and Bob is also receiving 2 inputs. And all the outputs are actually dichotomic again. The important thing is here that, as also in the swapping experiment, that there are 2 independent resources. That is S1 and S2, there are 2 resources, and they are actually producing the lambda 1 in the classical theory, and S2 producing lambda 2 in the classical theory. The important assumption here is that S1 and S2, they are completely independent and they are uncorrelated. So that means the joint distribution, that's rho lambda 1, lambda 2, can be factorized as a rho lambda 1 into rho lambda 2. So this is the assumption of factorizability of the sources here. Now, similarly, what we calculated for in the Bell CHSS scenario, that we calculate a joint probability distribution. Here we calculate a joint probability distribution of 3 outcomes, that is A1, B, the outcome of Bob, and Alice 2. So this is the joint probability distribution we shall be considering, and we use the factorizability condition again because I shall be using the assumption of locality here. But there are 2 factorizability assumptions. One is the source factorizability assumption that you can see here. It is written rho lambda 1 and rho lambda 2. Now again, you can see here that this joint probability distribution is actually in a factorized form. That is, probability of getting outcome A1 is dependent only on the X1, that means only on the input of Alice 1 and lambda 1. And it is independent of the Bob's outcome, Bob's setting, Alice 2's outcome, Alice 2's setting, and also on the lambda 2. It is independent of lambda 2. And similarly for Alice 2's outcome. Now, importantly here in the Bob's outcome, you can see Bob's outcome is B, and it is independent of the Alice 1's setting or Alice 2's setting or outcome, everything, but it is dependent on lambda 2. So you can see from the pictorially from the picture. So then we can also calculate, once you have the probabilities, everything is actually we can just calculate a joint correlation of 3 observables. For example, one observable of Alice 1, one observable of Bob, and another observable of Alice 2. Then you can calculate a joint correlation from here. Now, in this paper in Bankyard, Gisa and Pironio in 2012, they actually formulated that this particular kind of nonlinear inequalities, and then that can capture a peculiar form of non-locality within the whole network, within the whole 3 observables. And they defined that very interesting thing. You can see there are 2 correlations they defined, and they took there's a modulus and the root. So it's a nonlinearity is there due to the root, and they showed that the bound of this quantity is also equal to it's 2. It's quite the value is quite same, but actually the whole motivation and the conceptual things behind this is completely different than the Bell CHSH scenario. So they define this J1 and J2 in this manner. You can see, I mean, I have to explain a little bit about the notations, because the whole paper will be, whole talk will be a little complicated if you don't understand the notations. So you can see that I define this, I shall term it as a bilocality expression. So it's a bilocality expression. If you consider here, there's a delta, there's a superscript 2 and subscript 2. The whole talk, in the superscript 2, I mean that number of input. You see there's a number of inputs is 2. So I use this number, the subscript 2 is for the number of input, and superscript 2 is actually the number of parties, number of edge parties. So you can see there are 2 parties. I use the terminology edge parties for the Alice 1 and Alice 2, and Bob is the central party. So there are 2 edge parties, that the superscript is 2. There are 2 inputs, that's why the subscript is 2. And this terminology, that notation will be using the whole throughout the talk. So now you can see there are 2 correlations, J21 and J22 here. So that's a difference is that these 2 observables corresponds to the Alice 1, because you can see that's the superscript is 1, so that corresponds to the Alice 1, and this is for the Alice 2. And similarly, the correlation, second correlation, which is only the replacing the plus by the minus. So using this correlation, they calculated the bound will be 2. It is simple. I shall show a derivation for the more input scenarios. Now, in quantum theory, instead of taking these lambdas, that's a classical hidden variable models, you can have the entanglement resource. So you can consider there's an entanglement being shared between the Alice 1 and Bob. That means the source S1 is producing an entangled state, and S2 is also producing an entangled state. As I already mentioned, the assumption should be same. That is, source 1, S1 and S2 is completely uncorrelated. That means these 2 entangled state is completely uncorrelated, as we used then the swapping experiment. So it is seen that this violation, we get the optimal value of this bilocality expression in the quantum theory gives to √2. Again, it's quite same bound value we get like CHSH, but the conceptual viewpoint is completely different. Now the requirement again the similar, that observables of Alice 1 has to be mutually anti-commuting. Observable of Alice 2 has to be mutually anti-commuting, but Bob's observable has to be commuting. And the state that is required has to be the maximally entangled state. So this is the requirement. Once again, I have not mentioned any dimension, but since these requirements can be fulfilled for the qubit system, so you can say that these are the choices of the observable you can take for the qubit systems. And then B1 is a sigma z, tensor product sigma g, and B2 is sigma tensor x, tensor product sigma x, and they are definitely the mutually commuting. And the states required this, and that will provide the optimal value to √2. So we get the violation of the bilocality inequality. You can say that's a this is actually the non-bilocality we have. Now, in the literature, it's very hard to find that how this bound is calculated. Okay, and there's one work that is there by Tavakoli and this Gisa and Brunner, and also the Cyril was there, I think. So they calculated by using the Horodecky criteria that is used, but Horodecky criteria has a limitation that it cannot be used for the more than the qubit systems. But in our case, here we will need the optimization. We will need to use the more than qubit system. So we developed a technique which is common, but we actually modify this technique, and which is the sum of square approach. And using the sum of square approach, actually we shall be using throughout the talk. It is required, but I shall show the simplest form of it for understanding purpose. But in the paper, it is you can get the complicated sum of square approach is there. So it is essentially that we define a operator, this is gamma 2. Again, the gamma 2 means that the superscript is for the number of edge parties, and the subscript 2 is for the number of inputs we use. Well, so we define that this positive operator, this is a positive semi-definite operator. That means values can be greater than or equal to 0. We define in such a way that gamma 2's value can be written in this particular form. This is minus delta 2, which is the bilocality expression in quantum theory, and beta 2 is some number. Actually, this is the number we have to quantify. So when you have as I mentioned, it's a semi-definite operator. So then when it is 0, then you can get the optimal value of this, of the bilocality expression. So for our purpose, we defined the suitable positive operators, that is M1 and M2, which is at the polynomial function of the Alice's observable, Bob's observables, and Alice 2's observables. So this is defined in this particular manner. And you can see this M1 dagger M1 here, M2 dagger M2. Already I mentioned M1, M2 are the positive operators. And also I am assuring you that omega 1 and omega 2 are also the positive numbers. Okay, so the whole things are positive semi-definite. And this is the technique I developed in a paper published in this year in a physical review A, but not for this purpose. So it was for the general Bell inequality purpose, and you may take a look also. So we have cleverly chose this operator M1 and M2 in such a manner that M1 psi can be written in this particular form. It is cleverly designed. And here omega 1 1 and omega 1 2 is very important quantity. We can see that it is kind of normalization constant. So, and this omega 1 k, that means, for example, omega 1 1 is nothing but A1 1 plus A2 1, and it's the norm of this. And similarly for omega 2. So then, if you put it the M1 psi and M2 psi in the previous equations, you can derive actually exactly that gamma 2q equal to minus delta 2. This is the quantity we want to get the optimal value of it, and we can simply write that so root over omega 1 plus root over omega 2. So the whole thing is now to optimizing these two quantities. For example, when gamma 2 equal to 0, as I mentioned, it's a positive operator, then we can get the optimal value of this bilocality expression. That's delta 2. And that is only obtained when you can obtain when M1 psi and M2 psi both are equal to 0. So this is the things we have to optimize, we have to maximize. So you can write this omega 1 is nothing but, as I mentioned before, you can see that omega 1 is actually the product of omega 1 1 and omega 1 2. So you can write here, then it's omega 1 1 and omega 1 2, and similarly here you can write, and this identity we can always use. Is it as if it's an independent CHSH form? I mean, if you want to say, you want to calculate want to optimize the CHSH inequality by using my approach, then you can find that this is actually the independent CHSH. And here you can see here that this is actually the all Alice's observables. Alice 1 observables. That's A1 plus A2 plus A1 minus A2, and you know what the value of it is very common. It's very maybe sometimes you may look at joint measurability conditions. So its value is 2 root 2. It is, we know it, and it is only available when this A1 and A2 are mutually anti-commuting, and also for the same for here. So that means that these two observable A1 2 A2 2 are mutually anti-commuting, and this is obtained the value 2 root 2, and we can derive this 2 root 2 values. And also from here, from this condition, M1 psi equal to 0, M2 psi equal to 0. From this condition, from here, you can simply just estimate what is the observable Bob's needs, and it is found to be that Bob's observable are mutually commuting. How much time I took? Well, so now I shall quickly go to the straightforwardly go to the multi-input scenario, which is the purpose of the present talk. For better understanding, I shall give a little more generalized version of it without going to the all arbitrary n or scenarios. Again, I am considering the bilocality scenario. For bilocality scenario, there are two edge parties, but you can see the inputs are 3 inputs for the Alice 1, 3 inputs for the Alice 2, but Bob has 4 inputs. So it is a little bit generalized than the bilocality scenario we considered earlier. Again, the all things remain same, that is S1, S2 independent and all things. So we define 4 correlations here. Correlation, because we have 4 input for the Bob, so we have the 4 correlations here. So we consider the 4 correlations here. And this bound is 6. Now the bilocality bound, the bound of this bilocality inequality is 6. That I shall show the derivation of it. Now these are the explicit form. I think it is very hard to follow in a very quick time, but you may take a look at my papers. So you can see that's a B1, B2, B3, B4, and corresponding to these 4 observables, we have these correlations. And this left-hand side, A1, A2, A3 are for the Alice 1, and right-hand side for the Alice 2. And you can see that we can just replace one here all plus, but here 1 minus, there's another minus here, and this is also minus. By using this particular symmetric manner, we can actually derive the bound is 6. For this, let me show you quickly. So I consider the first correlation, that is J31, which is the all plus here, it's a B1, and it's all plus here, the Alice 2's observables. Now, J31 can be written this particular form because these are the quantities. This is the quantities in the lambda. I mean in the lambda levels observables. So when you have provided the lambda 1, then its value will be plus minus 1 because I have considered the dichotomic outcome. So you can write this in particular form. If you take the modulus, so modulus can be written in this particular form. But you can take a look at this one, the modulus of B1, as it's a dichotomic one. So its value is always less than or equal to 1. If you put it here, so you could get the inequality here. So this inequality now, this is for the Alice's 1 and this is for the Alice's 2. Similarly, all the 4 correlation, all the 4 J's, J1, J31, J32, J33, J34 can be written in this particular manner. If you do it, and using this inequality, this inequality, that's very well. I think this is a well-known inequality, concavity inequality. If you use it, and you can actually write in this particular form. And again, I'm sorry for this clumsy notations. So delta 1 can be written in this form. You can see this is all plus, but the modulus here, and here's a 1 minus, and the modulus here, and another minus. Of course, the modulus is very important. And this is minus and modulus 1. And it can be seen that whatever value you choose, A1's value is plus minus 1, A2's value is plus minus 1, and all the values are plus minus 1. Whatever value you choose because of the modulus, you will get always the value 6. So we get the non-local bilocality bound for this many input scenario. We get the bound is 6. And optimal quantum value, if you calculate, it will give the 4√3. Again, it is calculated by using the sum of square approach, and it will be very difficult to explain in this talk. But you may take a look at my paper in the appendix. It is provided there. So just let me tell you once again, what's the finding is that this all the Alice observables of Alice 1 or Alice 2 must have to be the mutually anti-commutative again. And Bob's observable can also be found, can also be calculated in this manner. So B1 is written. Similarly, B2, B3, B4 can also be written. And the state required here is the maximally entangled state. Now, since our requirement is the 3 mutually anti-commutative observables for the local system of Alice 1 and Alice 2, so that can be available for the qubit system because sigma x, sigma y, sigma z we have, and this can be possible. Then the optimization is possible again for the qubit system or the local qubit system of Alice 1 and Alice 2. So this is possible. Now, if you go to the higher dimension, higher number of inputs, in that case, qubit system will not be enough. So the things become complicated. So this cannot be handled by this Holodoki derivation. In fact, in the bilocality scenario and in locality scenario, derivations are not very given. I mean, more than qubit system, it is not considered until us. Well, I'm skipping this part. Okay, so what is the n locality scenario? Up to now, I discussed the bilocality scenarios and a bilocality scenario for 2 inputs and bilocality scenario for the 3 inputs. Now, I shall be considering the n locality scenario for m inputs, and n and m both are arbitrary. So, n locality scenario actually involves n sources. Let me go to the picture. So this is the n locality scenario. We consider a particular network, the star network scenario. Later we have considered other networks also. That will be uploaded soon. So this is the star network scenario. You see there are n number of parties, n number of edge parties, Alice 1 to Alice n, and each edge party is receiving m number of inputs. M is also arbitrary, n is also arbitrary. And we have n number of sources. You can see here that's S1 to Sn, n number of sources are here. And these sources are independent to each other. That's the assumption of the n locality, as we did for the bilocality assumption. Now, the Bob is receiving 2 to the power m minus 1 number of the inputs. So each Alice receiving m number of inputs, and Bob receiving the 2 to the power m minus 1 number of inputs. And there are total n number of edge parties. And this is the scenario we have studied. Well, so, and also just to mention that all the outcomes are dichotomic. That means their values plus minus 1 or you can say it's 0, 1. And we use actually the technique for this calculation and for constructing the inequality. We use the random access code as a tool to construct the correlation, construct the suitable correlation here. And we define this n locality inequality scenario. That is, we define an expression like how much time?
Maybe about 10 minutes. Yeah.
I have 10 minutes, right?
Yeah.
Okay. So n locality scenario, as I mentioned, n is arbitrary, m is also arbitrary. So we defined 2 to the power m minus 1 number of correlations. So if, for example, if m equal to 4, you will have 8 correlations. So a number of JMI is number 8 if you consider m equal to 3, m equal to 4. So this correlation is defined in a very particular manner. I have considered that you can see that's a minus 1 to the power yixk. It's very, I'm sorry because of the notation. It's very, very clumsy. So the meaning of this, why I introduce yxk, I shall explain soon. So this is the quantity we want to, this is the quantity we defined for the particular j, for the each I, it's a 2 to the power m and m minus 1 number of i's. So we define that number of correlations here, and this is the notation I'll be using JMINK, and JMINK is nothing but this form. And what is the value of this yxki? Yxki is actually either 0 or 1, so it's actually plus and minus. So this will be using to fix the plus or minus before these observables, right? And again, the non-locality assumption, n-locality assumption is that all states, all the sources are independent, so distributions are completely independent to each other. And we define this quantity as a JMIN to the power 1 by n. In the bilocality scenario, we had it's a 1 by 2. That means we have taken the root. But here, n-locality scenario, we take 1 by n. So we can write this particular form of this quantity. And then the whole scenario, that is whole delta mn, it's an n-locality expression, we can write in this particular form as a summation 1. Actually, then there is a summation and there's a product. And for our calculation, we actually using this inequality as an exchange between the sum and sum of product and to product of sum. Using this inequality, we can change it to the sum of product to the product of sum. So this is the quantity we get, and there's a product. And this we denote as alpha mk. And this we will actually be used in optimizing in the classical theory and classical hidden variable theory and also in the quantum theory. And since we have taken a completely symmetric things, that is all Alice has same inputs, so we actually get all alpha mk, it can be written as alpha m, it's independent of k. For every k, it is same. So if you put alpha k here, and alpha k to the power 1 by n, and there's a product is also k equal to 1 to n, that means actually it will return the alpha m only. So we actually optimize the alpha m in classical theory and in quantum theory. Okay, this is very complicated once again. So alpha mk can be written in this particular form. You can see there's a two summation. This summation is for the number of inputs, and this summation is for the number of inputs for the Bob. This is for the number of inputs for the Alice. So now let me fix that. How to fix this yxki? That will give you that how the correlation is actually constructed. So for this, we used, as I mentioned, I used the other encoding scheme of random access code. That is, we considered that there's a random variable y delta, which is 0, 1 to the power m, and where the number of delta is 2 to the power m definitely here. That means the 2 to the power m number of m bit string. Okay. So for example, if you take y delta equal to 0, 1, 1, dot, 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 whatever dot, how many dot you can put it, and 0, 0. In such a case, yx1 delta equal to 0. That means the first bit is yx1 delta equal to 0. So in that case, minus 1 to the power this will be plus. But whenever it's a 1, it will be minus 1, and it is so on. But for our purpose, we have not used delta. We use I. So we did a particular kind of encoding we have taken. So we took that number number of bits where first bit is 0. So then that is actually half 2 to the power m minus 1. So using this, we can actually calculate the fix what is the plus and minus just behind this an observable. For example, if you give the example of CHSS scenario, the bilocality scenario in 2 inputs, let's say either 0 or 1. So it's A1 plus A2, and you can get A1 minus A2 as well. Well, it's complicated. So it actually can be written in terms of the it's for convenience we have written in terms of the augmented Hadamard matrix, and which has every column is actually y1, because yi is actually the every column you can write, and you can see all are 0 here, and here all is 1 is 0, all are 1. So that's the first row is all 0. That's I mentioned before. Okay. So using this, maybe I can skip this part because it is very complicated and it is not very understandable in this moment. Okay, so what we found is that this calculation was little bit involved. So we found that the bound in the bilocality bound is this one, where m is the number of inputs, say mcj, and m minus 2j, and summation running from 0 to m by 2. It's a floor function. It's a floor. So we found that this is the bilocality bound. And we calculated by using again the sum of square approach, and in this time it is highly complicated. We calculated the bound is 2 to the power m minus 1 root m. So it is our classical bound, in locality bound, and this is the quantum bound that we have calculated. And we find that if you plot it for the Rn, the ratio between classical and quantum, we find that it is plotted over m, not n. It's a mistake. It's m. So number of inputs, if you calculate it, you will find that actually increasing the number of inputs is actually reducing it, and it is actually maximum when m equal to 3. Now, the important thing is that to get this optimal value in quantum theory, what is the requirement? Requirement is that each Alice has to use the arbitrary m number of observables, and that has to be mutually anti-commuting. So in qubit system, we have only maximum 3 mutually anti-commuting observables. So when the number m is arbitrary, you need m by 2 floor. The dimension of the Hilbert space has to be, local Hilbert space has to be 2 to the power tensor product m by 2 floor function. So that means you have Alice, and each Alice and Bob has to share m by 2 floor number of 2 qubit maximally entangled sets. For example, when you take the m equal to 4, Alice 1 and Bob has to share a pair of qubit entangled sets. And even if m equal to 5, the pair of 2 qubit entangled sets is also the sufficient. But if you take m equal to 6, in that case you need to consider the 3 2 qubit entangled set has to be shared between Alice 1 and Bob. Not only Alice 1 and Bob, each edge party and Bob has to share this kind of entanglement. So the total state can be written that is required for the optimization is this particular form. So this has been calculated in this paper. So let me conclude here that I discussed this bilocality and n-locality scenario in the quantum network. Mainly I considered the star network scenario, and actually we have now generalized for the linear chain and many other network scenarios. And as I mentioned, as I first showed that for m equal to 3 cases, and we find that m equal to 3 cases, the qubit system was enough. Each Alice and Bob, if they share a 2 qubit entangled state, that was enough to get the optimum value of quantum theory. But when you increase the number of inputs, the qubit system is not enough. You have to use some other, the higher dimensional entangled state. Higher dimensional does not mean here, interesting form here, that it's not higher dimensional. The sense is that it's a m/2 number of entangled states is required to share between each Alice and Bob. And I think that's all I had to say. I think I finished a little earlier, and you may ask questions. Thank you.
Thank you very much, Professor Alok, for regaling us with this really interesting talk. And unfortunately, you probably had to curtail your talk a bit in view of the time constraints.
Yep.
So, so the stage is open to the audience to ask questions.
Too heavy.
Hello, Alok.
Guruda.
So, can you go to your this sum of the square approach, something like that?
Yeah, sure. Maybe I lost it. Where it is? Yeah, got it. Okay, I'm going. There's some problem I'm finding. Problem? What happened? Something has happened here.
Yeah, but let me make a comment. In slide, what I saw, that left-hand side, some operator acting on a vector.
Yeah.
But on the right-hand side, it is number. Some mod something, root over mod of something. So that may be there may be some mistake in writing. Because some operator acting on a vector gives you another vector. Cannot be a number.
I understood. Actually, the problem is that the left-hand side also has to be mentioned. That I forget to mention that one. The left-hand side. I mean, the side.
Left-hand side should be in the mod.
Psi M1 dagger should be there.
Oh. Okay.
Yeah.
Right. I got it.
Yeah, that's a mistake. Yeah, that's a mistake. Yeah. I don't know. I cannot make it.
Any other question? Okay, if there are no further questions, I just have two minor questions to ask Professor Alok. So it's very interesting. I was like, you kind of partially answered what I wanted to ask. One thing is you presented here only the star topology, right? And you looked at other things like the chain. So have you also considered, or can you comment on the extendability of your method? For example, if you have networks with cycles?
Yeah, I think it can be extendable, because what was the problem is that the network scenario, due to this mod and root, it was difficult to optimize. Maybe numerically it can be done, but analytically it was very hard to optimize. That's why people have not gone beyond qubit system. So the first time this worked, we go beyond qubit system. Otherwise, yeah, you are right. Actually, you are also considering the other scenario like cyclic networks and many other topologies of the network. We are also considering. Yes.
Okay.
Hello.
Yes.
Devasita.
Devasita.
I have a small comment on this.
Sure.
Actually, if someone goes from this open type network to closed type network, then the situation is little bit complicated.
Yeah, it's complicated. Yes.
That is not easy to understand. To cope the topology of this situation, we have recently tried for triangle network this kind of things. The result will be under preparation. I have actually in this conference I have given that lecture on that triangle network situation.
I was doing election duty that day. No problem. I'll listen later.
No problem at all. We can discuss later.
Yes.
So if someone goes from this open type star or linear chain to some closed network or more complicated, then the situation is really complex enough. So
actually, this is my first work. So yeah.
Even some simple system, triangle type system, is complicated. Okay.
So you have written the paper. Already you have written papers, right?
No, that paper I have not sent. Just we have some results.
Okay. Okay. So we'll be very happy
that
to see.
I have discussed in this meeting also.
Acha. So maybe that's available in the YouTube soon.
Available in recently. I will give it to post to archive. Okay, then you will see.
Yeah. Actually, the paper with Amit, I closely studied, and we had a similar plan to extend this work.
Now, Amit is working on that things. Amit is actually the main scholar. He is working on that triangle network thing. Actually, last year when I give the lecture at RRI, then Asin puts that question whether this could be done in triangle type network or not. Okay. And then we have to take this challenge, and now that problem is almost solved. Okay.
Yeah.
We will put in archive very soon.
Yeah. Okay. And what is I just want to mention that last time we had the similar discussion here at RRI. After that, I started working in this direction actually.
I observed it is a very interesting work. Okay. Good. Okay. Thank you, Alok.
Thank you.
Thank you, everybody, for your questions also to Alok,
and
Debashish, and Guruda.
Yeah.
So if there are no further questions.
Sikant, can I use this platform to announce something?
Oh, please do. Please go ahead. Yeah.
Actually, I have a open postdoc position, and if anyone is interested, and I know there are many students also. I mean, if anyone is interested, I mean, I think if someone is submitted the thesis, also may be eligible for the to apply. So this is available for from the immediately. I mean, my one postdoc has left because he got a job. So it is available for the 2.5 years, and also the Professor Guru Prasad Kaur also is the co-PI of this project, and any interested, I'll be very happy. Yeah.
Thank you, Alok, for this. Yeah. So thank you, everybody. So we can, I guess, move on to the next talk. Is that okay, organizer?
Thank you, Sikant.
Thank you, Alok. Yeah. Bye.
Yes, sir. Yes.
We can go on to the
Yeah.
I mean, you guys have to do something because I think something has happened to my screen. I cannot go back to the thing. So you may take control of it. Yeah. Now I stop shared. Yeah. Yes, it's okay.
So, thank you, everybody. Now we move on to the last talk of this session, with the speaker being indeed one of the persons who had esteemed members of our audience who had just now asked a question to Alok. This is Professor Guru Prasadkar, and he'll be talking about multi-copy adaptive local discrimination, strongest possible 2-qubit non-local basis. Professor Guru Prasadkar received his PhD in physics from Kolkata University. I might as well add that he and his PhD guide, Professor Shishir Roy, have been pioneers of quantum foundations and quantum information theory in this country. And Guruda has been faculty of the Indian Statistical Institute, Kolkata since 1999. And presently he is a professor there at the Physics and Applied Mathematics unit. His area of interest are the foundations of quantum mechanics and quantum information theory. Over to you, Guruda.
Thank you, Sikant. Introduction. So, so my screen, can you see my screen?
Yeah.
It's okay?
Yeah, it's fine.
Then I am going to start. So first, let me thank the organizer, especially Subhashish, for organizing this online conference in this pandemic situation. And most possibly, he organized one more last year. So This is a talk purely on quantum information, and the talk is based on this paper in Theorem, led by Manik Bonik. And maybe Manik Bonik would have been the best person to present this talk, but I don't see him in the speaker's list. So I thought that let me talk. So this is about distinguishability of quantum states. Why this question of distinguishability comes to quantum mechanics? Because in quantum mechanics there are states, there are different states which cannot be distinguished. Of course, if you take non-orthogonal state, this cannot be distinguished. But here what we are going to study is that states are orthogonal, but they are shared between or they are shared among many partners. The question is whether the states can be distinguished by local operation and classical communication. So, if you consider classical world, then objects should be distinct in at least one of the measurable property. I mean, in classical world, if two states are different, then there must be some property measuring which you can tell which state it is in. Quantum, if you come to quantum world, if the states are orthogonal to each other, we will be considering only orthogonal state, because already we know that non-orthogonal state cannot be reliably distinguished. Even if you consider a set of states which are linearly dependent, then of course the probability of distinguishing among them is 0. So we will be considering only orthogonal states. Now, if you consider quantum world, if you take orthogonal states, then of course you can have an observable measuring which you can identify the state. So if you consider orthogonal quantum states and classical world, there is no difference apparent. So classical case, you can consider a two-level system, say two-level classical system. So there may be say two color, red or green, red or blue. So how do you distinguish? You measure the color and you can distinguish among the different states. Quantum world, if you consider just two orthogonal states, then if it is a spin state, then you measure the spin along a particular direction and you can identify which state you have been given. Now, you can come to classical and you consider a two-level classical system. So, and you are considering two properties, color and shape. So now, in classical world, if these are the four possible states, then of course by measuring color and measuring the shape, you can identify the state. Correspondingly, if you consider, of course, I have considered four base states. So how do you identify these four base states? They are orthogonal. So what you have to do, you have to measure the Bell basis jointly, and then you can identify the state. So till now there is a one-to-one correspondence between classical and quantum because we have considered orthogonal state, and we have not imposed any restriction on measurement. Now, let this global access is not allowed, so that in classical world, one particle has been given to what in classical world you are considering two systems. One is with Alice, another with Bob, and you are considering these four possible states. Now, still this can be distinguished in classical world by just communication. How? Measure the color for the first and shape for the second, and just they should communicate with each other and they will identify the state easily. Now there is a big difference. If Alice and Bob share this Bell state, one of the Bell state, and they have to identify the Bell state by local operation and classical communication, that means they are far apart. They can measure, they can make measurement on their own particle, but they cannot measure both the particles in the same layer. But they are allowed, of course, to communicate. Then this is impossible. Four Bell state, four orthogonal Bell state cannot be distinguished. So this is impossible. So already we see a stark difference between classical and quantum. But of course, for that we have considered entanglement state, but later we will see that entanglement is not necessary for this. Now let us see the proof why this four Bell state actually it may be a stronger statement. Actually, the probability of identifying among the four Bell state is 0. That means with some probability even you cannot identify the state. Let us see the proof. The proof is very simple. That Alice are Bob far apart, but that they share some classical variable, classical correlation. Using that classical correlation, Alice and Bob can prepare this separable state. To look at it closely, you see this BK means BK means Bell state, B1, B2, B3, B4, these four orthogonal Bell state. Now, this is Alice and Bob can of course prepare a separable state by just in a local way. This BK is a Bell state, this BK is also a Bell state. So this is a correlated state, but it is separable across Alice and Bob. So it is 1/4 BK for AA1, A and A1 are on Alice's side, and B and B1 on Bob's side. So by preparation, this state is separable between Alice and Bob's lab. But Smalling, most possibly in 2000, showed that this same state, which is separable across Alice and Bob, can also be written in this form, where you see this state can also be expressed as Bell state between AB tensor Bell state between A1 and B1. This was done by Smalling, and the name of the paper I should have referred to. Actually, the name of the paper, Unlockable Bound Triangle. Most possibly it was discovered in the So this state can be written in this form. Now you can have a big result. Now if we assume that this four orthogonal Bell state can be reliably distinguished, then there will be a peculiar result. If by this pair, say by this pair A1 and B1, Alice and Bob just distinguish this state by using local operation and classical communication, then this state is destroyed in knowing this state. But still, they will have a known Bell state. Because if they know which Bell state they are sharing by local operation and classical communication, then the other pair will remain, and they will get just one bit of entanglement between Alice's lab and Bob. So what happens? You prepared a separable state, and if you assume that four Bell state can be reliably distinguished by local operation and classical communication, then you have created one bit of entanglement between Alice and Bob's lab out of separable state, out of nothing. So this is impossible. So this tells that four Bell state cannot be reliably distinguished, but it is much more than that. Actually, you can make because it is separable. Even with some probability, we can identify the real state by local operation and classical communication. Then actually we will create entanglement across Alice and Bob's lab, and that is impossible because you cannot create entanglement by local operation and classical communication. So the result is much stronger. And not only that, already I have stated all these things. So not only that, actually you can show that even 3 orthogonal base states cannot be reliably distinguished, just extending this result. But of course, in that case, with some probability you can identify base state, but you cannot with 100% probability you can identify among 3 orthogonal base states. Yeah, but actually, this is a very profound result using thermodynamics of entanglement, but we are not lucky that we can solve all the problems of distinguishability involving entanglement by using this kind of elegant principle on entanglement. Myself, Devashish, Shivashish, Ujjwal, Aditi, we all tried to extend the result to other states, non-maximally entangled states. But we are not successful to discriminate all the cases. We could not comment on all the sets which involves entanglement. And actually, one has to analyze the possible POPM that Alice or Bob can apply, and then using this orthogonality of force measurement tested, using this kind of result, Hardy and Walgett finally could solve the problem completely for the Qkd tested. I mean, problem of indistinguishability. And this impossibility of identifying orthogonal state by LOCC has implications like in data hiding, secret sharing, and just some implication in foundational aspects also. In particular, data hiding, it is very important, and I would ask the students to especially read this paper written by Theorem and Divinson and others, published in 2001, because just we will see that 2 pure orthogonal states can always reliably be distinguished. So data hiding is not possible using pure state. It follows from the result of Hardy-Walgett. So this Theorem and co-authors, they actually could design a two orthogonal mixed state which cannot be distinguished by local operation. So this is very, very powerful result. And then the result was extended by this, most possibly Warner is also there. Now, till now what we discussed is that we cannot distinguish among some states when the states are when one copies of the state are given, like all the state cannot be reliably distinguished. But what about if you are given 2 copies? Then it can be easily done. What you do is 4 base state, if you are given 2 copies of the state, then you can reliably identify the state. What you do, you first both measure sigma z. They see whether correlated or anti-correlated. Then they can identify the group in which whether it is anti-correlated group or correlated group. Still there will be 2 more states, and then they can be identified by measuring sigma x. So with just 2 copies, you can identify the best. Now we are coming to some results, as I told you, provided by Walgett and Hardy. They proved that any two, as I told you, any two orthogonal states can be discriminated under LOCC given a single. So this is a very, very profound result. Any two orthogonal states, we are considering only 2 parties, but whatever the number of parties is, if the two states are orthogonal, they can always be discriminated by LOCC with a single. And if there are n number of orthogonal states distributed among some parties, then if you ask how many copies are there to reliably distinguish among them, then there is a result which tells that n-1 copies are sufficient. These are shown by Walgett and Hardy as well as from Provisional Protocol. That with n-1 copies you can do it. So if you take four states in it for 2 qubit system, so with 3 copies always you will be able to distinguish. Then the result is 3. If you consider 3 2 cross 2 orthogonal states, then they can be distinguished if and only at least 2 of them are polar. This result will be useful for our result that I am going to tell. Very important. To consider 3 orthogonal states for a 2 qubit system, then they can be reliably distinguished if at least 2 of them have to be polar. And if you consider 4 orthogonal states for 2 qubits, then they can be distinguished if and only if all are polar. So there could not be any entanglement. And this is the famous result that we told that Hardy and Walgett showed that if you consider just 2 orthogonal pure states, then they can be expressed in this. But these 1, 2 up to n, they are orthogonal set, and is eta1 orthogonal. This is eta2 orthogonal. So this any 2 orthogonal states can be written in this form, and then you can see that by just one way LOCC can be distinguished, because addition measuring 1, 2 up to n in this basis, she will collapse on one of the terms, and then Bob, if he informs Bob in which basis he has to perform the measurement, then Bob will know it, and Bob will perform the measurement in this basis, and they will identify the state. The question is, as I told you earlier, are there such problems with product states too? Sometimes we might feel that, okay, this impossibility of distinguishing among orthogonal states is a peculiar feature of entanglement. Of course, entanglement plays a role that we saw, but entanglement is unnecessary. Bennett and his collaborators in 1999 to provide a set of product states in 2 qubit system. They provided 9 orthogonal product states which cannot also be distinguished by local operation and classification. There are 9 states, but it is in 3 clusters. Of course, it gives a separation between LOCC and separable superoperator. Because of course you see that if you consider the projector on all these 9 states, if you make measurement in that projector, you can identify the state easily. So measurement is separable, but it is not easy, it is not trivial to show, but it has been shown by Bennett as well as Walgett and Hardy that these 9 states cannot be discriminated by the operation. And there is no entanglement involved. That's why sometimes it is called non-locality without entanglement. In that paper itself, this Bennett and et al. Asked this question, are there any set of states entangled or not for which some finite number greater than 2 of copies of the state is necessary for distinguishing the states reliably? So far, we have found no examples where more than 2 copies of the unknown states are needed. So this is a very profound. They did not put it in the form of conjecture, but still no one could find a counter example. If you consider any number of orthogonal state, multipartite orthogonal state, then still now we have the results that have been known that if you provide 2 copies of the states, then they can be reliable. So there is no counter example for which more than 2 copies will be needed to distinguish among them. Still we don't know whether there are such examples. People have not found any example till now. So we have crossed maybe 22 years, but we have not found any counter example where more than 2 copies are needed to distinguish among these. In this paper, we are addressing this question, but with some restriction. So, if you are given 2 copies, or even more than 2 copies, how do you perform the LOCC? You can take the pair of the state, but you can also, one side there are 2 particles, other side there are also 2 particles. You can make joint measure. You can make single measurement on each qubit or each particle, but as well as you can make joint measurement on both these particles. So, and this joint measurement or measurement in some entanglement basis on Alice's side or on Bob's side, this is more powerful measurement. So we are not considering that case. In a state, we assume this we call an adaptive scheme. What we do, in a state of addressing both the pair at the same time, you are addressing one of them each time. So what you do, you take the first pair, you do LOCC, local operation and classical communication, extract the information from this first copy. Using that information, you apply suitable LOCC on the second pair and you try to identify the state. This is called adaptive scheme. And for the first case, it will be called non-adaptive scheme. So obviously, non-adaptive scheme is much powerful than scheme. So now what we are going to analyze, we will be assuming that we will be adopting this adaptive scheme. I mean, we will address a pair at a time and extract information from them, and using that information, we will perform LOCC on the second pair. If there are third one, we will extract information from each pair and then apply that on the last pair, like that. So now we consider a not bare state, but peculiar kind of entangled state. So we are telling there are 3 parameters. We are considering four orthogonal states, parameterized by alpha, beta, and gamma. How are the states? First state is A1, second state A3, and then A2 and A4. So A1 is phi minus alpha, where phi minus alpha is nothing but cos alpha 0 plus sin alpha 1. So phi is used for correlated state in Bell case, and psi is used for anti-correlated for Bell case. We are adopting the same notation. So this A1 is phi alpha minus. Phi alpha minus is cos alpha 0 minus sin alpha 1. A3 is psi minus beta. Psi minus beta means cos beta 0 1 minus sin beta 1 0. And A2, A4, we have taken linear combination of phi plus alpha and psi plus beta. and similarly for A4. But we have taken this thing in such a way they remain orthogonal. You can see they are indeed orthogonal. So you have to considering these 4 states, and it can be shown that all of them are entangled when alpha beta is between 0 and pi by 2 without being 0 and pi by 2. So it is in the open set, 0 and pi by 2. And gamma may be in the closed set, 0 and pi by 2. Now, if you take this choice, then all of them are entangled. Now we are putting a theorem. Now we are taking that, we are considering this state. Maybe we told wrongly is we will choose alpha, beta, gamma in such a way that all 4 remain entangled. That you can do. Now we are coming to it. If you consider this state where gamma is equal to pi by 4 and alpha is not neither equal to beta nor equal to pi by 2 minus beta. If you consider this set, then they can be distinguished reliably under adaptive LOCC protocol if and only 3 copies of the states are available. So this is a very powerful difference. But under adaptive LOCC. So under adaptive LOCC, you are contradicting that conjecture, which tells that with 2 copies, you can reliably distinguish among any number of orthogonal states. But if you restrict yourself to adaptive LOCC, then this is an example where 3 copies are required. I mean, with 2 copies you cannot do. 3 copies are necessary. But of course also sufficient, because there is a result that for 4 states, for n state n minus 1 is sufficient. So for 4 state 4 minus 1, that is 3 are sufficient. So but this is necessarily insufficient for this kind of state. So only thing that we have made, we have chosen alpha beta in such a way that all 4 are entangled. Now how? Now, if any orthogonal ensemble with 4 states is 2 copy distinguishable under adaptive LOCC protocol, if and only, what are the possibilities? So with the first copy, it may be possible that with the first copy, you can distinguish among these 4 states. It may happen. Of course, for qubit case, it may happen if and only if all of them are polar states. Or what may happen by measuring on the first copy, you can classify this state in this. You can divide the state into 2 groups, and you can identify the group. It may happen that either you identify the state or is in the complementary set. So maybe it is psi1 or it is one of these psi2, psi4 or psi. Or what may happen with the first copy, you can identify the set in which the state is, and the set is size of the set, both size of the both set is 2. I mean, you may be able to identify whether the state in this set psi1, psi2 or psi3, psi. Now, so these are all the cases that may happen after acting on the first copy. Now, if the state is 2 copy distinguishable, then for the second case, if you could identify psi1, then it's okay. But But the states are given with equal probability. Sometimes you may identify the set in which the state is, and size of the set is 3. Now, already from Hardy-Walgett result, you know 3 or 2 qubit, 3 orthogonal states can be identified if and only 2 of them are product. At least 2 of them are product. And third case, if with the first copy you can identify the set of size 2, then with the further copy you can identify the state if and only this subspace, I mean projector on this subspace is separable. Similarly, projector on this subspace spanned by psi 4 and psi 3 is also separable. So these are the conditions which has to be satisfied if the orthogonal ensemble is 2-copy distinguished. So let me go further and just tell the same thing. So if only 2 copies suffice, then either the state, as I told you, the state can be discriminated with 100% with just 1 copy. Then second copy is not even required. But now we are coming to a theorem. We are proving our theorem. So all 4 states are entangled. So this is impossible because all 4 states are entangled. So just with 1 copy, you cannot even probabilistically determine which state. So it is impossible. Now, for the second case, either you with the first copy, either you identify the state or you identify the complementary state. Then this complementary set contains three possible states. But then this complementary set should contain at least 2 product states. But we have taken all the states to be entangled. So this is not possible. Because if you identify the set with three states, then as all states are entangled, so all these 3 states are entangled. So there is no chance that you can reliably distinguish among these 3. This is also impossible. Now we are coming to the case that in the first copy you have identified the pair of sets containing 2 states. So in this case, as I told you, then the projector on, then in the second copy, you can identify the state, you can run the projector onto the subspace spanned by this AIAJ, has to be separate. But these states, these 4 states has been chosen so cunningly, the 4 states has been chosen so cunningly that in which way you divide these 4 states into pairs. If you take the projectors on this 2-dimensional subspace, they are always entangled. And it has been shown by calculating partial transpose. Here we have taken A1, A2 on 2-dimensional subspace and A3, A4. You can take A1 with A4. I mean, you can take all the combination and you can see subspaces are always entangled. So it shows that just with 2 copies of the state, if you adopt adaptive LOCC protocol, with just 2 copies, you cannot identify the states. Yeah. So they are not already, we have shown that they are not separable, so it is also impossible. Now we are coming to a theorem which actually you don't need to do anything to prove it. It's just obvious. If you consider an orthogonal basis of two qubits containing exactly 3 entangled states, then it is obvious that you need 3 copies of the state for perfect discrimination. The proof is obvious. I'll come to this. You look at this picture. So 3 states are entanglement, so 1 is product. So with 1 copy, so you cannot distinguish it by just 1 copy. Now come to the second case. So if you distinguish among 1 copy and the other 3, then at least in this state with 3 states there would be at least 2 entangled states. So again, you cannot do with just 2 copies. Now come to this point. This is obvious because both the subspace cannot be separable. Because in one of the subspace, it will be one entangled state, another is product state, and they are orthogonal. And if you that subspace can never be separable. The projector on that subspace can never be separable. I mean, actually, it follows from a more general rule that if you consider a pure entangled state and the product state, you cannot. If you take a mixture of a product state and the entangled state for the case, with whatever coefficient weight you give, you cannot make them separate. So it is self-obvious. That any orthogonal basis of 2 qubit containing exactly 3 entangled states, if you have 3 copies of the state for perfect discrimination, if you adopt adaptive velocity. Now, this is a nice result. So there are 3 entangled states, 1 is product state. So it involves less entangled state compared to if you consider 4 base state, 4 orthogonal base state. But for 4 orthogonal base state, just 2 copies are sufficient to distinguish among them. But we are considering a say where 3 are entangled, 1 is product. In that sense, it involves less amount of entanglement. But with 2 copies, you cannot distinguish among them. So it is a phenomena called more non-locality with less entanglement, first observed by Borodecki group, but they observed it in 3x3 system. But here you can see it in even qubit. Now we will show that not only that, using this example, you can show the separation between LOCC and separable superoperators. Already we know there is indeed difference between LOCC and separable superoperators. In particular, Chidambar has shown it. The examples. So how much time do I have?
You have about 10 minutes more.
Maybe I finish it. Sometimes I used to think that maybe separable superoperator is more powerful than LOCC. So of course, obviously, separable superoperator cannot create a time out of separable state. That is obvious from its mathematical construction. But still, I used to think that if we start with the entangled state, maybe which LOCC cannot do. LOCC cannot increase any. LOCC cannot increase the entanglement, but maybe separable superoperator can increase entanglement. But still, I don't see any example. And once I asked Professor Charles Bennett, whether a separable superoperator can increase entanglement. Charles Bennett answers simply negative. He believed that he told that he believed that separable superoperator is not that strong that it will create entanglement. But of course, there is indeed big difference between LOCC and but from this example also you can see this difference between LOCC and separable. I mean, you can see separable superoperator is stronger than LOCC. And of course, you know that. Yeah. So LOCC means it does not contain any entanglement projector. But if you consider separable superoperator, it also contains no entanglement projector that I told when I was discussing these 9 states in 3×3. But to implement it, you need assistance of some entanglement. And of course, if you consider global entanglement projector, but it can also be implemented locally with the assisted entanglement. Now, if you consider this class of 4 states, where this is pi by 4, gamma is pi by 4, and alpha is not equal to neither equal to beta. This is a parametric class which is 2-copy distinguishable under LOCC, but already we have seen that this is you cannot distinguish among these states with 2-copy. But the set can be distinguished with 2 copies if you consider separable superposition. So obviously it shows that separable superposition is more powerful than LOCC, even in this context. And there also we have found a parametric class which is 2-copy indistinguishable even under set. Even if you consider more stronger operation like separable superposition, there is a class where gamma is equal to pi by 6 and alpha beta satisfies this condition, sin 2 alpha by sin 2 beta, not equal to 3, neither equal to 3 or 1 by 3. In that case, they are indistinct, they cannot be distinguished even with a stronger operation like separable superoperator with 2 copies. That means in this case you may need 3 copies. So this construction is a bit complicated, and you can see the appendix of this paper that I showed. And result follows 1 and 2. Now, still, this non-adaptive scenario remains open. So, what may happen? It may happen that there are orthogonal sets which cannot be even discriminated using non-adaptive scenario. Then we will find the strongest non-local or a stronger non-locality. But if it is possible, I mean, if we 2-copy and using non-adaptive scenario, it is possible to distinguish among all possible scenarios. I mean, whatever orthogonal states you consider, to consider 2-copy, then they remain distinguishable under adaptive LOCC. Then this super additivity of locally acceptable is a phenomenon, because with adaptive LOCC, what you can find more assume non-adaptive scenario. So this is a clear example of superadditivity discussed in the paper by Zaid. So this is the message that you should take. A state of 2 cross 2 states with 3 parameters cannot be discriminated with just 2 copies under adaptive velocity. And of course, we have found a stronger parametric class, which even indistribuable, even if we use adaptive separable superoperation. And we have an example where you see that adaptive separable operation is more powerful than adaptive velocity. And using this thing, you can have a secret sharing protocol, which is secured under adaptive scheme. And of course, not adaptive scenario still remains. Yeah, Siddharth, I have finished.
Yeah, thank you very much, Guruda, for this wonderful talk. So the stage is open to the audience to ask your questions.
Guruda, I have a question.
Yeah.
So for adaptive scheme,
yeah,
there are examples, or you have a theorem actually that 3 copies are required. Okay.
yeah.
Now, is there any example that there are 3 copies are required for adaptive, but 2 copies are sufficient for non-adaptive scheme? Is there any example?
So for 2 copies, if you consider non-adaptive cases, then there is no example till now for which it will be impossible even with 2 copies.
Yes.
So I know people, they are searching for set of states for which 2 copies will be insufficient for
Non-adaptive scheme.
For non-adaptive scenario. But still,
there is
yeah,
still no example.
They have all, still people believe. I think Bennett believed that with 2 copies with non-adaptive scenario it will be always possible. But I know there are people who believe that we will have a counter example, but still we don't have.
Maybe it may happen partially for partially entangled state that 2 copies will not be enough for non-adaptive case also.
Especially Devari, I was thinking, if you look at this theorem, that if there are 3 copies, if there are exactly 3 entangled states for 2p with 4 states, so this is very asymmetric. Maybe with this set, 2 copies with 2 copies you may not be able if you adopt non-adaptive velocity. But I was asking Ramesh, they checked and they told that no, they are also it is possible with 2 copies.
Okay.
Are there any other questions? If there are no other questions, I have 2 minor questions, Guruda.
Yeah.
Do you think that the issue of tomographic locality will impact this issue of local distinguishability in some sense? Like when we consider real quantum mechanics versus, complex quantum mechanics, you lose tomographic locality. So do you think that will have impact this sort of your comments on?
Yeah, I think that this result may not have implication in this case because for real Hilbert space this tomographic locality does not hold, but it is not large number of states, and with large number of states you can identify the state by just local value. But if you consider real Hilbert space, this does not hold. But for complex Hilbert space, it does hold. I don't think that this is finite copy scenario. So maybe that question is different from this question.
Okay.
What your other question?
Yeah, so I was just thinking, so other, like you have now pointed out, for example, in the case of adaptive, local measurement, you have this nice case where you've pointed out that we need three copies, right, in order to, so that kind of provides an indirect or a kind of a oblique answer to Bennett's conjecture. But I think theirs was in a full arbitrary LOCC, and this is an adaptive LOCC.
Yeah.
So I was wondering, can one consider other ways of weakening the local measurement, the way that instead of considering a general LOCC, you considered an adaptive, local measurement. So can we think of other ways of weakening the measurement in an interesting and natural way to provide answers?
Yeah, I mean, so there it is adaptive, non-adaptive. Whether you can consider something in between.
Yeah, in between. Yeah, exactly. Exactly. Or any other ways of weakening the way that adaptive measurement is weakening what a local party can do.
Because this non-adaptive thing is very powerful. So
Correct.
maybe some other weakening. Adaptive is also weakening, but
Correct.
some other weakening.
Some other weakening.
That can be thought.
Okay, if there are no other questions, we will conclude this session by thanking Guruda once again for this wonderful talk. Thank you to Guruda. Thank you to the audience for being with us.
Yeah, thank you.
I thank Dr. Shrikant for his time to chair the session and speakers of this session for sharing their work with us. Now, this is a time for a tea break. I hope to see you all at our Academia Startup panel discussion after the tea break at 17:20 hours. Thank you.
Good evening. Am I audible?
Yes, you are audible.
Good evening, all. We are very excited to have second panel discussion of this conference. This panel discussion is about academia and startups. In this panel, we have Professor Pankaj Sethia from IIM Ahmedabad, Dr. Rahul Patil, Chief Growth Officer from QNU Labs, Mr. Ashutosh Kumar, Head of Engineering, Adaptive Computation from Kalishe Private Limited, Mr. Shob Mazumdar, Director and Founder, Felonius Private Limited. Now, I would like to thank Professor Sethia for taking this time to come in and to moderate the session. Professor Sethia is a professor and founding chair of the Center of Digital Transformation at IIM Ahmedabad. Studies how organization leverage IT applications and digital capabilities for superior organizational performance. Open source development and diffusion is another area of interest. He has been invited to give research talks and keynote speeches by universities from different countries, India, US, and Singapore. In general, he has traveled across the world for academic work. Let's now welcome Professor Sethia to start the academic startup panel discussion. Over to you, Professor Sethia.
All right. Thank you, Jyoti, and thanks for the introduction. Welcome, everyone, to the panel. Very delighted to be here and talking about this very interesting and upcoming topic on quantum information and computations. We are joined with a few panelists who are doing active work in this domain. So what I would do is I would start the session by asking them all to give a brief introduction, and then I would ask them to elaborate a bit on the specific applications that they think they are seeing as highly valuable, and we will go from there. So if we may take a very quick introduction from Rahul, Ashutosh, and Sawa, if you may go ahead and introduce yourself very quickly.
Yeah, good evening, sir. This is Shobhu Majumdar, and I represent my company, Apollonius Computational Business Solution. We are basically utilizing the quantum infrastructure of IBM, basically for the for the portfolio optimization. So that is one of the area we are basically focusing on. And as you know, that quantum technologies is yet to go along ahead of time. There is it's at this moment it's mostly at a research level, and everyone is exploring between the Adiabatic computing system and the different computer like T-Wave, IBM, so different kind of computation system. And the application wise, we have focused on the financial sector because we feel that India is a budding hub of financial activities, and India has got a huge potential to utilize and harness the capabilities of the quantum infrastructure. So keeping in mind of the thriving economy and the vision of our Honorable Prime Minister about the digital India, so India is going long ahead of time in thinking about the digital, how to digitalize the financial perspective of the country. So their quantum computing plays a very important role. So that's why we have kept in mind of that particular scenario. And we are doing our, the research, innovation, and our activities in that particular respect area. Yes, sir.
Very good. Thank you so much. Rahul, you want to go next?
Sure. Professor Sethia, it's an honor to be here with you. I am also, by the way, in Ahmedabad. Also, the company is located in Bangalore, so maybe I'll have an opportunity to meet you in person someday.
Sure.
So we are QNU Labs. Our name itself starts with Q, which is for quantum, and Nu, which is the smallest particle of light, which is photon. That's how our name came about. We have focused our energies on a specific application, so to speak, in quantum, which is security. So what we have created is a portfolio of products as well as solutions as well as services around quantum cryptography, quantum security, and then we are applying that to various industries, including BFSI. So while Saurabh says that quantum computers are yet to come. We have actually created products on security that are quantum enabled. So we can have a very good discussion around that. So thank you for this opportunity to IIT Jodhpur.
Sounds very good. We look forward to that. Ashutosh?
Yes. Good evening, Pankaj.
Hello.
First of all, I thank Subhashish ji and Dr. Narayanan from IIT Jodhpur for identifying and collaborating with us and then inviting us here. Because for 2 years, we have been conceiving the technology of quantum computation and how it will help us solve specific use cases in petroleum industry. And while we do this, there is a lot of scope for potential collaboration that will bring research from labs to the real world application. And on top of that, I know everyone here is talking about working on infrastructure hosted by certain companies. However, I will emphasize during my talk that there is a requirement for developing our own quantum computers. And this is the time where we begin. So, Pankaj, now on to you, and let's take this discussion forward with wonderful panelists such as Mr. Majumdar here and then Dr. Rahib. Over to you now.
Thank you so much for the brief introductions. I want to start with this. I think I liked your idea, Ashutosh, that the time is right. I do firmly believe. I know there are a lot of people listening here. I do firmly believe that there is no time. You should have started yesterday kind of logic should be there. So you're already late. I think in as far as innovation goes, the only way to excel is to do it yesterday. And so always live with the fact that you are late and just run as hard as you can because you're not going to catch up anyways. So just live with that fact. And this is not a hyperbole either. In our case, especially if we are in the Indian context and we're talking that, it is not a hyperbole. We are late. There are countries who are ahead of us. And so it is not even an exaggeration. This exaggeration or this hyperbole is even followed by countries that are leaders. And we certainly are not there yet, to be realistic. But I think if we continue to do what we are doing and do it with urgency, we should be there. And I'm thankful that we're having this conversation with that intention. Just to start, I think we will come to applications later. But I want to build a little bit more on this idea of quantum infrastructure. And Ashutosh, you said quantum computers, and Sovia is mentioning quantum infrastructure. I want to talk a little bit about, if you may define how this quantum, one of the things is we shouldn't get into jargons and things. So how is quantum infrastructure going to be a step over the digital infrastructure, right? So digital we already have, quantum we'll likely have, or we have it in a very nascent manner. Very crisply, what are the things that will make quantum infrastructure better than the digital infrastructure? I want you to answer that a little bit in terms of what your views are. And maybe that's an opportunity for India that we can leap scale digital to go directly quantum if we identify what are the things that are really going to be great there.
Yes, let's start with the story here. And I will make this story relevant to the oil and gas industry. And as and when things are required for as an explanation, I will provide it, because I understand that here we have researchers, and then when I start talking about subsurface and hydrocarbon reserves, at times it will become very difficult. So back in 19th century, there was a system designed to filter water supply for France that was designed by Darcy, who took a tube, filled it with sand, and passed the water. And then at other end, we got filtered water. And then this principle built the foundation for modeling the phenomena in a reservoir. Well, before I move ahead, reservoir is like 3,000 feet, 3,000 meters under your feet. And we drill through multiple layers that consist of different rocks or beds, sediments. And we intend to reach that rock, or rather the thick rock, wherein hydrocarbon is present in the pores. And till today, the Darcy law had it had been doing justice, and it had been helping the researchers to model the flow of hydrocarbons there. But recently what has happened is unconventional reservoirs has come up, wherein when we have the small chain hydrocarbons, they intend to flow through those pores. However, the long chain hydrocarbons, they remain stuck there. And here, the pore that we are talking about, they are nanoscale pores. So everyone is thinking about what is the best way to model the subsurface. Because unless we are able to model the subsurface, how do we go about placing the oil wells? Now, again, let us emphasize that it is important to place the oil wells so that initially we can harness the pressure that is built in the subsurface. Because if, like fundamental physics, if there is pressure, hydrocarbon will be pushed up, and it will be economically it will be quite economically beneficial. So now, in case of the unconventional reservoirs, Darcy law breaks. So what do we do now? So we take a step backward from reservoir models. We try to model the nanopores, the molecule of water, gas, and hydrocarbon, and the surface of the rocks present there. And for modeling this, classical computers fail. Or even if they do not fail, what's the point in devising a method that is not sustainable? Because at the end of the day, we are talking about research and application that should be sustainable. Because we need to, it's quite simple mathematics that if we are putting in some money, it need to have some economical benefits. Now, if we are able to model that correctly, then we will be able to place a well there in the unconventional reservoir in a more profitable way. And the calculations say that if we are able to reduce the number of wells by 10% per well, the gain that we will make is around 6 million USD. And okay, I will make one more point here. It costs around 10 to 20 millions to develop a quantum computer. So right here, we are talking about a sustainable business model. Now, over to you, Mr. Pankaj.
Let me summarize this, and I'll go to solve a little bit later. I think what you're saying is that compared to the normal digital computers, efficiency it is much more with a quantum computer, which means that they are able to do the same task at a cheaper cost. If that is the assumption, or if that is the one factor, I think that you're saying, then startups, because we're talking in the context of startups here and new organizations looking at quantum computing as a business model or aspects of it, one thing that they can think of is the gains in efficiency in computation or computational efficiency. That seems to be one aspect that you have identified, Ashutosh. I want to go back to Sova a little bit and see what, because they're into the idea of quantum infrastructure as well. What do you see as a reason to think about quantum infrastructure as being superior to the normal current digital infrastructure?
Yeah, actually, I truly agree with Ashutosh, what he has actually just now said. It is a computational, computational excellency. So compared to there are certain models in case of our scenario, I'm just explaining, optimization problem. There are certain optimization problem which are intractable in nature. So even the supercomputers are unable to solve those kind of problems when the complexity of the problems, the number of variables increases. So those problems, what we generally say is that it's an intractable kind of problem or NP-hard kind of problem. So those problems are categorized like that. But quantum computing has given us a hope, as a light that, okay, this kind of problems can be solved. It is not only with respect to the financial problems, but again with the supply chain, logistics, aviation industry. So there are a number of industries which uses this kind of a, the non-polar, the NP-hard kind of problems, and those problems, if the quantum computers can solve those problems, we can actually have a real benefit. And again, it will turn out to be more beneficial for the organizations. to churn out the profit out of it. And that's why more the top-notch financial companies across the globe, they're trying to harness, they're trying to understand and leverage the power of quantum computation. Even the aviation sector, the service sector, they're also now coming into and trying to understand how the capabilities, as you said, the digital transformation. Yes, digital transformation is not only with respect to, only a single technological transformation, but a digital transformation is a holistic transformation, where we have to understand how we can enhance the computational power. We are talking of artificial intelligence. We are now, most of us are now discussing of the deep learning. We are thinking about the hyper artificial intelligence and the strong artificial intelligence. But artificial intelligence, the true power of artificial intelligence can only be harnessed when we have a matching computational capacity. So that's why most of the organizations, they are trying to build up this infrastructure, try to find out that, yes, what kind of solution, what kind of business solutions can be solved. So their quantum computers really play a very important role. And as one of my other panelist member, he has rightly said that, yes, India also should look into developing its own infrastructure. But here I have a different opinion. I just say that it's always better, since, as you have said, that we are already late. So it's always better that whatever we have developed. So try to explore that, try to build based on that. So it's just like build or buy kind of scenario. So it's a kind of a decision which an organization needs to make, that whether we should build every parts by ourselves, or we should actually get some of the things who are expert in that, maybe they develop, and we make the top of models based on that. So that is the philosophy we are actually adapting. Yeah, over to you, Professor.
That's a good point. I think that's a good point about build versus buy. I want to go back to Rahil a little bit. Rahil, you are building infrastructure in security and cryptography and others. And we are hearing here that we may not build everything in quantum. So what is the quantum infrastructure all about? What are the different parts of it that would be required for a large scale organization? Let's say hypothetically, if if some people who are listening here start to build a startup which will create quantum infrastructure, and they want to be the full-scale solution provider for it, what are the different parts of the infrastructure that such a company would have to master and build? Security and would be one for sure, but what are the other components, including security also, if you may want to talk about that?
Yeah. So I think this is a very evolving field. There's a lot of research going on. Not all things have been figured out yet, so the opportunities are endless. So I'll start there. In terms of what needs to be figured out, I think there are two things that are coming to bear, right? One is there's so many transistors you can put on a single chip as we try to produce in the traditional, or what we call classical computing, right? We follow the Moore's law. There's a certain limitation coming to bear, which we all think is coming very soon, right? So the logical next step is to evolve that understanding of computation, right? And what we feel, or what the industry feels, or what the world feels, is that bringing quantum into the state would drastically remove that barrier, and it has been researched quite well and proven that quantum computers will be good at doing a lot of things that we potentially cannot do today with the combined computational power that exists all over the world, right? So even if you put all the supercomputers and all the computers together, we would still not be able to solve certain problems. And primarily, we feel that a 1,000-qubit quantum computer will significantly change the landscape of our understanding in various industries, including finance, including for drug discovery, including astronomy, so on and so forth, right? So from a infrastructure perspective, I think now you can imagine if you're building a net new computer from ground up, what all things you would require, right? So starting all the way from the processor itself, to the memory, to the storage, to the cooling, to the power, to the algorithms that actually do the communications, to the interfaces that enable exchange of data. All these are areas where there's tremendous opportunities that exist. So I agree with Saurabh when he says that build versus buy, but I think even buying may not have all the answers today. There's a lot of building that's still required. And that, I think, in my opinion, in my personal opinion, is a very drastic and very, I would say, paradigm shift of an opportunity that exists for India. And since we're talking to folks in IIT, I think this is where if we as a country scale to the or take up the challenge, I think we can bring up the golden days back to India. So so in summary, I think Professor Setia, there's tremendous opportunities across the board in terms of research, in terms of creation of ancillary as well as primary requirements of quantum computing, and security is just one small portion that we have started to work on. And to kind of give a little bit more color, even when we are producing things, we are still reliant on certain things that are not available in India today. So so we have to import some of the things across geographies in Europe, in US, and so on and so forth. And therein again lies the opportunity that if those capabilities are brought on back home, not only the cost will go down from 6 million to maybe 3 million, because we are very efficient that way, right? Indians are very efficient that way. But I think it will create a complete ecosystem that will give birth to new things beyond just computation in quantum arena for many more young budding graduates coming out of IITs. I think that is my sort of take on it. So,
no, I think that's very interesting. That's very interesting. There is severe chip shortage going on right now as we talk, and US is actually the government has intervened that they're going to fix it by building capacity within the states. So that's a very pertinent topic, I think. And if you enhance the computations, obviously the shortage will be less. There has been an adverse impact on India. Automobile, especially sector, has had to reduce the supply, which means the production has been hit because of the chip shortages. The question that I would have is for all of you is, what are the areas that you think, because you mentioned build versus buy, and Rahul, you mentioned a lot of import going on as well. I'm not going to target anyone, maybe all three of you can suggest what are the key bottlenecks that you see for India going in future. There is always research and there is always need for doing more. Work will always be a bottleneck, but not bottleneck, but more you work, the more you get kind of logic. But what is the bottleneck in terms of external lines and the kind of components that you think may hamper the growth of quantum in India?
Okay, I will take on. I would like to continue with Pankajji.
Anyone can.
Okay. I will go back to history for a while. Let's go back to 1980s. That was the time when India was seeking foreign alliances for supercomputers. And the foreign alliances, they had their own assumptions. As a result, India decided to build its own supercomputer. They built it. That was second fastest supercomputer in the world and at a cheaper price. So when it comes to pricing, we have proved multiple times, like Mission of Mars, that we can do it at a cheaper price. However,
Ashutosh, let me stop you there. I think price, because I come after a long stay in US of about 17 years, price is something that I'm not usually very excited about, because when we say lower price, it means we are paying our engineers less money. I get a little bit offended with that because I think our engineers are top class. And if anything, they should be paid more at par with others. So price is a tricky, slippery slope argument. I know we get very happy that we are cheaper and all that. I sometimes take it with a pinch of salt. We are, the price here is largely salaries of talent that adds value or that creates products costly in US because they pay their engineers quite a bit. I think we should be a little bit more proud of our engineers. I am very proud. I always went to you. I mean, like I said, I stayed in US for 17 years, and I always felt that our engineers were at par, if not better. In fact, they are better in all ways. And I would be very happy if we create the best, the fastest, the quickest technologies. If they are more expensive, so be it. I think it is a respect to our engineers to do that. I know it's kind of against the grain of what we think mostly as Indians, but I think someday I think we want to be. I would not mind our products being expensive if they are indeed world class and better than anything else produced elsewhere, which I think we still are very close to already. But sorry to that.
Yeah, I do agree with Pankaj here. How I intended to talk about the efficiency part, and I missed that, and I didn't consider the human resource part. But I do take your point, Pankaj here. Now, as we talk about certain applications, let that application be in case of DRDO or as in case of natural resources, we do have to rely on our computation for reasons that are known to everyone. Secondly, like Rahul ji has said, that currently, let's talk about the scenario of hardware versus software. We know that today we are dominant in software as a country. How about if the quantum ecosystem is beginning to come into existence today as an economy? Then if we focus on infrastructure as well as the algorithm, it will build the market for the quantum hardware, as let's call it for the time, because it's not yet clearly defined what actually is quantum hardware. And if we have that quantum hardware, it will help us to retain the talent, and it will have a sustainable model for the talented people as well, so that once they come out of the research labs, there is an ecosystem that will sustain them. Okay, I can go on with the next use case. However, Pankaj, with your permission, should I continue or should I pass on?
Go ahead.
Okay, yeah. Now, when in my last discussion that I had, Pankaj rightly captured the aspect of efficient computation. Let's talk about the molecular scale of things there. Because currently, quantum has all the potentials in drug discovery, chemical reactions, because we can model the molecular level bonding and molecular level chemistry there. And here I am looking at our own industry, that is the petroleum industry. As I mentioned, once we drill a well, there is natural pressure with which the hydrocarbon comes up. Once that natural pressure dies, as is the case, because in hand pumps also, if some of us in the audience have seen, we need to create some sort of artificial pressure and the water comes up. So even after that artificial pressure has died, for case of oil well, there comes the injection process, wherein we have the hydrocarbon here, and this is the well that needs to produce. So what we do, we place another injector well and pump some liquid so that the liquid will push the hydrocarbon and we are able to produce it. Now, on the molecular level, there are two aspects. One, the molecular level. Second, the economic aspects. So first, let's talk about the molecular level, where we want to reduce the viscosity of hydrocarbon by, again, looking at the bonding with the rocks inside it. And we require an optimum surfactant or chemical that should be present there. So before I jump into the quantum wall, what do we do currently? Now, this analysis of identifying a surfactant and then pumping it inside the reservoir, it takes a time period of around 15 to 20 years. Now, think of the situation if we are able to model the the molecular interaction and identify the perfect chemical for that is cheap, but at the same time that helps us produce hydrocarbon. So this is called as chemical recovery. Now, okay, since I have given two use cases, what is it in for the academic institutions? Now, let us say that I have talked about all of this, and academic institutions, if they collaborate with an organization who have the existing solutions and they are willing to create a quantum counterpart, it will be a win-win situation for them. That is, they can come in, develop their solution, and do the profiling. That what is the benefit that we have from that quantum, the quantum solution in the quantum ecosystem, right? And this is where academia comes in. And now we are, I think, hitting right at the panel discussion topic, that is academia startup collaboration. So therein, now again, I think after I complete my discussion, there will be a lot of questions arising here. So Pankajji, please pay attention to the questions, because I will go ahead and say that, like I approached Subhashish ji and Dr. Narayanan here for collaboration on institute level, that's quite possible. But how about the students who are thinking about the sustainability if they pursue the quantum computation or technology that will be built in the quantum ecosystem? So for them, I'd like to say, why don't you contact us? We are here. Okay. Okay. Now let me take another example. The example that lies in fundamental physics. I talked about the 3,000 or 5,000 meters of depth under my feet. Now, how do we, that is petroleum engineers, identify what lies in that region, that is between my feet and the reservoir? What they do is they have an equipment that produces vibrations, and there is a grid of receiver on the surface at a pre-decided distance that records that sound. And once we record that sound, currently we adhere to a process of binning, where, okay, of course I will not go into binning, but they rely on concept of the ray, the Fermat's principle, wherein we treat them as rays traveling. However, let's ask this question, that should we really treat that as ray? And where does that hope lie? The hope lies right here in the quantum ecosystem, wherein if we have a source of vibrations, then depending on the weighted probability, how is it being recorded by the receivers on the top, right? And then from there comes the seismic imaging part. An entire ecosystem has a potential to shift towards quantum processing. So now, since I have given this philosophical analogy, how do we validate and how do I go ahead and collaborate with the researchers here? So so what we can do as an organization is we can provide with them, like I said, with the existing solutions, and then let them build the solution in the quantum ecosystem, and from there on we can go on brainstorming and identifying better solutions. Now, Pankajji, I think I have taken quite time of the panel. I will pass on the mic to others. Thank you.
Yeah, no, that's interesting, but I want to see what others have to say on this topic as well. What is it that we should be focusing on to enhance India's dominance in the quantum infrastructure? What are the bottlenecks? What are the opportunities? Maybe others can have other comments on it. I'll hold my comments on Ashutosh's thing and probably say it after.
Here, I would like to focus on just emphasizing on what Ashutosh ji said. What I believe is that prima facie, India requires a pool of young, talented, and skilled quantum efficient engineers. So what I mean to say is that is a set of engineers. Maybe it is a kind of a culture. It is a kind of a kind of an ecosystem we need to build up with the thematic discussion, panel discussion, that is a startup industry and academia collaboration. So there needs a kind of courses on various modules. I know some of the courses have already been launched on NPTEL and other platforms, but there is a holistic research, collaboration, and a brainstorming kind of sessions and workshops needs to be organized by the various institutes at a different level, where more and more students can be trained. There may be undergrad students who are the fresh minds, they have fresh ideas, enthusiastic, highly potential. There needs to be students from the postgraduates to the doctoral scholars who are already doing their research. So those kind of ecosystem needs to build up on the different areas at an infrastructure level as well as at an application level. So maybe a group of researchers, students who can work in the infrastructure level, a group of students and the researcher, they need to work on the application level. As already Rahil ji said that they're working on the area of the security part. Ashutosh ji is working on the applications of the oil. So there are several areas, and there are many more areas where we can find, like healthcare. Healthcare is another area where quantum can have an immense potential to explore. So we don't know at this moment that what kind of potentials might be there, but yes, whenever we have a superior computational power in our hand, that is the possibilities are endless. So it is only the brain, the young brains, who can actually think. So there needs to be maybe any hub, a kind of a centralized research hub, where the different startups can come up, they can share their ideas, students can enroll, internships programs can be launched with a very specific focus on different applications. The MBA students, the financial people, the marketing people, the HR people, everyone can participate and they can share their ideas. When we have a bunch of ideas from the different industry, from the different academic institutions and students, and holistically, that idea, some of the ideas can be developed, and that will leverage to a superiority. Because we know that in the West, how it happened, because all the technologies is just because of collaboration. The students, the industry, the academia, the researcher, they all work together towards a singularity goal, and that's why they have achieved that goal. So it is the time when India also should, because like nowadays it's become much easier to collaborate, to coordinate due to this virtualization and the online session. We all are sitting at different places, but it's sharing our ideas. So it's much more easy. We don't have to travel a long way around the country to discuss, to assimilate the ideas. So that is how we need to focus on. And there, I think the different academic institutions and startups and big industries, the mother industries can collaborate, and that will drive the quantum revolution. What is basically, I think, the idea, the quantum revolution India should bring forth. Yes, sir.
Thank you, Sobaji. Rahil, you want to add to the discussion on what India needs to do, especially the academia and startup coordination or collaboration. What are the factors, even beyond that, what are the factors that might become bottleneck, or what are the factors that will give an advantage to India in this new era?
Yeah, so I think India has a very good education system that has played a very good role in terms of producing good talent, right? But that talent ultimately ends up working for companies outside of India, right? So I think this now has created an opportunity to, because the ecosystem, while yes, there is a little bit of better ecosystem outside of India, but I think we are in a position now to reverse that trend and create a very good ecosystem here, because the basis of quantum physics is based on just two fundamental things which are very strong in India, which is mathematics and physics. And I think we have very good talent available there, right? So from an opportunity perspective, okay, we may not have the fabs, we may not have the manufacturing scale of, let's say, a Taiwan or somebody else, but we do have the talent to produce intellectual property. So why not focus on our strengths, right? I think if we are able to produce a lot of research work, if we are able to publish a lot of papers, a lot of patents around various categories of quantum research, then that will inherently bring the attention of the world to produce, to make things here, and I think we will get benefited enormously, right? Secondly, as I think Ashutosh also mentioned that we may not have the the capability of creating hardware today, and we have much more experience in software. So why not again play on that strength and create models or algorithms that are quantum ready, right, or quantum feasible, right? I would say not ready but feasible, right? So I think again a lot of opportunity lies in academia itself to create such forums for students. And then again, obviously the ecosystem for startups is already there. And the best thing that I can actually say that has seen a drastic change in India is specifically that now there is actually a quantum mission, right? The country has actually identified that there is a need for this. So at a policy level, it has been supported. At a financial level, it has been supported. So if you have a very great, unique idea that you want, that you want to execute, there are now funds available to students, to academia to kind of pursue it. What needs to change? I think the bottleneck, right? So these are all the great opportunities that exist in front of us. The bottlenecks today, in my opinion, Professor Setia, is that there's a lot of I would say on paper research, right, that never get ended. I think we have to get out of it. I think as a country, and it's not a stab at any particular institution or a particular organization, but rather country as a whole. I think we need to get out of it. We need to have industry relevant, problem relevant research done, executed, and then potentially hand it over to young entrepreneurs like Ashutosh and others to solve the problems, the large problems that they are trying to tackle, right? So I think it's now, imagine if we create this ecosystem or we create this pipeline, then imagine the impact it will create on all industries. Forget just one, right? We are here from various industries, and we still have some ramifications by quantum coming to bear. Now imagine if we are able to extend that to everything that we do today, including healthcare, to government, to defense, to to banking, to what have you, right? I mean, so I think that is the ecosystem that we need to produce by removing this bottleneck. And I think we have, as I said, we have the platform, we have the capability, we have the policy support. It's just a matter of taking this more seriously than just another project that we typically take and never finish. So I think that's my view on this.
I think these are excellent points, and I heard some very good comments, and I'll try to summarize, and you can comment if I'm not getting it right. I think what I heard, especially when Ashutosh was talking about finding business models and finding places where we can, he was explaining one particular case in petroleum, but there are many such cases that would arise. And that makes me think a lot of it is around what we started the discussion with, around computational efficiency. There are certain places that will gain more from it. There's a 15-20 year timeline in solving a problem, and you can compress that time to a much shorter range. There's a lot of gains to have. And I think it's those big ticket computational efficiency items. And so I see actually, and I know we talked about the quantum efficient engineers, etc., that we were mentioning, but I think there is equally a scope in that case of combining the business talent and the technology talent, because when you talk about the gains due to efficiency, that's a lot what the business people will like to identify. What are the big areas? What are the big domains where things can be solved rather quickly? What are the places where disruption, quote unquote, can happen? Things of that nature, I think, which are largely the focus in a business school, I think should become center stage. How to create business models around the places where technical efficiency may be very apparent with the quantum computing. I think that is probably going to be one of the key factors for success, as I hear you all speak on that. I also want to highlight the comment about collaboration between university and industry, and I think Rahil last said about applied research and not theoretical. I think to some extent academia has a very unique way it works. I've often been questioned by some students, largely these days, PhD students, also swayed by the growth in modern technologies, be it the social media and so on and so forth, excites them a lot, and they kind of try to find practical relevance on that. I'm going to tread that path carefully because I'm speaking to industry here, but when I speak to my PhD students, I often give them an example that the power of academic research is the theoretical research. And by that, what I mean is work done in 50s and 60s on electron is the reason why you go online and put a message on Facebook today. So don't underestimate the power of long-term theoretical research, because what it creates is unique. We're talking about quantum computing today because people were really excited about quantum mechanics and quantum physics and everything else. They did not care what efficiency will be. They were excited about the fact that it can be done, or there is a science. There's a beauty to science, which is theoretical. Now, let me switch the gear there. It is not just the theoretical research that academia does. I am speaking to you here. I've recently come, like I said, to India, and we've started a center for digital transformation. I have on my center leading industrialists. Nandan Nilekani, there is NASSCOM President Devjani Ghosh. There are academics from US. There are people. There's TCS head Rajesh Gopinathan. I can continue to take names on that, and it will never end. The point is, industry relevant work happens in academia as well. I think there are different places for these two, and probably there is a need to balance the two. I'm even stretching it further to say there should be a technology and management joint collaboration if you're talking about quantum computing. I'll be happy to explore questions. I have hired the person who's running my lab is from IIT Delhi, or the person who's running my center, I've hired him from IIT Delhi. I hire people, engineers, and I hire people from everywhere. Point is, I see digital transformation as a much bigger than a management or a technology domain. And I think if we have to do anything meaningful, it should be treated as a much bigger effort that can transform countries, and not just organizations, but countries. And that's where our passion lies. Theoretical research is necessary, but so is applied research. And I think academia will have to probably take that into account as we go forward as well. I think I want to, I can say a couple more things, but I think I want to hear, and I think most people here would like to hear from you. What are the 3 areas that you think, people who are listening here, we're talking about startups and others, and people here are mostly in the institute and academia. What are the 3 areas that you think will be the first ones? And you may differ. I know each of you might have a different assessment of it. What are the 3 areas where startups are likely to be most successful in this new quantum ecosystem that is emerging? And it could be in the building of that ecosystem as well, not just using it in application.
Okay, Pankaj, I will take it first, if I may. So, sure. 2 days ago, when I was listening to the industry and academia panel, there was a question that was put forward, that is, the government has their policy, the academia, they have their role, the way they work. Now, even though the government has initiated organizations and let's say organizational structure like TIH, Technology Innovation Hub, there somehow the synergy, it's hard to find the synergy. So now, what startups can do there? Now, startups come in between them. Or one of the roles that we can play among the many that we do is we can come in between, because we are agile, we have energy, and we have the time that we can devote. Let's say today, as of 2021, I am here. I have 40 years ahead of me. If I take on this quantum mission, I can devote 40 years, 12 hours a day. That's the commitment that we can give. And since we have this commitment, now it's upon us to make things right if we make this commitment. So this is one of the areas where we can put our where we can build our credibility and the role we can play. Now, okay, that's not really very far-fetched. What we currently do is we have our mentors from industry, like Pankaj here rightly said. Like he has a lot of members in his organization. We have mentors from industry who have seen the business aspect, the technology aspect, and the human resource aspect. We brainstorm with them and we identify the problem statement, like the ones, some of them I discussed. Once we have that problem statement, we approach the researchers so that, okay, we do allow the pure theoretical scientists to carry on the research who are pure science based and who are entirely theoretical. However, those who are in applied domain, now, I would like to put an analogy that do we come with in our defined problem statements that is sustainable, or do we allow the applied researchers to work on the same problem for times immemorial? Because like Rahil ji here said, there are research that starts from the page and ends on the page, and 6 years of time and a lot of money has been consumed. And similar aspects are there for the courses that are being designed. I strongly believe in the education system that we have, and however, there has been certain courses that has come up. Since we touched upon the domain of AI, we all believe and we know that not all the courses are of the quality that is required. Though they have on papers a lot of commitments and they vouch a lot of things. So what we can do, or what rather academia can do here, since this is the initial time, they can collaborate with certain organizations who are working on applied aspect of things. And then there is people from that particular industry or the organization who are working on applied things and who know the business model. Of course, business model is just for sustainability, but they know the application part. There comes one of the researchers from institutions. Now they work together and define a course so that it is aligned with the day-to-day work with the researcher as well. And at the same time, it is aligned with the agenda of that particular organization as well. How does that sound? So this is, I think this is another point wherein startups can come in and they can work towards this startup and academia collaboration.
Ashutosh, if in the interest of time, I mean, the administration of university will be done by university largely. I think that freedom is somehow the reason why we are not a dictatorial country yet. So I think the academic freedom, I don't think is ever negotiable, and we probably would own that. But I think what might be good to talk about is what are the areas, the 3 areas that you think these, the startups you think are likely to be the most successful. The startups are likely to be the most needed. Petroleum, probably, I'm sure you are very excited and you see the potential there because you are very into it. Are there some other areas that you see are going to be really very interesting for some of the young guys who are listening here? Might be thinking about ideas. Who knows? Tomorrow's Infosys or Tesla might come from one of the people here in the room. So, would you suggest something that is very appropriate to work on for people listening?
Okay. Here, one question that I ponder is: should I give the philosophical aspect, or should I point to use cases in other industries other than petroleum industry?
In the interest of time, we might have to go quickly, and so I think we are ending in 6 minutes, and I want to see
So
quickly, whatever you want to do.
What I say is: be committed, be determined, and pick up problem statements, the unique problem statement for which you can devote your entire lifetime, because your life is unique, and you want to make it worth the time that you spend on the earth. With this, I will conclude, and all of you can approach me after this panel as well.
Yeah. I'm sure you are around, and people. I think you can write questions as well in the interest of time. Anybody who has I'll try and quickly take them. But So and Rahil, any 3 areas that you think will be most productive for the people listening here to think about in whatever capacity they want to engage with quantum computing?
Yeah, my take in a very summarized way, I must say that one is the finance that has got a huge potential of success, and students can involve in various areas of finance, not only the portfolio optimization, risk profiling, another area where people can actually invest and do a real good research. Even students from the business schools, they can do research on the risk management. The second area of quantum application, which I believe would have a lot of impact, is in the telecommunication sector. Telecommunication sector will have a lot of impact of quantum computational application. And thirdly, obviously, healthcare can be explored. Healthcare will have a lot of, mostly the data management and analyzing the, the disease propagation, because at this moment we are undergoing a pandemic. So maybe in future we might face this kind of situation, but we must be prepared beforehand. We should not be like this. We cannot afford to lose 2 years of valuable time. So we must be prepared, because this may be an ongoing process. We might face it again in the next 10 years or 15 years. Who knows, we face it. But quantum computer, with the lot of data which has been derived, we know like every country is now having a lot of data, the health data. So people's health, various, the parametric data are available with every country. So this data should not be wasted. We should develop models, those artificial intelligence based models, machine learning based models to design the healthcare system, and to design the system for the enormous data a country is having, like India is having an enormous data now they are having. So that requires a computational power, and that computational power is basically the quantum computational power. So quantum computational power, with the data already India and countries are having, we can develop a holistic model which basically is going to prevent us from this kind of catastrophic scenario that is actually the entire globe is undergoing. So that is another.
Very well said. Very well said. I think very well said, and you're rightly pointing the urgency, because this may not be the last pandemic we see, or many of the people here see in their lifetime. I mean, who knows the kind of things that are happening? And I think some leaders a few years ago had mentioned that the risk from pandemics is likely to be more. And so, who knows what we are looking at in future, and hopefully we don't repeat what happened here in terms of being prepared. Nobody was prepared in the world right now, but I think we probably going forward should be much better prepared to deal with such situations. So very well said, I think, on that. And Rahil, any thoughts on the 3 areas that you think will be?
Sure. So I think energy is one. I think that is a global need, clean energy in particular, right? So I think there's a huge potential there for any students looking at a lifetime of excitement, along with obviously the quantum research, right? Then I think energy follows by obviously the climate change, right, that we are addressing. So how we actually go about addressing the forecasting that is required to sustain life on this planet, right? So again, a huge challenge, but again, quantum ready challenge, I would say. So I think that is another area that people can focus, and these are very large areas. So even niches within this area can have a huge impact of what comes out. And then lastly, but I think that's been mentioned across the board, is I think at a molecular and drug discovery, I think is probably the largest area that I see for a country edge use as ours, with a dense population. I think we have to be better prepared, better ready, better forecasted in terms of what may come, right? We haven't even categorized potentially half of the viruses that exist in the animal world. Isn't that something that we should take on before we find out again with a new pandemic, right? So I think these are very 3 large areas that pose huge amount of potential for the student, for the industry to take on. And what we do is probably the easy one. So security is probably easy one, cyber security is easy one, financial data chunking and modeling is probably the easy one, compared to this larger challenges that we have in front of us. So I think in the interest of time, I'll stop here.
I think this is excellent. I really appreciate all 3 of you sharing the thoughts. One last thing I would say, Rahil, Ashutosh, and Sova have, I think, given an excellent introduction and an excellent basis for you to think about either philosophically or specifically to the various areas and the bottlenecks and the areas. One thing I would say, what I've heard, and I hope people here listening follow, the next few years, especially of your work life, would largely be where a lot of exciting value will be created by research. By research, the types of some of the examples that were discussed here, whether it's about hydrocarbon search, pharmaceutical, drug discovery, health solutions, so many other things that would, and computational power, or the efficient computations, will be the key to success, from what I hear. So if you're a student, or if you are a young person thinking about where to go, just keep these 2 things in mind when you're thinking quantum computations. Think about research. Think about the way, the problem-solving abilities. where and how are you going to focus on that? What are the type of problems that excite you? I think Ashutosh said it well. Where is it that you will spend the next 40 years of your life being excited and being, driven to come to office every morning and just strike on that problem again and again? When you fail many times, just strike it again because you just love to find a solution. Success comes much later, but I think the passion comes much before success. And so I think find that. I think Ashutosh has rightly summarized it and combine it with the computational efficiency and tremendous research. I don't see many questions here on the chat, but I think that probably is because you've been explaining things very clearly and lucidly. I'm pretty sure the panelists are open for questions even after. If you come up with any and would like to reach out, and if there is nothing else, unless I'm missing something, and then the host can tell me otherwise. But unless there is anything else, Jyoti, are we good to close or anything?
Yes, sir.
Pankaj,
Thank you again.
I see 3 questions here. They're saying
questions.
An old one.
Okay. Thanks.
Sorry,
Thank
I
you.
don't see any. Thank you so much again, Ashutosh and Rahil and Soa. And again, it was very nice interacting with you. Thank you, Jyoti, and I hope everyone benefited. And please stay in touch if you would have questions. I'm sure all panelists would welcome them.
I just would like to take this opportunity and thank you, Professor Setia, for moderating. I think the questions are important, so as the answers. So, but the questions are more important. So, thank you for challenging us with the right questions.
Thank you so much.
Thank you very much, IIT Jodhpur, for conducting such a interesting panel discussion, because a lot of ideas have been generated, and it's a good way of interacting with a lot of quantum enthusiasts. And thank you, Professor Setia, for giving us this opportunity and asking the questions which are really relevant. So, so this is a great platform to interact with all of you. And I'm open to take questions from yours, the enthusiasts in future also. Maybe this collaboration should go a long way ahead. This is just a beginning. I must say this is just a stepping stone, but we must work together for a better quantum India, quantum enabled India. So thank you very much from my side. And Ashutosh ji, yeah.
Okay. Now, Pankaj ji, Rahil ji, and Soa ji, I look forward to sharing the panel somewhere in future. And at the same time, I thank Subhashish ji and Dr. Narayana, and I would like to come back to IIT Jodhpur and have interaction with the wonderful students and researchers here. Thank you for your time.
Yes, absolutely. We would like to meet. Sometime we should have this physical conference, so that we can meet face to face, have more interaction with the brightest mind of India.
Yeah. This is Narayan from IIT Jodhpur. IIT Jodhpur will host all the panelists, including Professor Setia, moderator. Once the pandemic is over, we are free to travel. And I thank everyone who participated. And it's really a good opportunity on this, especially this kind of interaction. And hopefully, we will have much more deliberations in the similar directions to take it forward. Yeah. I thank everyone. Yeah. Thank you.
Thank you very much.
Thank you, Dr. Narayan.
This was a really wonderful discussion. I thank Professor Setia for moderating the discussion, and Dr. Patel, Mr. Kumar, and Mr. Mazumdar for sharing their views and experience. Thank you, sir. Now, for the third session of day 4, Dr. Guru Prasad Kar will be chairing the session. With that, I would like to call Dr. Kar to start the session.
Shall I start the session?
Yes, sir.
So this is the session 3, and this is the last session actually. There are 2 speakers in this session, Professor Fabrizio Piacentini and Professor Apurvo Patel. First talk by Fabrizio Piacentini. He's from Torino. And Professor Piacentini obtained both his master's degree and PhD in physics. And since 2008, he has been conducting his research activity in the optics, now called quantum metrology and nanoscience, which is a division of IEM since 2016. And now he is the permanent researcher. His research fields cover experimental optics, which is very important for quantum information theory, and also quantum information and metrology, and also some foundational aspects. It is related also with quantum technologies, and he also participated in many Italian and European research projects. So he is going to speak on temporal teleportation with pseudo-density operators, how dynamics emerges from temporal entanglement. I request Professor Piacentini to start his talk.
Okay. Thanks, Professor Guru Prajat Kar, for your nice introduction, and thanks to the organizers for giving me the chance to speak at this very intriguing conference. And the title of my talk, I will try to share my screen now. Okay. I will just choose this one. Can you see my screen? Which one? Okay, this is not the one.
It is not full screen, I think.
But yeah, I will just move to another one. Okay. 1 second.
Yeah.
Okay, this is the good one.
Yeah.
Thank you for your patience. The title is slightly different, but in the sense that it includes also the previous topic, but together with another one. And I will talk about pseudo-density operators and how to exploit them from open time-like curves modeling to quantum dynamics via temporal teleportation. Okay. This is the outline of my talk. I will present a generalization of the density matrix concept called the pseudo-density operator by Professor Vlatko and co-workers. Afterwards, I will show you one of the scenarios in which pseudo-density matrix or pseudo-density operator can, let's say, perform better than pseudo-density usual density matrix in modeling the quantum system. It is the case of an open time-like curve with an entangled pair entering it. I mean, open time-like curves are a special case of time travel in which one object travels back in time without interacting with itself, compared with a closed time-like curve that includes this interaction. Then I will show you that it can be this scenario in terms of correlations can have an analogy with a qubit model of an evaporating black hole, and can also solve, in a sense, the information loss paradox in an evaporating static black hole. And then I will show you how quantum dynamics can be recovered in this pseudo-density operator framework as a temporal teleportation from a series of temporal teleportations in different time instants. And I will then give you some concluding remarks and just my greetings. Okay, let's move on. Let's move on the first part. It is the introduction of this pseudo-density operator. You all know what density matrices are. The density matrix of quantum states contain all the information, all the correlations of the state at a precise time instant t. And that does mean that it does not include any information on temporal correlations. Temporal correlations are not included in density matrix, in the density matrix formalism. Then Fitzsimons, Jones, and Vedral tried to, let's say, extend the very concept of pseudo-density operator by saying of density matrix by replacing it with a pseudo-density operator that not only incorporates all the information included in the density matrix, but also includes temporal correlations. Not only that, but temporal and spatial correlations are treated on an equal footing. There is not a special distinction between the two. All of them are treated and modeled in the same way. You know that density matrices for an n-qubit state can be written in this formula, in this decomposition on the Pauli matrices sigmas. And essentially, a pseudo-density operator for the same n qubits can be written slightly differently from this one. As you can see, the only different term is this one with respect to this one, which is the difference between these two. And that is really the core of pseudo-density operator that allows including the temporal correlation is exactly this. These are not the expectation value of the measurement run on this n qubits simultaneously. These are the expectation value. This is the expectation value of the product of the results of an ensemble of separate von Neumann measurement events on each of the qubits. This means that there is no way that we don't have to take into account what is measured together with the other qubits of the state. I mean, if I consider a measurement on one qubit, the result is that one. If that result can have an influence on the other qubits, and of course it can, I will have to just exclude that influence and measure and consider the other qubits as they were measured without anything else together with them. That's the difference. Okay, let's review some properties of pseudo-density operators. They are Hermitian trace-one operators, and they allow the partial trace. And we like it because we know that this is properties that even density operators should have. They allow considering both spatial and temporal correlations together, treating them on equal footing. That's a very nice feature. But unfortunately, there is something that is not as nice as this. They are non-positive. Negative eigenvalues are allowed. This means that a PDO might appear like an unphysical state, because you know that negative, positive semi-definiteness is one of the cornerstones of density matrices. Here we don't have this because we have to take into account temporal correlations that might give rise to negative eigenvalues. But of course, if I restrict myself on a subsystem involving only spatial correlations, there I recover the physicity of the state. I recover the positive semi-definition of the reduced PDO that becomes a proper density matrix. But one could say, okay, what do we need it for? Well, there are scenarios in which temporal correlations play a crucial role, even more than spatial ones. And density matrices might fail to describe them properly. One example of them is represented by an entangled pair entering an open time-like curve. Essentially, every kind of time travel scenario can give rise to crucial temporal correlations that can be properly described by density metrics. Not only that, but with PDO, we can also formalize quantum dynamics as a series of teleportations in time. That is a novel concept, another way to look at quantum dynamics, essentially. Okay, let's move on to the first scenario. That is the open time-like curve. What is an open time-like curve? As you can see, I have initially 2 qubits, Q1 and Q2. After some time, Q2 enters a time portal, be it a wormhole or whatever, and becomes and is re-emitted essentially together with its past copy Q2 as the qubit Q3. Of course, if Q1 and Q2 are maximally entangled, also Q1 and Q3, since nothing happened in between, should be maximally entangled. And as well, Q2 and Q3 should be maximally correlated. No, it's not a real appropriate entangle, but their correlation should be maximally null basis because they're essentially the same qubit at 2 different time instants, TA and TB. And this is precisely a scenario in which the density matrix formalism gives rise to some inconsistencies in the theory. Okay, you all know that in the past we had initially the Newtonian absolute time with where the time was a true and mathematical concept that was passing equally without relation to anything external and no reference frame or whatsoever. Then we had special relativity. Time is just the 4th coordinate of space-time. A proper time can be defined for each observer as the time seen on the observer's clock at rest. There are relations between time intervals, the velocity, the speed of the movement, and everything else. And then we have general relativity, where time becomes just a general space-time coordinate, allowing in principle even time travel. And about time travel, we have the example of a closed time-like curve in which a particle travels back in time, affecting its past self, giving rise to the celebrated paradox of grandfather paradox. That means if I was supposed to travel back in time and kill my father before he was giving birth to me, should I be born and be able to do that? But this is still an unsolved problem in some sense in general relativity. But we don't have only that. We have also the open time-like curve. It's a special time travel case in which a particle travels back in time without causally affecting itself. One could think that this does not give rise to problems like in the CTC case, but this is not true. Okay, these paradoxes, it's good to hear that thanks to the work of David Deutsch in the early 90s, can be somehow reconciled thanks to quantum superposition at the level of quantum particles. This is a network scheme of a closed time-like curve. We have an initial state that is this rho no vector times O times rho CTC. The rho no are the qubits that don't enter the CTC. The other ones that do enter the CTC are represented by the minus T here. This is the gate working as an modeling. The quantum gate causing the unitary evolution on the joint subspace of these two systems. And we have a consistency conditions that say that if this rho CTC is equal to the trace of the evolved whole system of this entering this gate, then there is no problem, and this network is perfectly consistent. And so this kind of CTC on the quantum at the quantum level can be even allowed, that does not give rise to any paradox if this condition is satisfied. There have been done some simulations of CTC with optical qubits. We have these two works that essentially model it, proving that proving the theory from David Deutsch. And unfortunately, one has to notice that the CTCs cause nonlinearity. And of course, although they are allowed, the linearity can give rise to different issues, like perfect discrimination of the non-orthogonal states, violation of the uncertainty principle, of violation of the cloning theorem, and so on. Some criticalities can arise even in OTCs. This is the scheme. This is the scheme of the previous OTC that I presented before in the slide before. And if qubits 1 and 2 are initially maximally entangled in the chronology violation region, that is the one, the one in which all the qubits are present here, treating qubit 3 as not as the copy of the qubit 2, okay, with traditional density matrix formalism. And we know that one should observe the monogamy of entanglement, saying that if 1 and 2 are maximally entangled, 2 and 3 should not. And this is not true in this framework here, because 2 and 3 are essentially the same qubit at 2 different time instants. And monogamy of entanglement, if we model it, if we model this scenario with the usual density matrix, is violated. How can we allow the violation of the monogamy of entanglement? Well, one could consider the solution of adding non-linearity to quantum evolution, but we like linearity in quantum evolution. We like quantum mechanics to be linear. Let's look to something else, because this violation is, of course, due to the fact that one entanglement is due to spatial correlation at the same time, and one is due to something that appears at different time instants. Okay. Here we have this the CTC, the OTC scenario that I illustrated before. And this is the pseudo-density operator that describes it. We have these quantities here that are essentially these correlation coefficients. And let's see what we can do with this OTC. Let's see what we did in our labs trying to model this CTC. We have the same scenario as before. We try to simulate the same scenario presented before. We have a quantum optical setup producing entangled pairs by parametric unconversion. The singlet state produces this one. We have entangled photons in polarization. And then, as you can see, we have Q1, Q2, and Q3 that represent the measurement events on the 3 qubits that are present in our scenario. And of course, if we want to reconstruct the PDO and not the density matrix, we have to evaluate the eventual correlations like these measurements don't have influence on each other, okay? And this is not true if you perform usual tomography. You should have, this is a different framework with respect to the density operator, and it needs a different set of rules. Okay. Here we have our measurement setup. First, we measure the whole set of observables X, Y, Z on photon A at time T1, that is Q2, and at time T2, that is Q3, including all cross correlations. And what we obtain is this R23 that is an unphysical matrix. It has one negative eigenvalue. Then we measure the whole set on photons B and A at time 1, let's say Q1 and Q2, obtaining this singlet state density matrix. And we do the same, but with photon A at time T2, essentially obtaining the same result as R123 as R12. That is the density matrix of density parameters of a single state. And then we measure the whole set on photon B at time 1, A at time 1, and A at time 2. But the one on A at time 2 should be identical to the measurement occurred on Q2. Why? Because otherwise, those we would have correlations showing the influence of measurement on Q2 to on measurement on Q3, and this is exactly against the spirit of pseudo density operator. This procedure highlights some of properties of the pseudo density operator. Essentially, we have R13, that is a single state, but should we obtain it as a trace over subsystem 2 over the more general of the general PDO R123? Well, unfortunately, this cannot be obtained experimentally because if we acquire measurement for the 3-point correlations and then average over the results of the measurements on Q2, that was actually our initial mistake in doing this kind of experiment, we don't obtain this. Why? Because if we have this kind of scenario, we apply the Born rule with a PDO, we don't obtain this. This might be the trace over this quantity, might be not a real probability, might not be above 0. Because the trace over a temporal degree of freedom is not equivalent to averaging with respect to all possible values of the observables measured at the same time. So although R13 can be obtained as a trace over qubit 2 of R123, this is not something that applies when experimentally you try to do tomography or procedure close to tomography of the density operator, of the pseudo density operator. It's not possible because although the treatment within the PDO formula is the same, we cannot deny that experimentally the physics of temporal and spatial correlations is not the same. Otherwise, we wouldn't have negative eigenvalues that are proof of temporal correlation. I mean, it's not that temporal correlations are always related to negative eigenvalues. Negative eigenvalues must be due to temporal correlations, but temporal correlations can be even give rise to positive eigenvalues. So there is no way also to discriminate between efficiently between the two. Okay. Let's see the results that we obtain with the technique that I illustrated before. On the left, we have the theoretical R123 modeling the OTC or scenario. Of course, I didn't report the imaginary part because it's 0. And on the right, you have the reconstructed imaginary and real part of the matrix. As you can see, the correspondence is almost perfect, aside from some imaginary components arising here due to imperfection in the optical equipments and maybe on the visibility of the state, although it was quite good. And if we do the reduced density operator, if you look at the reduced density operators to quantify the agreement between the theoretical expectations and experimental results, we obtain this. This is R12, the reduced matrix R12, that has a fidelity of 0.96. This is R13, again 0.96 fidelity has been reached. And this is R23, and of course, no fidelity could be calculated because it doesn't work like this. I mean, it doesn't work for non-physical density matrix. Okay. Of course, I talked about before I introduced the problem of entanglement monogamy violation in C. If we have to respect entanglement monogamy, we have to respect also this relation here made on the CHSH inequality values. Okay, we measured this quantity here, and what we obtained was this: C12 plus C23, C12 plus C13, and C23 plus C13. In all the cases, we have a more than 20 standard deviations violation of entanglement monogamy. That is something that is in sharp contrast with respect to the density operator for normalism, but is not in contrast, and it is predicted and allowed by the pseudo-density operator. So we don't need any more for nonlinear evolution. We can keep having CP maps mapping this, a PDO to another PDO without taking into account anything less trivial, let's say. Okay, and this is a proof of how the pseudo-density operator is able to perfectly model a situation like this, in which temporal and spatial temporal correlations play a non-negligible role, much better than what a density matrix can do, because the problems related to entanglement monogamy here are not present anymore. I mean, we still have entanglement monogamy violation, but here is perfectly allowed. Okay, enough with this time travel topic, and let's look at how this can have an analogy in the qubit model of an evaporating black hole. Because the same PDO structure that appeared before can be exactly performed in a scenario like this. We have a black hole, and the black hole evaporates, emitting Hawking radiation, only thermal one. Let's simplify the case, but these thermal radiations can give rise to entanglement particles on the event horizon. Let's say that if the entangled pair is generated in the just close to the event horizon, one of these particles falls into the black hole, and by the inversion of a Schwarzschild metric, the correlations in the spatial domain between these particles become temporal correlations because of the space-time signature swap. Then black hole evaporation must be a unitary process. And if qubits are infinite number, after half of the qubits have evaporated, a maximally entangled state is formed between the interior and the exterior of the black hole. Then more evaporation would violate again entanglement monogamy. But by exploiting the PDO formalism, we are able to correctly incorporate space and time-like correlations, avoiding entanglement monogamy violations and reconciling the information loss paradox in an evaporating black hole. Curious enough, if we consider one qubit inside the black hole becoming entangled with this one that falls within the event horizon, the structure of this 3-qubit PDO is identical to the one of the modeling the OTC in terms of correlation. Okay, let's switch to the second scenario, quantum dynamics via temporal teleportation. Okay, we have stated that in PDOs, temporal correlations and spatial correlations are treated in on equal footing in the same way. This means that, essentially, PDOs provide a static picture of the universe with all the events laid out in space-time with their connections encoded in the PDO. This is a similar scenario to what happens in the block universe, in which you have this, here we eliminate one of the special dimensions, but here in the block universe, you don't have dynamics, essentially. You just have the events encoded in different points of this universe with temporal with time as another coordinate, and there is a little room for dynamics. How in a framework analogous to this one, because PDOs are not block universe, not the block universe framework, but in this sense, they could be considered analogous because even PDOs provide a static picture of the universe, essentially. And the answer to this question is temporal correlations within the PDO allow qubits to undergo quantum teleportation in time domain. We know that quantum teleportation is a common quantum communication protocol in the spatial domain, involving entanglements in the spatial domain. But here we show how this can be transferred on the formal level to the temporal event, and how can dynamics be described as a series of teleportation events in time. Okay, let's suppose to have a maximally missed qubit initially, undergoing trivial evolution. The case of a non-trivial evolution is not different, but is just a little bit more complicated as in formalism. So I want to restrict ourselves in let us restrict ourselves to the simplest case scenario. And let's suppose to measure it at two different time instants, TA and TB, in the basis X, Y, Z. What we obtain, if we compute the PDO, is this one, with perfect correlation in all bases and negative eigenvalues present, of course. Okay, in analogy with the Bell state basis, we can form a set of 4 maximally correlated PDOs that are orthogonal with each other. So here you can already see that if we substitute these PDOs to the usual Bell states, we can have a sort of hint of how temporal teleportation can work to transfer our qubit from one time instant to the other. And this is how it works. We have the density matrix of the qubit at the nth time instant Tn, with the Rx, Ry, and Rz being the components of the block vector. And at time instant, the following time instant Tn plus 1, the qubit density matrix becomes this thing here that can be calculated as the trace on Tn and an associated subsystem A of this quantity here. But if we substitute this trace, in this trace, these pseudo-density operators with the usual entangled pairs Bell states, we have a formal analogy with traditional quantum teleportation. Then, since this is simply a transfer, let's say, of the qubit from one instant to the other, quantum dynamics can be formally represented as a series of teleportation in the time domain, generalizing the n parameter. But I have to underline that this is just a formal representation, because PDOs do not represent physical states. Then this temporal teleportation does not correspond to a physical process. It's not that I'm really doing temporal teleportation. Of course, it's impossible, because the PDOs that are needed here are unphysical states. I cannot produce them. I cannot obtain them. What I'm saying is that the mathematics undergoing it is the same, and so it we can let's say rephrase quantum dynamics as a protocol involving a series of teleportation in the time domain. Okay, how do we experimentally demonstrate this? Of course, not by generating the PDOs that I mentioned before, because they are unphysical. I cannot do quantum teleportation with temporal states. But what I can do is show the correspondence between temporal and spatial correlations, giving a hint of how temporal and spatial teleportation can be analogous one to each other. To do that, I measure a generalized multiparameter CHSH inequality in the spatial and temporal domain, being, of course, S related to spatial and temporal and T to temporal one, with n parameters and settings for each experimenter, let's say. C is the usual correlation coefficient between the Boolean variables A and B. And please notice that the average on A and B is given by the Born rule applied to the PDO and not to a density operator, because it requires two different time instants, TA and TB. And we also study a special case on a sort of hybrid CHSH inequality, in which half of the correlations are taken in the spatial domain and half in the the temporal domain, and half in the spatial domain. Okay, we have these inequalities to be tested. To do this, we use this experimental setup. Again, we have a singlet state produced in our parametric non-conversion setup. We have a visibility of the state estimated from a fit on the coincidence events collected, that is 0.98, then a quite good visibility. And then for the spatial domain, we just look at these two measurements here, ignoring and removing what happens next. And of course, for the temporal one, we have to just relate on the two measurements of channel 1, neglecting what happens on channel 2. By doing this, what you obtain are these results. As you can see, we have the experimental point with their uncertainty bars for the three CHSH inequalities studied. And there are also three different theoretical behaviors. And you know that in line of principle, by generalizing n, in the limit n going to infinity, these should essentially, the limit should essentially go to 2. Okay. This does not happen even, this happens in the temporal domain, but as you can see in the spatial domain, we reach a maximum and then we have a degradation. This is due to the fact that these theoretical curves that perfectly fit the experimental data has been calculated with the visibility of the state that with n equal to 10 already prevents us to grow anymore in this asymptotic and to reach the asymptotic regime. While for the temporal domain, since perfect correlation is expected, we use the usual the theoretical visibility, this one. By this, we can say that, and of course, in the hybrid one, we used an intermediate visibility. With this, we demonstrated that spatial and temporal correlations behave in the same way. This allows us to formally reformulate, by analogy between the quantum teleportation in the spatial and temporal domain, formally reformulate quantum dynamics as a series of PDO teleportations in the time domain. So quantum dynamics can still be recovered in the PDO formalism, although they include the temporal coordinate, by recurring to the teleportation tool in the time domain. Okay, let's look at some concluding remarks. I presented a new quantum mechanical formalism called the pseudo-density operator that extends the usual density metrics to include and treat on an equal footing temporal correlations, at some costs. As you can see, we have to give up on positive semi-definiteness and on physical states. That means it's quite a huge loss. But in exchange, PDOs can help modeling scenarios that a traditional density matrices fail to describe, e.g., the ones hosting OTCs, CTCs, and generally chronology violation space-time regions. Not only that, but the quantum simulation of OTC that I presented has been realized in our labs in Torino, and has shown a good agreement between the reconstructed pseudo-density operator and the theoretical one. And because of that, a strong violation above 20 standard deviations of the entanglement monogamy in the chronological violation region of the OTC has been measured as predicted, correctly predicted by the PDO. Then we performed the analysis, the same analysis on another scenario that gave rise to similar PDO that can be modeled, let's say, by a similar PDO, an identical PDO actually in this case. And this can give a good explanation, a good reconciliation of the information loss paradox in an evaporating black hole. Then finally, although PDOs include temporal correlations and can initially be thought to give a static picture of the universe, like the block universe one, that quantum dynamics can still be recovered inside PDOs by a series of PDO teleportations in the time domain. Although it's impossible to prove this because quantum teleportation cannot be done with temporal PDOs, since temporal PDOs are unphysical states, we gave an experimental proof of this by showing how temporal and spatial correlations in quantum mechanics behave exactly in the same way, allowing for this correspondence between spatial and temporal teleportation. And okay, of course, I didn't do this by myself. This is the crew behind these works I presented. There are two postdocs, Salvatore Diazzi and Enrico Bofello in our group in INRIM in Torino. Then there is me, Dr. Alessio Vella, Marco Gramegna, and Ivo Pietro De Giovanni, our group leader, Marco Genovese, and then we have on the theory side, Professor Chiara Marletto, and Professor Vlatko Vedral from Oxford. And these are the works that have been presented in this talk. And with this, I thank you again for your attention.
Thank Professor Fabrizio for his nice talk. And now it's open for question. So is there any question?
Hello.
Yes.
Hello, Dr. Piacentini. Could you go to the previous slide where you showed your experimental setup for Q1, Q2, and Q3 measurements?
Okay. Sure.
Thank you.
Just 1 second.
Yeah, so I wanted to ask you how, like, I'm assuming Q1, Q2, and Q3 are measurements here. So how do you make Q2 the measurement Q2? It's not like Q1 and Q3 they go to single photon detectors, but Q2 I don't see.
The way to make Q2 uninfluential on Q3, you mean?
Okay, so the active measurement on Q2. Okay, right. Okay, fine.
Yeah, the active measurement on Q2 definitely influences Q3. But if I essentially I don't when I do the reconstruction, I don't do for the whole quantum tomography procedure, because otherwise I would see such influence. But if I measure commuting observables, let's say the same observable on Q2 and Q3, it's just like one can say that Q2 never happened because I have the same result.
Okay, sir. Thank you. Thank you.
It's just taking a subsystem, a subsample, sorry, of the whole quantum tomography procedure, because I have to remove the influence of Q2 on Q3.
Yeah, any more question? Yeah. So So maybe there are no questions, but I have simple question which may be very mathematical. So if you consider on the product measurement, I mean local measurements,
Okay.
yeah, then still you can return probability, I mean positive probability, if you consider even witness operator, which is more general than density operator, and which may have a negative eigenvalues. So I am wondering whether your operator, which you are calling pseudo density matrix, they are like this witness operator. Witness operator is positive on product observable. So, but when you consider entangle basis, then it may give you negative probabilities. But if you consider only product measurement, then it gives you all positive probabilities. So I'm wondering whether the pseudo operator that you are considering, they are kind of witness operator.
Well, that's a nice question and a good one. Well, I think that's pseudo-density operator. The advantage of pseudo-density operator, the good thing is that they are the same for product states, and they can allow to model product states, entangled states, mixtures, and whatsoever. We don't have. I mean, just the fact that we have negative eigenvalues is because of just of temporal correlations. It's not because of the kind of state of kind of system that we model, and we have to allow for temporal for negative eigenvalues, because otherwise how could I explain that if I have my qubit, I measure it at 2 different time instants, and without I suppose to measure it, not I don't measure, I suppose to measure in 2 different time at different time instants. I have to allow to perfect correlation in all the Pauli bases. I have to, because it's not, it has not evolved. The correlation between my thought measurements should be 100%, and this can happen only if we have a negative eigenvalue allowed. So it's a slightly different perspective, in my opinion. Okay. But I might be wrong. I mean, I'm an experimentalist, so probably I didn't even give the right answer to your question. I apologize for that.
Okay, thank you. So if there is no further question, then let us thank the speakers once again. Yeah. Okay.
Hello, hi.
Okay then. So you stop sharing your.
Yeah, sure. Okay.
So
Thanks.
Thank you. So our next speaker is Professor Apurva Patel, who is a very well-known figure in the community of quantum computation in India. He is a professor at the Center for High Energy Physics at the Indian Institute of Science, Bangalore. And he obtained his MSc in physics from Indian Institute of Technology, Bombay. And he did his PhD in physics from the California Institute of Technology from USA. And he has extensively worked on lattice-based theory investigation of quantum chromodynamics. But as we all know, that he's an expert in quantum information and quantum computation, and he has some notable work on quantum algorithms, the application of quantum theory concepts to understand the structure of genetic languages. So I request the pattern to start his talk. The full screen?
Thank you, Guru Prasad. Can you see my slide?
Yeah, but is it full screen?
No, I will make it full screen.
Yeah.
Okay. So my talk is somewhat on a different line. I'm going to describe a software simulator for noisy quantum circuits that we constructed. Right now, it is an educational platform, but it can be developed further to do many other interesting things. This software library is based on IBM's Qkd platform that is publicly available, and our Ministry of Electronics and Information Technology has made it available as a nationwide facility for anyone who wants to use it at a website which I have listed here. It's called qctoolkit.in. So why does one construct simulators? They are used before actually manufacturing complex systems and devices, because they are easier to make. The model system using less hardware resources, and they are also easier to tune. So one can play around with the design parameters and optimize the fabrication, which ultimately will be done. The fabricated devices, in addition, are always going to be imperfect. Maybe slightly, maybe more. And in such situations, the simulators are also useful as benchmarks. They can perform checks which undergo two different labels. One of them is verification, which means does the design system meet all the input specifications that have been built in. And the other is validation, whether the system provides the intended target performance. These two are not necessarily the same. On top of that, the simulators can also help in reaching a wide audience and generate interest in the field of research. They can help us understand physical phenomena better and also explore new possibilities. Most of the time in situations where detailed analytic results are not available, either because the system is too complex or because our analytical capabilities are limited. So this kind of simulators are used routinely in our conventional industry, they go under the name computer-aided design tools. They are much more important because quantum devices are far more fragile and can have lots of noise and imperfections compared to the classical systems which we are used to. And so there is all the more reason to try out various features of quantum systems that we want to make on a simulator first before we go for manufacture. There are lots of parameters you can include in the simulators. There are interactions with environment, exceptional disturbances. You can put some values for them, tune them in some manner. You can also vary the physical properties of the hardware, which will be provided by the materials, the geometry, and the connectivity of different components. And one particular feature which arises in playing around with this parameter is that the naive estimates of errors are actually too pessimistic. They are conservative. They give some kind of bounds. And the actual device may perform better. They will have some tolerance levels and thresholds to be satisfied. But the modeling can be tuned so that the error remains under control, and that saves a lot of trial and error effort. The reason this happens is the errors themselves can decay in the process of evolution. They can also have destructive interference in quantum evolution. And those are the kind of features which are left out in analytical estimates, but they can be put in directly in the simulator. So what we are going to describe is a imitation or mimicry of a noisy quantum processor constructed as an open quantum system. And by necessity, this description has to be the density matrix language, and various kind of errors will be included in the evolution. The errors which we have included in 4 different categories. One is the thermal effect, initialization of the quantum registers itself. Even when you say that the initial state is 0, it may not be exactly 0 because the ground state can have admixture of other states in a system with non-zero temperature. The logic gates are going to be imperfect, maybe because the instruction is not that precise, and maybe the fields which are applied to execute the instructions, they are not precise. Decay and decoherence of quantum state occurs throughout the evolution. They are due to the environmental effects, just a generic label. They are due to degrees of freedom over which we have no control. And at the end of the evaluation, there are going to be errors because the measurement instruments are not perfect. And one of the most common measurement error is depolarization. So a simulator includes these different types of errors. Of course, if one can think of more errors, they can be added. What we have planned to do for future is add some new things like the connectivity between different qubits. Right now it is all-to-all connectivity. And what are the fundamental logic gates that will be selected as elementary operations? They can change depending on the actual hardware quantum processor. And such additions will convert this educational platform to an actual design platform that one can use this for designing actual quantum processor. And the situation of this kind of design is generic. Any quantum device that you want to make will need a simulator. As a matter of fact, all the companies which are running after developing quantum processors, they have their own simulators of doing various things. Only thing is that those simulators are not in public domain. What we have done is work which is open source, available for anybody to use and modify. So this simulator, as I said, is based on IBM's open source Qkd platform. It expands on it, and it is following the same conventions of Qkd. So it is written in Python, and it is compatible with the names of the routines that are used. It's open source and available on this GitHub website. The structure is that an n-qubit quantum register is described in the Pauli basis. Pauli basis is just tensor product of the four fundamental qubit operators: identity, sigma 1, sigma 2, and sigma 3. And this structure is very useful for several reasons. One of them is programming convenience itself, that the coefficients which I have denoted A with subscript I1 going to IN are all real. The complex number algebra completely disappears. We are working with codes which has only real numbers. And that's a great help in programming. The more common density matrix expression is written as 2 raised to n times 2 raised to n complex Hessian matrix. And if you want to deal with that, you have to keep track of the complex numbers. Compared to the simulation of a noiseless system, which actually is much more widely available because it is simpler to code for, that works as a pure state in the Hilbert space structure. There are vectors describing the quantum state with 2 raised to n coefficients. To deal with the density matrix, we have to go over to 4 raised to n coefficients. Instead of a vector, we now have a matrix. So we have a lot more variables to deal with, and that requires larger effort both in memory as well as execution time. But this is the price that has to be paid if you want full flexibility, include all kind of external noise and errors which can affect a quantum evolution. There is just no way to describe quantum evolution with noise in a state vector language. What is the bottom line that is useful for anybody who wants to try it out? That this software can simulate circuits with 10 qubits and of the order of 100 operations in a few minutes on a laptop. And in that form, it is fairly portable. If you want to deal with larger systems, you can go a little bit higher, say up to 15 to 20 qubits and up to 1,000 operations on powerful workstations or computer clusters. But that is the kind of limit, because the Hilbert space is growing exponentially with the number of qubits, and going beyond this size will just not be possible. If you want to check out, just figure out what is the number 4 raised to 20. How much disk space will be needed, and how many operations will be needed. So now let me go to the explicit construction. Density matrix is an ensemble description, and I gave the parameterization in terms of Pauli basis. In this structure, the coordinates which I labeled 1, 2, 3 can be freely chosen independently for every qubit. There is no specific direction which is selected. And the coefficients have very simple bounds. One of them is the trace law equal to 1, so the coefficient will add up. And we have already normalized so that the 2 raised to minus m in front of the expression makes trace law equal to 1. On top of that, we have a generic constraint that trace of rho square is also equal to 1, whether the state is pure or mixed, and that gives a bound on the overall magnitudes of this variables A. Sum over all the A square is less than 2 raised to n. So the numbers are going to remain bounded, and the first number, which is the coefficient of identity, is always 1. What else? You can do several simple calculations rather trivially. If you want to measure an operator of the density matrix, you write the operator in the same basis, and then trace of rho times 4 is just the dot product of the two sets of coefficients. If you want to compare two density matrices, you can evaluate the distance between the two as trace of ρ1 minus ρ2 whole square. And this distance just turns out to be the Euclidean norm for the two coefficients for the density matrices, say A and B. So the whole structure is perfectly suited to do all kinds of things using simple linear algebra. What are the inputs you put in? Well, we want to include arbitrary errors, and the generic formulation for that is given by super operators specified by its Krauss operators on representation, which I have written down as the evaluation from rho to mu, rho, mu dagger, sum over all the values. With a normalization constraint that mu dagger, mu, sum over all values of mu is identity. Note that this representation includes both unitary evaluation and projective measurements as special cases. Unitary operator has only one term in the summation over mu, and mu is replaced by matrix U. Projective measurements will have many terms, but this variables mu will be replaced by projection operator Pk, which are orthogonal and square to themselves. And so we do not have to deal with unitary evolution and projective measurement at two different parts of the dynamics. They are part of the same dynamics. And the generic dynamics is specified by choice of a suitable set of this operator mu. And for various types of errors which I described, I will point out what are the corresponding Krauss operators that have to be included, and that will do the job. Every operation will be implemented by this simple rule in some sequence specified by the algorithm. So let me now describe the individual steps. There is a initialization procedure, and for many states which we are interested in, it can be quite conveniently factorized. For example, the uniform superposition state is just 1 plus sigma 1 raised to the power n, operating on the ground state made up of all zeros. If you want to go to another state which is specified by a particular strings of zeros and ones, the corresponding density matrix is nothing but a tensor product sequence of 1 plus sigma 3 and 1 minus sigma. Just write it down explicitly. What about the logic gates? We had to choose an elementary set of logic gates which can be implemented easily, and Qkd already has a particular convention. So we took the parts which were useful to us, and this set is essentially written down with 3 different operations. One is rotation of a single qubit around a specific axis, which has the notation u1, and the rotation angle is theta. A generic rotation about any arbitrary axis for a single qubit can be decomposed in the Euler scheme, where there are 3 single axis rotations, but the axis of rotations are fixed. They are not going to point arbitrary direction in space. And this is common for practical implementation in a hardware quantum processor, where the fields are applied to perform such rotations, but the directions of the fields are externally fixed, and they can be aligned with a particular set of axes that are of interest. And typical choice is the Cartesian coordinate axis. The Euler scheme requires actually only 2 directions out of these 3. The third can always be generated as a commutator. And that defines the operator U3, and the 3 angles are parameters which specify how much is the angle of rotation. And all other operators can be done in this decomposition. For example, the Hadamard operator, just I times U3 with angles I by 2, 0, and pi. So this can also be easily implemented, provided we have a code for rotation around the Cartesian axis. And the third operation which we included is a 2-qubit operation, and we chose the most popular one, which is the control knot. And this set is sufficient in the sense that any quantum algorithm can be broken down into this elementary set, and then by applying these elementary operations in some sequence, we will generate the total transformation specified by the quantum algorithm. Whatever projective measurements, that also is very easy, provided we perform it by going to the same basis, which is specified by the Pauli operator. So for single qubit, that is always easily done. You specify the direction of measurement by some unit vector, and that can be written in terms of linear combination of Pauli matrices. So to perform the projective measurement, you just have to read the corresponding coefficients from the density matrix. To prepare the post measurement state requires a little more work, but that is also easily done. All you have to do is keep the component along the direction of measurement unchanged, and keep the components which are orthogonal to the direction, make them 0. The components which go with the label identity or the index 0, they remain invariant. Nothing happens to that particular text at all when you perform the qubit measure. And all these properties, what are the probabilities of specific measurements, what are the post-measurement state, they can be converted to many different structures which are used in algorithms, and I have listed them here. There is a single qubit measurement, this is the easiest thing to do. Then is a ensemble measurement where you perform binary measurement on all the qubits in some computational basis, and they can be just carried out as tensor product of the individual coefficients. You have to sum over many possibilities. That is essentially what happens, and the tensor product dictates the sign of whether it is up or down for a single qubit measurement of a Pauli operator. Expectation value is part of the easiest, as I said. It is just given by the dot product of the two vectors of the state and the operator, and it is just one particular coefficient. Nothing more complicated than that. But we did a little more, and we implemented bin basis measurement, a qubit pair as well. It's a little exercise to describe what the base states correspond to the density matrix language, and it turns out that they are rather symmetric. They are just linear combination of the same Pauli matrix on both the qubits, tensor product together. And different base state correspond to the sign of this tensor product of Pauli matrices become plus or minus. And even that can be implemented by the same logic. Keep the measured components and the directions unchanged, and everything which is orthogonal to it becomes zero. On top of that, we needed an instruction for resetting a qubit. This is not a measurement operation, but it is very closely related to it, and it can very easily be done by saying that the state is basically the cat vector 0 or equivalently 1 plus sigma 3 by 2 in the density matrix language. You just have to put those coefficients to appropriate value, and with all the overall multiplication, it means that the coefficient with ik equal to 3 is made equal to the coefficient with ik equal to 0. And we are setting the state to cat vector 0. Okay. Now the noisy part. We assume that the noise is local. This is the standard assumption in most error models, where what happens to one qubit is completely independent to what happens to other qubit, and then the whole system can be nicely factorized. For example, the initial state can have a contribution from excited state given by a Boltzmann factor, and that can be easily incorporated by making the density matrix a distribution with P and 1 minus P on the diagonal, and then you can raise it to number of qubits which are forming the register. For the logic gates, the rotation axis already got fixed as the Cartesian axis, and the errors basically arise after that and some inaccuracy in the rotation angle. And these errors can have two components. There can be error in the mean value of the rotation angle, and there can be fluctuations around the mean value also. Both of them are easily incorporated in the trigonometric functions which describe rotation, and all that has to be done is multiplying the sine theta and cosine theta by some scaling factor R, which measures the fluctuations around the mean, and change the mean by the bias which got introduced in the angle. The same logic can be applied to the control knot operation if it is interpreted as a transition selective pulse, where depending on the state of a qubit, the target qubit undergoes transition or not. Again, this is a common situation in practical implementation, and then the error is only in the duration of this transition selective pulse, and that can be modeled by the same logic as the error in the rotation angle. In the conventional notation, the control knot operation is implemented by the polymetric sigma 1, and we just have to disturb the rotation operator corresponding to sigma 1 a little bit if we want to include an error in this transition pulse. Measurement is model dependent. What we took it to be is the most common possibility, which is depolarization. And it's a generalization of bit slip error, which means that when you measure 0, you may not always get 0, sometimes you will get 1. And such depolarization error, the quantum language is just mixing of the density matrix with the identity matrix with some coefficient, and that coefficient can easily be put it as a parameter. It just changes the expression for the density matrix, which is n dotted with polymetrics by a multiplicative coefficient in front, which I have labeled D1 in this description. And finally, the major error, which happens all the time while the data is just sitting in the memory. And this has two components. One of them is called a decoherence. What happens in decoherence is the off-diagonal components of the quantum state decay. And we have chosen the computational basis to be the same as the basis of sigma 3. So the off-diagonal components are described by sigma 1 and sigma 2, and we just have to scale them appropriately. On top of that, we have to apply this decoherence continuously, and the simplest solution is to go to the digital implementation of the quantum algorithm as a sequence of time steps or clock steps in which every elementary operation is implemented. And for a quantum system to work reasonably well, the error must not be too large over a single text. Once that is granted, this error decoherence can very easily included by just a total formula. Let's say some logic operation followed by some decoherence and another logic operation, another decoherence, etc. And because the errors are small, the Trotter expansion is fairly reliable. In the computational schemes, all that happens is the off-diagonal components are going to be multiplicatively suppressed by a factor, which is something that has been given as an input parameter to the algorithm. One can also have a decay toward a thermal state. This is because the 0 and 1 are the ideal states of the environment, and environment has some temperature. And that also can be modeled. In this particular case, the diagonal density matrix components with the label index 3 also change, because 0 can decay towards the thermal state, 1 can decay towards the thermal state. Of course, in practical situations, 0 is much closer to the thermal state than 1, but that can be included as the rate of decay of the parameter, and one can work out the algebra, what this usually does in terms of changes in the quotient. There is a multiplicative factor and there is a translation. The translation factor is due to the state 0 moving towards 1 and the ones moving towards 0. Both of them try to go somewhere in between. And here is the observation of a simple algorithm with all the different parameters varied over a certain range. The calculation implemented was a fairly trivial one, just a binary addition. 110 plus 11, the result should be 1001. But when the errors are there, the final result will be not just 1001, but a distribution over the values of the 4 qubits. And one can measure the accuracy by calculating the fidelity or the success probability, which is nothing but the overlap of the density matrix, which comes out of the evolution of the algorithm, the simulator, with the exact answer, which is the result when there is no noise. And this success probability is plotted here for various different kind of errors, which I just described. There is a thermal error, depolarization, angle in change of rotation, decoherence, and decay. And what we see is that most damaging of the errors are the decoherence and the decay contributions. That is expected because they are acting continuously during the whole evolution, while the other ones act only over some specified operations or intervals. But what is also noticeable, that the decay is actually more damaging than decoherence. There is no simple explanation for that, but it just says that when you design the actual hardware, tune the parameters so that the decay rate is smaller in terms of the errors it produces compared to the decoherence rate. In standard language, which is often used in NMR description of quantum processors, decay and decoherence are described by time constants which are T1 and T2. They are independent quantities, though constrained by certain overall rules. But this observation tells you how well you should control T1 and how well you should control T2. Now the question of complexity. What is the effort required to run this simulator? As I described, all the operations are basically linear algebra operations done with all real variables. You just do additions, multiplication, and permutations, nothing more than that. And these operations can easily be counted. And the counting gives that the memory required has specification of 4n real values. The logic gate linear algebra is local and it can always be written as operations involving block diagonal matrices with fixed block sizes. And so the effort is again 4n, the size of the density matrix. Similarly, the environmental noise is also local and expressed as block diagonal matrices with fixed block sizes. That is of order 4n also. The measurement is actually much easier because for many operators, it's just a value lookup. You already have the operator in the poly-observable form, you just have to read the coefficient. And that is an order n effort if you have n qubits. If you want to perform the closed measurement state, then you have to do detailed implementation involving multiplication with the projection matrices, and it becomes of order 4n. So this is fairly straightforward. And now I can give the bottom line. What happens when you actually run the simulator? The simulator takes more effort in the density matrix structure because the resource requirements are going up as order 4n compared to the simulator which works with a state vector in Hilbert space description where the resource requirement is already order 2n. So that means if you have the same fixed resources, the density matrix simulator will simulate about half the number of qubits compared to what you can do in the state vector language. But this is the price you will pay to be able to include arbitrary errors coming from the environment. What did we actually do to code this whole library efficiently? That we kept the overall structure of Qkd, which means the code is written in Python. Programs are written in terms of Jupyter notebooks. And there is a graphical user interface where you can point and click on various things you want to carry out. Internally, the high-level instructions are simplified. Because that is the job of the compiler. And Qkd actually has broken it up into two parts. One is related to software and the other is related to hardware. The software related part is called a transpiler, and it combines various components of the logic circuit when possible. Some adjacent gates can be multiplied together to construct a composite operation in the same class. Sometimes the gates can be cancelled using computation rules, and that will reduce the number of operations. On top of that, one can identify the logic gates which can be executed in parallel. They act on independent qubits. And then we take advantage of the parallelism to reduce the overall running time. So the running time dictates the decay and decoherence errors, and we want to control. And so we organize all the parallel logic operations into set of partitions, and all the operations of specific partitions are executed in one shot. Depends on the hardware you have available. On the sequential machine, it will be just a sequential set of operations, but on a parallel computer, they can be assigned to different processes. And then to implement the second part of Tyler job, which is linear algebra operations, essentially manipulations of vectors and matrices. And there is a linear algebra library available for all languages. In Python, it is called NumPy, and that is written in a lower level language tuned to the hardware. This is the hardware of our classical computer to cut down its execution time. And this can be just added as one line instruction in the algorithm. What is the software library you want to use for linear algebra? Nowadays, there are parallelized and improved version of this library available. One of them is called JAX, JAX, and those are useful if you want to run the program efficiently on a multi-core CPU or a graphical processing unit, or even what is called a tensor processing unit. So that's basically it, as much as I want to say. Constructing this whole structure was not complicated. It was done as a summer project with a group of undergraduate students. So it is within everybody's capacity to play around with this. Everybody who is interested to spend some time, find out some new features about improving the system, the libraries, whatever components there are, also adding new kind of capabilities, etc. Doesn't require that much of a skill, and our undergraduate students worked on this, just worked with their laptops. There was no sophisticated hardware requirement either constructing this particular design. There is something else which has come out recently. It has nothing to do with the simulator, but it is related to the execution of quantum program on a realistic hardware when the description of the system is given in this Pauli basis. So it's actually an advantage for using this Pauli basis instead of just the Hermitian complex matrix. What is the advantage? Is that you can determine these coefficients, which I call A with subscript I1 going to In, very easily when you have a quantum hardware available as well. One feature which can be easily seen, then is Pauli operators have a very nice property. You have 4 raised to n of them, but they will either compute or anti-compute. There is nothing else. And so if you take 2 copies of them, that means you have to prepare 2 density matrices with the same prescription, and then measure a joint observable, which is the diagonal one and the sigma I times sigma I basis, similar to what is done for Bell pair measurement. Then all the sigma I cross sigma I mutually compute. So you can measure all of them simultaneously. That means the magnitude of all these quotients can be determined by just using 2 density matrix copies, nothing more than that. And given the kind of problems that we have, it will turn out that lots of these numbers are tiny, or 0. So you can forget about them. And all we need is the sign of this quotient that will give you the complete output. Because a lot of these operators are going to be 0, and there is a reason behind it that when the operators don't commute, they will not have simultaneously large eigenvalues or corresponding quotients. The version of uncertainty principle. And so there are only small number of operators which have a large values, and they will be the ones which will correspond with the, will give you contribution to the expectation values, and we want to focus on them. And sometimes these features are there in the program specification as well, that we want to calculate only a mutual commuting set of observables as an output, and then only we are interested in some reasonably clean subset of all these 4 raised to n coefficients. This can be done provided the observables are listed in some particular fashion. For quantum chemistry applications, actually people have listed what are the kind of observables which are nice sets of mutually commuting operators. What else? The sigma I also have eigenvalues plus or minus 1. And there is a nice result in statistics that when the expectation value is bounded away from 0 by epsilon, the sign can be determined with high success probability, say 1 minus delta, by just performing a measurement, a sample, say n copies of rho, and taking a majority vote. And the result from statistics is that the number of copies needed is of the order of log m by delta divided by epsilon squared. One more thing which is buried inside here is that when you want to measure lots of Pauli observables, say capital M of them, you can perform the measurement on the same copies of rho. You don't have to reset it every time. And then the total error is given by what is called as a quantum union bound. And that error can also be bounded. This net requirement gives this nice result. And it looks surprising when you write it back into the density matrix language. How many copies of rho needed to predict all the expectation values of all 4 raised to n observables, where it is order n. Exponentially different. This is a big separation compared to a classical algorithm where the number of copies required for the cell process will be 2 to the power something linear in that. And this is a nice property of this polybasis, and which is reason to use it for parameterizing lots of quantum structures, both in software as well as hardware. That is the last thing I wanted to point out. I would stop here and answer any questions you may have.
Yeah, thanks, Professor Patel, for your illuminating lecture related to simulating noisy quantum circuits. So now it is open for question. Yes.
Is this density matrix simulator available over the IBM Quantum Experience platform?
Yes, there is any question?
Yes,
I
sir.
didn't understand the question.
Is this density matrix simulator available over the IBM Quantum Experience platform or not?
It generates arbitrary quantum system provided you include all the suitable Krauss operators. We have taken into account some Krauss operators which were the models for the type of noise that we thought about, but it has the capability to generate arbitrary quantum evolution in presence of any environment that may be present.
Yeah, any more question?
Yeah, I had one question. Yeah, Professor Patel, thank you for the nice talk. I just wanted to know, would it be possible, like since all the noise models are Markovian, would it be possible to implement something like a quantum trajectory that would allow you to efficiently, like, increase the number of qubits that you can work with, and like you can solve these trajectories on clusters and something like that?
This Krauss operator evolution includes both Markovian and non-Markovian possibilities. Okay, it's a general CPTP map. Markovian structure you have to worry about if you want to write it as an evolution of a differential equation. But I'm not using that. I'm using a discrete map.
Okay.
And so as long as the initial state is nicely factorized between the system and the environment, it generates any possibility allowed by quantum theory.
Okay, okay.
Okay, there is no restriction.
Any more question? So if there is no more question, then we can thank once again Professor. Yeah, we once more thank Professor Patel for his talk, and I also thank both the speakers in this session, Professor Piacentini and Professor Patel. And I close this session. Okay, thank you.
Thank you, Dr. for chairing this session.
Anything to say?
Sorry?
Dear organizer, anything to announce or something to say?
Yes, sir.
Please speak.
Yes, sir.
Please speak if there is some announcement or.
Yes, sir. Thank you, sir, for chairing this session, and thank you both the speakers for their informative talks. With this, we conclude day 4 of QFA 2021. We'll meet again tomorrow at 1200 hours IST. Bye. Good night. Thank you.
Thank you. Good night.
Thanks. Bye.